Hello, 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 check. Hello, hello. Hello, hello, hello. Check one, two, three. అటెండెన్స్ షీట్ ప్రింట్అవుట్ కావాలంట. అది ఇంకా
Nice. వినయ్ అన్న దగ్గర హలో వస్తుందా? హలో చెక్. హలో 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 వస్తుందా? హలో 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 ఎండేమో ఇది ఎస్టీఎస్సిఎంసి కాదు కదా, వేరే అది పెట్టారు. నాకు ఒక ల్యాప్టాప్ ఉంది, మనం ప్రింట్ చేయొచ్చు. నేను దీన్ని కనెక్ట్ చేసిన ఎవరైనా అరేంజ్ చేస్తారా? నువ్వు వాళ్ళది కాదు, మన బయట వాళ్ళు ఎవరైనా ఒకరు ఇక్కడ ఉండండి ఈరోజు హెల్పింగ్కి. ఇక్కడ ఒకరిద్దరు ఉండండి మీతో పాటు.
Hello? 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 Hello?
Good morning to all of you, and I would like to. This is a very important day, particularly for me, in a sense that I could organize this memorial workshop, particularly in the memory of a person who has been very much influential in a way in my, how to say, professional life, in the sense long ago when I started texture, and this is continuing, and somehow it was a commitment with Professor Arkere. Sometime he will come to University of Hyderabad, which was almost, if you see the picture there, this was taken and merged. So he said, okay, next year I'm like after US, I will come back. And somehow it could not happen. And today is the situation like when Professor Leo was coming here, then I was thinking like, okay, the idea was set up more on the correlative high throughput material characterization. Then I thought, you know, when you do the texture, which is a part of the microstructure particularly, so it's already give you extra dimension and to understand the microstructure. So I thought it would be an interesting setting to do a kind of a workshop, which is like a texture in microstructure, presenting the past, present, and future in particular, and taking the scientific legacy of Professor Ranjit Ray. So that was the point. So I would like to welcome on this day, particularly Professor Leo Keston, Professor Satyam, and Professor Pinaki also will be joining in a while, and then Professor Anand Kanjrala from IIT Madras. So even one of my, how to say, PhD mate when we were doing the PhD together at U Delft, Professor Manojit Ghosh. So it came out very nicely. So we thought, okay, let's do it in that fashion. So I would just want to share some of the points which I want to connect today a little bit, because sometimes texture is a bit of a complex subject, but I want to put some connections. I hope I am successful in doing that, because the young minds are also there on the other side. So we have the whole graded community in the audience. So the point is, like in the presentation yesterday, when my, how to say, colleague, Professor Sudarshan Pani, he was relating the character, human character, and with the material characterization together. So what I want to say here is that when you want to see the connect, particularly you are born, so born in a certain situation like the stars, and then you have an impact of it. So if you look at your birth card and you go to a person, I will not say astrologer, but you know, you can simply try to see why I am here in this world. Is there any connection? And if it depends on the person, how he will, how he has the experience in like a database, either it's a experimental or modeling, he can tell sometime better things on that. So same goes to the microstructure side. So in the sense, like if you have an idea about the crystallographic orientation in a three-dimensional space, and then you connect with the microstructure, it connects very well. So you know then who can do that? It's like some of those, Professor Ranjit Ray, for example. So if I'm blessed in the sense, like when I was reading the papers, so I was thinking like, how could you know so many things? Because in those days with X-ray, you don't see the microstructure, and you see microstructure separately. But now we are in the new generation with the EBSD, you can see both things together and connect well. So I was sometime feeling like I would have born a little bit earlier so that I could do also more things like what Professor Ranjit Ray have done, or some other, how to say, great researcher. But I'm now also feeling like with the younger audience, like they're full of options. I would have been maybe coming 2 years later, maybe AI would have been helping me, or machine learning would have been helping me. So anyhow, I'm happy the way I am here, because I can have both feeling together. So, you know, so how you do that, like this connections, You have electron diffraction, X-ray diffraction, these are the means. So today in particular, we will be having the experts who will simplify this. So I'm very happy that we were starting with Professor Satyam Suvas, who know, I think, very closely Professor Ranjit Ray, and he will connect the legacy in a personal and professional way. So I would like to give the floor and invite Professor Satyam, please. Thank you.
Well, very good morning to all of you, and it's my pleasure to be here on this very special occasion. I am indeed grateful to Professor Gautam because he called me for this, probably the most pleasurable moment for me to talk about Professor Ray. And he also told me that I have to talk about what impact Professor Ray has made in Indian texture community or Indian science, material science overall. That's why I have not kept my talk deeper into scientific aspects, which some other time we can talk. We have kept it just what Professor Ray, when he started, what way it was there and how different topics evolved through his research. But before that, I must tell Professor Ray was a great teacher, and the most important attribute of Professor Ray was he respected everyone at the same level, whether he is a director or president of the university, whether he is a senior academic, whether he is a junior colleague, and whether it is student. Everyone got similar respect from him. This is a very unique characteristic. I try to imbibe in myself, but sometimes it's very difficult. It is not possible. You need to have very unique personality. For him, every student was great. So he received an award, a Distinguished Educator Award by Indian National Academy of Engineering. And when he was asked to speak about what are the most important things in your teaching career, he said that my whole teaching career has been based on two principles. One is there are no bad students, there are only bad teachers. Second thing he said, that nobody can teach anything to anybody. That was the two things he said. Even after he is not here, people who have not worked, I did PhD with him, but Professor Jay Gautam, he didn't have any academic association except for the inspiring, he was an inspiring personality for many of them. He is organizing this workshop. So I'll just go through this. So Professor Ray lived till 2025, and he was born in 1942. And he was one of the persons who, as a small child, immigrated from India, Pakistan, this thing. When he was 7 years old, he had to come from East Pakistan, stayed in a refugee camp in utter poverty up to school. He came one of the top students in West Bengal State Board, the whole state. And then after that, he came to the famous Bengal Engineering College, that time now it is called IIEST. He was admitted, that time IITs have started, he was admitted to IIT Kharagpur, but just because of his economic condition, he told me once that he couldn't afford to go out of Calcutta to study, so he stayed back in IIT Kharagpur and probably IIST Shibpur, that time Bengal Engineering College, probably it had a similar stature that time in metallurgy. So his entire education up to one PhD was in Bengal Engineering College, and then he continued to teach there. Later he went to do PhD at University of Birmingham, where he worked with Professor Bevis Hutchinson and Professor R.E. Smallman. And one of the first few works that he has done, I'll show you a little bit. I think Professor Leo Keston will elaborate on that more. Then he, after coming back, he joined IIT Kanpur as a professor, where he had about 3 decades of distinguished career, and many people came out of that. And then post-retirement, IIT Kanpur, he worked in Tata Steel for about 10 years as a consultant or visiting scientist. He was my guru in all respect. Guru means not only a teacher, but also the person who improves your personality, who gives lots of things to you, who enlightens your mind. That is, in India, we call him guru. So he was my guru. I joined PhD in the year 1994, purely because my master's thesis in the same institute was with someone else, but I joined him for PhD just getting impressed with his teaching. I took one of his course, and it was like eating sweets, right? You will get the same feeling when you hear his lecture. So he used to, and then I was so impressed that I joined him for PhD. And I was his 9th of his PhD students. And then our collaboration flourished further, and towards it ended up in a textbook which is reasonably well known amongst the student community particularly. And also another aspect of Professor Ray, before I go into the research that he has done, he was also a very good writer on a general topic. So he wrote a book, The Global Man. This is in the name Rakura, Ranjit Kumar Ray. And this is totally non-academic book describing social and political context starting from Indian freedom movement till date, how society has evolved and how a global man should be. I never knew this aspect of Professor Ray, but during Corona time he wrote this and he shared with me. It's a very nice book, everyone should read it. He has been a very active researcher all through his career, and his last affiliation was AICT INA Distinguished Visiting Professor, where he mentored 2 institutes, SRM Institute in Chennai and CMRIT Bangalore. And one of his last contributions was one of the book chapters that I co-authored with him. And these are the things. Up to 2025, he wrote the year he died. In fact, the proof correction of this was done by him 1 week before he passed away. So this was a great thing. He has worked on various materials from 1970 onwards. He has contributed to Indian texture community. He has worked on various materials. This copper and copper phosphorus alloys were his PhD topic, where he also continued a little bit of work after coming back. He was one of the early ones to work on dual phase steels, a lot of work on nickel alloys. Then when intermetallic era came, he worked on nickel aluminide, iron aluminides, titanium aluminides, IF steels, IFHS steels. This was during his Tata Steel stint. He also worked on superconductors, so that the rabbit process, what people call, he worked on that. Dr. Pinaki Bhattacharjee has done his PhD on this. And then the coated steels. There may be other topics also, but these are the important ones that I could get. Many important people, excluding me, they have been graduated from him. This is the list. Professor Manna, who is a very famous metallurgist now, he started his texture career with Professor Ray. Then these are the people. Dr. Ghosh Chaudhary, Director of National Metallurgical Laboratory, and so several people have worked with him, right? So this is these are the poll figures that are from his PhD thesis, and this was on the this has an outcome that the deformation and recrystallization texture in pure copper, which were determined using a Siemens texture goniometer, the results were plotted as a pole figure, and in situ experimentation those days in high voltage electron microscopy he heated the foils, and then after that he realized that he extracted cube oriented nuclei. So we were just discussing before this talk how people used to correlate the misorientations and all that. So this was done, and then he also measured the pole figures. That time this is 95% cold rolled copper, and this is the annealed copper, which clearly shows cube texture. But this is not just an observation. That time there were competing two theories were going on: oriented nucleation theory and oriented growth theory. And probably this was one of the first evidences where it was shown that by texture analysis that oriented growth theory does not explain the predominance of cube texture in recrystallized pure copper. So it was oriented nucleation theory. The most important part which I wanted to tell, that these days we get into arguments and some kind of it turns out to be animosity if you propose something which is not favorable to your opinion. This was Professor Ray worked with Professor Hutchinson and his group for oriented nucleation theory supported, but he also worked with Professor Kurt Luke after that, who was oriented growth theory, the proponent of oriented growth theory, and he also worked with him. So he could work with people with diverse opinions without having any conflict, and he was again a very favorite person with Professor Luque. So this is, I think, I could see quickly that Professor Leo Castens is going to talk about this. These are some of the micrographs which were recorded by Professor Ray during his PhD. He that time to find out the mechanism of nucleation was very difficult, and he has done this heating in the TEM and found the origin of this nuclei, and later he has explained it. Also time resolved microscopy, which ones will grow and how this so-called pancake shaped grains are coming up. This was shown under annealing in high voltage electron microscopy. Later on, as I mentioned, that in IIT Kanpur when he came, Professor Manna did work on titanium added nickel iron copper alloys, where the optimization of annealing parameters were done to develop a strong cube texture in NiFeCO alloy, which is a magnetic material, and cube textures are very important for them. And it appears that 98% cold deformation followed by annealing at 1050 degrees C for 2 hours in dry argon atmosphere constitute optimum conditions for the desired texture development. This was from the thesis of Professor Indranil Manna, and this was measured by, I can tell you, there was a manually operated texture goniometer in Kanpur. So where you rotate all these chi angle by hand, you rotate, take the intensity from the digital display, note it down, again go to another position, note it down, and likewise you can, in 1 week probably you can measure the pole figure. So that is how he has done it. Professor Manna did it. So, and this is one thing. Then a very important work that came up was texture transition in nickel aluminide based intermetallic alloy. This was done by 2 of my contemporary PhD students of Professor Ray, Dr. Ghosh Chaudhary, who is now Director of National Metallurgical Laboratory, and Dr. Bhattacharya, who works in Tata Steel. And there, first time again it was shown, Professor Ray has done many things for the first time. So he has shown that a boron doped nickel aluminide and nickel aluminide with boron and zirconium, they undergo literal texture transition from copper to brass type at higher reduction level, and this transition was associated with phase change in materials from the ordered L12 to ordered DO22, and this was assisted by a twinning mechanism which was explained by these things, and it was done very rigorously by line profile analysis and orientation distribution function analysis, appeared in many papers written by these 2 PhD students. This was another important work that he did this was done exclusively by Dr. Pinaki Prasad Bhattacharya. I don't know whether he's here or not. Dr. Pinaki Prasad Bhattacharya has worked on coated superconductors where cube textures are highly desirable because you get maximum critical current density if the material has a cube texture on it. So it has to be deposited on yttrium barium copper oxide. So this was nickel 5 atomic percent tungsten alloy was used, and he optimized the condition of obtaining strong two-stage rolling by two-stage rolling procedure followed by annealing for the development of long flexible superconductors with high critical current density, which need a substrate tape with sharp and stable cube texture with as low misorientation angle at drain boundaries as possible. So this was done with lot of rigor, and this is the one which we could see that this is 99.5% grains are cube oriented, and this there are a very small fraction of these boundaries. This is the boundary analysis. We could see that most of the misorientations are within 15-degree range. Another important work that he did is on texture in IFHS steel. So here, for the first time, a strong correlation between precipitation, texture, and mechanical properties in IFHS steel was established, and the deleterious effect of iron, titanium, phosphorus precipitation and the way and the means to eliminate its formation were highlighted in a series of publications. This was the work by Pampa Ghosh and Chiradeep Ghosh, who did PhD with him. A very rigorous work was done, and textures were measured for that. IF steel work was done by other researcher called, his name is Rajiv Saha. He is also working in Tata Steel, and here he has shown that IF steel forms very sharp textures after severe cold rolling along with the formation of nano to ultra fine grains. The CSL boundary fraction increases continuously with deformation, and these seem to have a strong influence during cold rolling, recrystallization and grain growth stages. And this was again very strong gamma fiber and alpha fiber, we could see here very clearly. Then another work was done on coatings. So galvanizing and galvanizing and galvannealing processes, the coatings develop very strong fiber texture, and this whole work was done by Anirban Chakravarti, who is now in some steel company in the US. And he developed, through his thesis, a new insight was given on how formability and powder characteristics of coating can be influenced by, they can influence the textures very strongly. This was my PhD. So what I did was to work on titanium aluminides with niobium containing titanium aluminides, which were gas turbine materials that time. It was very strongly emphasized in those days in mid-90s, and there texture development was an important topic because different textures would decide different mechanical properties of these materials, and then we have analyzed it. Processing was difficult, and characterizing texture was even more difficult because to measure hexagonal texture, I was the first one that time to start hexagonal texture measurement, and then it was very difficult to get the ODFs done. Some way we managed it, and in fact we worked together, right, to get orientation relationship between alpha and beta phases in this alloy was a big challenge, and we did a lot of work in that direction. Then this is a very important work. It preceded all our works by Dr. D.K. Mandal, who was assistant professor, who was a professor in NIT Durgapur, and he worked on deep dryability in a cold roll and recrystallized dual phase steels. This was one of the early works on texture of dual phase steels, published in 1992, but the thesis was done much earlier. And here, very importantly, it was established that although reasonably strong 111 fiber texture could be developed in this steel, which is known to be a guiding parameter for most of the material for very good formability. So it was developed, but this did not reflect into a high R value that is required for satisfactory deep dryability, because you can see there very high R values are obtained, more than one it is here, but it couldn't happen, and Professor Ray believed that it is the whole expansion ratio that decided the formability of this material, and then a lot of further work was carried out in this direction. There was another work again by Dr. Arunanshu Haldar, who who is now again Vice Chancellor of some university in Rajasthan. So he worked on ferrite rolling of extra low carbon steel during, this was warm rolling in ferritic region, and there he developed this was a unique work, that the practice of rolling in upper ferritic region instead of in the austenitic region has been termed as warm rolling, or alternatively ferritic rolling. In this steel, the gamma fiber texture develops at lower warm rolling temperatures, and a weak alpha fiber develops at higher rolling temperature. And just the temperature of deformation itself could optimize the gamma fiber fractions, and then high density of deformation bands were identified during the course of rolling. Right. Now I am little bit emphasized on this work, which was closest to Professor Ray. So this work he did on nickel and nickel iron, nickel cobalt alloy. This has this problem of brass type formation of brass type texture in FCC materials. He worked with a very important texture scientist, Dr. Torben Leffers, and they contradicted many of the existing theories, and these texture theories were not so well established. It was considered as a 50-year-old puzzle. Since 50 years people gave different theories on this texture evolution, brass type texture formation in FCC materials. For the students, the brass type texture is the one where brass component dominates, 110, 112, where your unit cells will look like this, most as if you can see the unit cell in a sheet, you can see them, all of them oriented like this. And this is the copper component. Of course, copper component also, copper type texture also has some brass component and S component, but these are the dominant texture component. So the transition from high to low stacking fault energy material is accompanied by copper to brass transition. So this was very close to Professor Ray's heart, and many years later, after I joined as a faculty in ISC Bangalore, and he came and he told, why not to start some program and close this chapter, because now you have all the tools like EBSD and others, we can very closely examine and close this issue. So we prepared the alloys where the transition was clearly observed, nickel 40 cobalt and nickel 60 cobalt alloys, deformed them, and we examined textures very clearly. These two, in this alloy, the texture transition takes place at a larger deformation. You could see here that still at a lower deformation, like up to 95% rolled condition. We have strong brass component, but we also have copper component. But if we go from 95 to 98% rolling condition, we have almost vanishingly small intensity of copper component, and brass component strengthens. While in nickel 60 cobalt alloy, we have brass component from the beginning. It just as a function of rolling from 40 to 98%, it strengthens, and there is no copper component present there. So both the cases we get brass component, and then the mechanism to unravel the mechanism in this, we carried out rigorous EBSD examinations for nickel 40 cobalt alloy, which was a kind of medium stacking fault energy material. We could see at 70% sparse deformation twins, and so the twinning theory which was proposed by Wasserman was, and time and again rebutted by Dr. Torben Leffers. It was revalidated here that the twin fraction was very small. Twins were there, but these twins acted as a cause for a kind of a restriction in the deformation, and then at very large deformation, at say about 90%, the shear band formation was initiated, when the shear bands were the main responsible cause for the texture, for brass texture formation. So we examined it very carefully, shear bands, and then also we saw the nucleation in the shear bands. That was another aspect of this investigation. Then we did pinpointed investigation here. We just took for nickel 60 cobalt alloy just to understand which grains twin and which ones are stable. So we figured out two grains like this green and kind of pink grains. You can see that we deformed without changing the positions. You could see that even from the initial condition to 30%, there is no change in color of grain 1, right? This is 110 type of grain. So these grains remained stable, just orientation spread was there, but you just see the grain 2 with increase in deformation, you see that it started changing. This grain is shown here. It started forming twins, and more twins, and then this led to the complete reorientation. So we could see the stability of these Gauss grains here just as a result of orientation spread, and we could see the transition of this grain, this copper, close to copper oriented grains, and we could see that how twinning takes place and consumes the entire grain and reorients it to this. So 110, the grains with orientation close to 112 parallel to ND are prone to twinning, increase in fraction of twins with deformation. So we correlated how the orientation change takes place. And for a very large deformation also, we could see that in this case also, it is finally the strongest texture that was formed as a brass texture was related to shear band formation, brass type shear bands formed, and we could evolve the hierarchy of deformation. And we could correlate with lots of other works which were done, and we proposed a twinning, shear band, deformation band, how they assist in texture transition, what are their individual roles in which stacking fault energy range. That was established, and this work was published as 2 papers in Actamite and 1 final overview paper in Philosophical Magazine. And then we gave a clear path of brass texture formation by modifying. This was the path proposed by Wassermann, who was proponent of twinning theory, and we could establish that there is another sequence that is possible. This was Wassermann's way of going there, and we could see that no, we need not go through this route, rather we can go like this by planar slip and shear banding. We could get this Gauss and brass orientation very clearly, a brass type texture we can get, and then so this was modified, right? Now I come back to again how textures evolved in India. So now there are important notable developments have taken place in Indian texture community, that in 97, 98, 2 important developments have taken place that turned around the Indian texture research. 97, the first ever conference dedicated to texture was organized in India at DMRL, Hyderabad. And this is the proceeding of this conference, where 23 papers were presented and very important people came, 10 international speakers, right? Professor Bunge, Professor Van Houte, Professor Dagan, Professor Rollet, Professor Khalid, Leffer, Sarasay, and Jata. All these people came, and it was a very vibrant. This was my first international conference I attended, and really I was sold to the quality of this conference. Excellent conference. It was then. Very rarely we see this kind of conferences. And in 1998, this was again very important thing. This gentleman came to Indian texture community. He's the only one probably out of all the active texture people in India, other than people here in this room, who is not related to Professor A group. He worked with Professor Roger Doherty and came back. Professor Indradev Samajdar, he joined in 1998 at IIT Bombay as assistant professor. Then he developed this National Facility of Texture and OIM under his leadership with supports from different funding agencies, and that has really nucleated and accelerated texture research in India. So a lot of credit goes to him, and those who know him well, his energy and enthusiasm is beyond comparison. He's excellent, right? Excellent person. You will hear online his talk this afternoon. And he is the first one who started EBSD work in India. When he was doing this work in India, he was still in Europe. I did in Europe, but in India, he was the first one who started. And the texture, so there were four international conferences were organized. In one, first I mentioned in 1997 in DMRL. 2008 it was in Tata Steel, where I think Professor Leo Keston also came in Tata Steel conference. Then there was one in IIT Bombay, this ICOTOM was organized. And then there was another texture conference, 2017 was organized in ISC. And there are several workshops, maybe more than 10, were organized 2-day, 3-day, 1-week workshops we organized just to propagate the texture knowledge in India. So these were the important initial centers of textures in India. So initially it started all from Kanpur, Professor Ray's thing, an academic institute. Later on it went to SAIL R&D, where again Professor Ray, some of the students also worked there. And then Jamshedpur, Tata Steel Jamshedpur. Then in R&D labs it was in Hyderabad. And then IIT Bombay. Then it came to ISC Bangalore. And then now, at this moment, you see there are so many places texture activities going on. So it all started with Kanpur and spread all around the country. Now, where the texture is going now from here? So Professor Ray always liked this picture, and this was a picture, it's a very famous book by Annibale Carrassi, right? Domine Quo Vadis, where Christ is running away with the cross, and he is asking I think Saint Thomas or Saint Peter, he was just seeing him going ahead, and he gives him direction how to go about. So the message is we have to constantly keep changing, right? So your goals constantly keep changing. So Professor Ray, towards the later part of his career, became very fascinated with the role of grain boundaries, particularly special boundaries on texture, and he did a lot of work, particularly in IF steel. He correlated the evolution of gamma fiber with CSL boundaries. This was again Rajiv Saha's work. And later on, Professor Rollet also, they also collaborated with Professor Rollet, and the textures were correlated with CSL boundaries. A lot of conclusions were drawn that different CSL boundaries were identified in cold rolled IF steels, and the prominent boundaries during cold rolling were these. Then during recrystallization, again these boundaries evolved, excluding, so there was one extra boundaries was seen, that sigma 13b is a very important boundary in steel, and this can be related to change in volume fraction of texture components. And the plot shows the drastic increase in fraction of these boundaries during grain growth. Most of the CSL boundaries during grain growth are related to rotation around common 111 axis. Now, again, Professor Ray he has a belief that the recrystallized grains are not equiaxed. Though normally what we see them in two-dimensional sections, they look more or less like equiaxed. He always said that these are pancaked grains, and he has this evidence, intuition from his PhD thesis, one of the slides that I have shown, where all these recrystallized grains were pancake-shaped grains. So when this 3D EBSD came in, so he just requested Dr. Arup Das Gupta, he was the first one to have it in IGCAR. And then some investigation was done, and he indeed saw that in the cold rolled multipass material of 9 chrome 1 MO steel, where the grains were elongated. Now when it was annealed and recrystallized, again the recrystallization also led to pancake shaped grains. So he was very fond of this picture, and he was showing, actually all the pictures that I am showing, all the slides, because I was entrusted to make slides for him. Towards the end, he was not very familiar with all these things. So I had all his repository of his slides, so I picked up things from various places, and I did it. Another thing which he always believed, that the role of internal stresses in the microstructure is very important, and again this work he did with one of my PhD students, Atanu Chaudhary, and he realized the region for recrystallization, and he saw that by plotting this grain orientation spread and grain reference orientation maps, he saw that the microstructural evolution is clearly related to the internal stresses that are localized in the microstructure and in the grain, and so does the texture evolution. And there was very detailed paper we have published in Acta Materialia, and there we have shown how it is related. So he said that the whole science of microstructure has a separate tetrahedron. We know that processing property, microstructure relationship, there is a tetrahedron by Ashby. Now, this was a tetrahedron Professor Ray always plotted, is microstructure, texture, grain boundaries and internal stresses. He always put as fourth corner of this, and he said that the microstructural characterization should involve all four. They are so correlated that you can't explain any phenomena without using all these in a holistic way. And he always said that initially people have certain views, or we get certain views by our observation, but it's not a good idea to keep that view completely strict. He said that a true scientist must always be ready to change his mind in the light of new evidence or better viewpoints. Actually, this was a statement by Professor Jan Delamore, who was again a towering personality in texture. He said so. Yeah, this picture comes again because of my, so this picture is by Italian Baroque master Annibale Carracci, housed in the National Gallery in London. Depicts the emotional apocryphal encounter of the Appian Way, where St. Peter, fleeing Nero's persecution, asks the vision of Christ, Lord, where are you going? So that is what it is. So Professor Ray always said that we must think of future of our discipline. So he said that he has pointed out four things. One is a coordinated approach to study all four parameters: texture, microstructure, grain boundary distribution and internal stress. They may ultimately lead to the development of holistic materials models to the benefit of material scientists and engineers. Then he said that newer areas of texture application in different materials must be explored. One such example is materials produced by additive manufacturing. Some variants of AM have shown capability to induce strong crystallographic texture in metallic materials using laser or electron beam powder bed fusion and directional solidification. The interrelationship between the textures obtained and the parameters of the adopted procedure are yet to be properly established. Then he has told that we must jump into the applied research, and this is an example that he has taken from an implant, orthopedic implant, and he said that how these implants have also very strong orientation characteristics, and they can be texture engineered to give the better performance. This is from some reference. And also the turbine blades. The turbine blades are a classic example of texture control, where one part of it, the aerofoil, it requires a unidirectional orientation or texture, or as close to single crystal as possible, because this is the part that goes through the creep deformation, and the dovetail has to be a random texture. So this gives you the optimal performance. Again, he was very clear about that biominerals and biogenic ceramic materials vital to the host's organism survival. As structural materials, biominerals are evolutionarily optimized to obtain both high strength and toughness. Thus, these materials, biologically generated ceramics that address classic material design challenges, are how to generate hard or non-brittle materials. And this is one such example is the outer calcite shell of black clip pearl oyster, which is made of layers showing a gradation of texture from very weak to strong. And such texturally graded bioceramic exhibit intrinsic toughening properties similar to those found in compositionally graded synthetic materials. So this is what he said. Now this is some of the memories of Professor Ray when he was little young, giving lectures, meeting various scientists. I think these are not very clearly. This is Professor Laszlo Toth. Professor Bonge is here. He was very fond of going to conferences, attended most of the international meetings. In the time when country was resource deficit, he used to start applying to various funding agencies, writing letters, get money, but he always attended these scientific meetings, right? This was the last one that we had in Icotome. We had a session organized in honor of Professor Ray in 2024 in Metz. And all these people are belonging to Professor Ray's group. Professor Hutchinson is there, Professor Ray is there, myself, Dr. Bhattacharya, and several others are there who are his direct PhD student. then my student Nilesh Gurao, he is there, his students are there. So that way 6 generations were taken together. Many people attended this conference. Here you can see many people which was organized in Professor Ray's honor. So with this, I conclude my talk. I just tried to take you through various research topics that Professor Ray worked. It was not possible to go in detail of all these things, but each paper of Professor Ray is a new work. Whenever I used to do some experiment, and as a young researcher, you feel that all your results are very novel and it must go to a paper, publication. And then he used to ask one question in Hindi, "Isme naya kya hai?" That was the question. I will translate it for you. What is new in this? Means if the phenomena, you are just giving an example of an established phenomena. So till something is new, he was not accepting to take it forward. Whether there is a deviation from established knowledge, right, or a new knowledge, right? If it is an example that, he always used to say that without your telling, I will say that you reduce, the example is for copper, if you reduce the grain size, your yield strength will increase. Tomorrow you take molybdenum and do the same thing. Even though nobody has published, it is known that you reduce the grain size, the yield strength will increase. So what is new in this? So you get something new before you bring it to publication stage. With this, I think I was able to convey. It's very difficult to talk about all his academic legacy, but some of the things I try to highlight, and I think I have severely exceeded my time.
Yeah.
Thank you very much for patient listening. So I think.
Thanks a lot. I think because of the time, maybe we'll push the questions on the other side, but I think there were very clear messages for us to take away and for the young minds to take away. So thank you, Satyam. Next speaker is Professor Leo Kasten. You know now he is a university chair professor at University of Hyderabad. Of course, a brief time. I think yesterday we were discussing with Professor Satyam. Keep on coming. I think that's what I can simply say. Find it as a second home. We have a lot of people here looking for you. Thank you.
Thank you, Jay, and thank you for your wonderful hospitality and accommodating me here in a busy schedule. It was great, and it was a very grateful week for me, memorable week. We had already very interesting discussions with your colleagues, and you obviously with your colleagues, your students. So, and of course, I'm very much looking forward to extend our collaboration in the future. So also thank you for giving me the opportunity to speak today here on this tribute symposium for Professor Ray, which was indeed a very exceptional personality. So, who was a very exceptional personality. As I was not his direct student, so I never formally worked with him as a student, but nevertheless, indirectly, he has a great effect on me because he was not only, I have had plenty of discussions with him. I met him at various occasions, many conferences. I will come back a little bit to this. And but apart from his outstanding scientific content, Professor Ray was also a very eminent personality. It's like really, Professor Suwa said, it's he made you, he respected everyone, and you felt this immediately. You felt respected. So if you discuss with him, it always was a memorable event, something that you took home, and you whenever I went to an event and I knew Professor Ray would be there, you look forward to meeting him. That was he had a very amiable, sympathetic character. That was undoubtedly true, and it was outstanding also from that point of view. So let me go back to the early origins of his work. Actually, he did part of his PhD, I think, in University of Birmingham in the early 1970s, long ago. And he was part of what I would call a golden generation there, because he closely worked together with Professor Hutchinson and also Professor Duggan. Now, all the three of them, they became eminent scientists, and they belong to the first generation of founding fathers of what became the international texture community. So they did not only do excellent work, but they also grouped together and later on spread the word, I would say. So they went to various corners of the world, but always kept in real contact and created this community, which now lives on, in fact, even already second and third generation. But we are still proud to carry, to maintain some of the traditions that they have initiated. And why it doesn't work? Okay. So one of the earliest papers, it was submitted in September 72 by Ray Hutchinson, Person Bisach, and Professor Smallman, who was it was on in situ work on recrystallization of pure copper, pure and somewhat alloyed copper. And I will now, this was a very special work. Why? Because actually, and as I was rereading a little bit these papers for this talk, they were written in the early 70s, more than 50 years ago, but still today they read as what you just said, something new in there. So actually they were so remarkable in many different ways. First, because of the language, they directly speak to you. They are if you read these papers, they are as lively now as actual now as they were 50 years ago. That was one thing. Second thing is that the remarkable experimental skill that went into that work. So think of it, they did in situ transmission electron microscopy, that the annealed samples in the transmission electron microscope made video recordings, analyzed and interpreted the data without any modern day support, no computers, no data post processing. Everything had to be done manually. And for example, they did not have FIP software, FIP microscope to prepare the sample. If you would ask someone to do similar work now, the first thing that's, oh, where is the FIP so that I can prepare the sample? They did this work, mind you, on 95% cold-rolled copper sheets, and the copper sheet was 0.12 millimeter thick, 0.12 millimeter thick, and they did transmission on the TD section. So how did they do this? Well, they developed an ingenious technique. They electrolytically deposited copper on either side of the very thin sheet, on top and bottom, and then they had a thick enough sheet so that they could take a transmission and a TEM sample perpendicular to the transverse direction. Genius, just incredible. And that's also something that we should take away today. Use your imagination, use your creativity if you do experiments. Don't always go and look for the most, so all of us also today, we are facing limitations in our work. We don't have all the equipment that we would like to have. We don't have unlimited resources. But even at that time, 50 years ago, with limited resources that were at their disposal, they did genius work. Okay, so and what was this remarkable feat that they observed? Let's go. So later on, a little bit later on in 1975, everything was summarized in a very important paper in Acta Materialia by Ray, Hutchinson, and Duggan. And actually, they observed, this is cold rolled and this is annealed at 200 degrees C. And they observed, in fact, during static recovery, they observed migration of subgrain boundaries. And that's very important. So I want to just to guide you through a number of the conclusions of this paper, the Acta Mat paper, and I want us to walk through this because we will take it to the future. So they observed nucleation of static recrystallization observed in situ on TD samples in copper cold rolled 95%. So the material examined, they observed considerable recovery involving migration of subgrain boundaries. So you had these subgrain boundary bands, and they increased in thickness. They positively observed this. They also observed the bulging mechanism. So at the start of recrystallization, the subgrains with a lower dislocation density were bulging out in neighboring subgrains with higher dislocation density. And this was one of the main recrystallization mechanisms. And also they highlighted the role of mobile high-angle grain boundaries in this process. Okay? So now let's shift gears to today. So recently, well, I mean the last 2-3 years, I've been working together with a group of people on a long-standing problem in texture study in steel. And what is the problem? It can be briefly summarized as follows. So if you cold roll, for example, a low-carbon steel, IF steel, for example, to 80% reduction, and you cold roll, you get this typical alpha-gamma fiber texture. If you do warm rolling, you get a texture that is very similar. What is warm rolling? Warm rolling is rolling at elevated temperature, but still in the ferrite domain. So you don't go to the austenite domain. So actually, what it says here is that the temperature of deformation does not have a major effect on the deformation texture because it's controlled essentially by crystal plasticity mechanisms which are not thermally activated. That's what it says. Okay. However, after recrystallization, the picture totally changes. So although the deformation texture is very similar, the recrystallization texture could not be more different. You have a typical gamma fiber texture after cold rolling, and you have a somehow cube fiber texture with a maximum on the rotated cube after warm rolling. Okay, so this is in literature, and this you already find back in the review papers of Ranjit Ray, very often explained by making the link with the Taylor factor, which is the crystal plasticity based measure of plastically dissipated power. Okay, so actually it says that here this is the cube fiber. These are, this should be reversed, of course. These are low Taylor factors. Sorry for that, and these should be high Taylor factors. So here the cube fiber orientations, they have a low Taylor factor. It means that they require less plastic power dissipation during deformation as compared to the gamma fiber grains, which are less favorably oriented and require more energy to deform. Okay, so now we did an experiment, and we compared meticulously this was IF steel, cold rolled 75%, and rolls, either cold rolls or warm rolls. And we compare 3 conditions. We compare the S received cold rolled condition, the static recovery condition, and the dynamic recovery. Dynamic recovery I refer to as the warm rolled condition, because the major difference between static and between cold rolling and warm rolling is that you have thermally activated dynamic recovery in warm rolling, which you do not have in cold rolling, or much less. Okay, so and we mainly see here blue and red grains. The blue grains are the 111 orientations, the gamma fiber. The reddish grains are the close to 001 orientations, what we call the theta fiber. Okay, so blue and red. What you can immediately see here is that after static recovery, you have a growth of the structure. So the average bandwidth has increased. These white regions, these were recrystallized grains. We had to disconsider them, so that's why we put them just white. So, and this is also obvious after warm rolling. Do you see the connection with the early work of Ray in the copper samples? So he observed something very similar by TEM. Now, we took it one step further. Of course, today we have all the modern analytical techniques and post-processing of EBSD. And here you could see, indeed, there is a very important difference between these 3 material states. What you see is, on the vertical axis is the misorientation gradient, or sometimes called the CAM slope. CAM is kernel average misorientation, and it's the gradient of this kernel average misorientation, which we have reason to think that this is a good measure of the stored energy. So here on the vertical axis, you have the stored energy of plastic deformation. And you can see that after cold rolling, you have, of course, the highest value. After static recovery, it is reduced, but it does not reduce to the same extent after dynamic recovery. So although the texture, the global texture of these 3 conditions is hardly any different, the internal distribution, the level and distribution of stored energy is clearly different. And so we think that this is the reason why you have such different behavior in recrystallization. So schematically, what happens, this is actually the misorientation, a schematic representation of the misorientation distribution in the blue grains. These are the 111 grains. If you have cold rolled, you have a lot of stored energy in those blue grains, but not only stored energy, you have a lot of short range misorientations. So actually, if you then have statically recovery, this misorientation gradients, they diminish, because that's exactly the stored energy. It's in these misorientation gradients. But nevertheless, you still have enough short-range differences, short-range gradients to allow for nucleation here. Okay? Whereas if you have dynamically recovered material, these blue grains, they don't have that much short-range misorientation gradient anymore. That means not enough short-range gradients to allow for local nucleation. And that's why after dynamic recovery, that is after warm rolling, you will not have recrystallization, whereas here you will have recrystallization. We also could confirm this. For example, this is a transmission Kikuchi diffraction. This is high resolution EBSD with spatial resolution 2 micrometers. So this is a warm-rolled material. You can see there is almost no internal gradient anymore, or much less, whereas this is the cold-rolled material. You have a far larger. So here there is still potency. There is a potential for subgrain growth migration. Exactly the mechanism that was described by Ray in this early paper from 1975. And we didn't leave it, so okay, this is, I can skip that, I already conveyed. We didn't leave it like that. We also developed a model. This was actually published in the PhD thesis of Konstantina Traka. It's which was in collaboration with Max Planck Institute. And this is a cellular automaton model. And it's entirely based, it's a grain growth model, in fact. Grain growth based on two, sorry. Actually, this is the only physics in the model. There is a mobility law, which simply says that low-angle grain boundaries have low mobility, and high-angle grain boundaries have high mobility. And there is an energy law, driving force, which is simply based on Reed-Shockley. So you all know the Reed-Shockley equation that establishes the relation between crystal misorientation and grain boundary energy. And we assume that this drives the entire system. So actually, these are the evolution laws of recrystallization. And now you apply this to the microstructure of the substructure of the deformed material. And the relation that the results that come out are truly remarkable, because you can see this is a 80% cold-rolled IF steel, and the annealing temperature was 800 degrees. The annealing temperature determines the activation energies of the mobilities. And you can see this is the alpha-gamma fiber. It doesn't look really nice because for time limitations we had to shrink the surface on which we did the model. We ran the model. But nevertheless, you can recognize the alpha-gamma fiber texture. Okay, fine. Now you have 81% warm-rolled, iron 3% silicon. We did iron 3% silicon because it doesn't transform. You can go to very high temperature and you still are in the ferrite domain. I said what we understand with warm rolling is rolling in the ferritic domain. It's rolling in the ferritic domain. This is the deformation texture, and these are the models. And you see what comes out. Exactly the same model. We didn't fiddle any parameters. So the same evolution laws. Now we obtain a very strong cube fiber in the recrystallization texture. And you also can see it here. You can see that after cold rolling, you have a lot of internal nucleation inside the blue grades, because there is the orientation gradient. That's where you have the stored energy difference.
You still have
5 minutes, okay, good. So I'm going to close, and actually I have mainly learned to know Professor Ray through two very important review papers that he has written. And actually, I have a little story to tell about one review paper is about transformation textures. It was written in 1990, and both were written with Professor Jonas. And the second review paper was in 94. And the first time, in fact, I started my postdoc at McGill University with Professor Jonas, and I arrived there in May 94, May 94. And the first day, I still remember, I arrived in a weekend in Montreal, in McGill. And at Monday morning, I went to the office, to the department, like a first day at school, so to say, of a first-year student. And I was welcomed by Professor Jonas in his office, whom I already met. And there also he introduced me to Professor Ray, which I didn't know really at that moment. So I shook hands and we met and we met. And what happened then is that only later I realized the importance, because they had just finalized this paper. They had just finalized this masterpiece. So it was as if I met for the first time two giants, in fact, in one room, who collectively finalized one of their opus magnums in texture research. So only later I was ignorant at that moment, and I realized the importance of that moment. So I was very privileged to watch this from up front, a masterpiece in the making, so to say. And yeah, there are many. I strongly encourage, if you're interested in texture, in steel, to read these papers. They are still the basis of everything what you need to know about it. For example, I very much like this picture, comes from this review on transformation texture. It shows the hot band texture of three different structures, namely polygonal ferrites, diffusion type transformation, acicular ferrites in short range diffusion, and martensite ferrite no diffusion. And the intriguing thing is that they all look very similar, which for me is always very mysterious, because these transformation mechanisms, they are very different. If you look at the structures, you can see the difference with your eyes closed, so to say. But if you look at the texture, they're very similar. You couldn't tell the difference. And this has main repercussions on how we analyze the phenomena. And then I come back to what Professor Suwa said, like we have to, looking at the texture aspects of physical phenomena in metallurgy is a really useful way. It tells you something about the reality, about the physics, what is going on. So unfortunately, I don't have time to go into detail. This is another picture of that review paper. So Professor Ray always had you also mentioned it, a very keen eye on the process. Metals are made by specific processes. So look at the detail of the processes. And that was some of the work that I did for my PhD long ago. And okay, I will not go into details, but I just wanted to say that the conclusions that that we arrived at that time in Leuven were in perfect agreement with another paper of Professor Ray in Acta Materialia. So very two independent confirmations of behavior, which in industrial research is quite exceptional. Okay, so I'm going to finish here. I would like to thank Professor Ray for his legacy, for what he did, but above all for the person that he was. He was a true a guru indeed in the good and the meaningful, valuable meaning of the word. Thank you.
Thanks, Leo. I think, can I invite one question? Just if you have any query.
So good morning, Professor. I have one question. So in one of the slide, it was mentioned for the statistically recovered and dynamic recovered. So what are statistically recovered and dynamically recovered slide? So what are the potential nucleation sites, like subgrains or shear bands, for the dynamic recovery to happen?
Very good question, very short answer and clear answer. Wherever you have gradients in stored energy, and this is gradients in misorientation or grain bound in subgrain size. So, and this can happen at various locations in the microstructure. It can be inside shear bands, it can be at previous grain boundaries, it can be in deformation bands, but look for local gradients in misorientation. That's my answer.
So according to that, particular slide. So statistically recovered do recrystallized and dynamic recovery do not recrystallize. So they
No, they both recrystallize,
Okay.
but they, of course, also dynamically recovered material will recrystallize, but different crystal orientations will recrystallize because they have different gradients of misorientation. So in the cold rolled material, you have strong gradients in the blue grains, the 111 grains, and these gradients, they are reduced somewhat by statically recovery, but not reduced to the extent that they limit the potential for microgrowth selection, for micro subgrain growth. Whereas in the dynamically recovered, the internal orientation gradients in the blue grains is on average not large enough to generate large-scale nucleation, whereas only remains there the gradients between the red and the blue grains.
Thank you. Thanks, Leo. So I'll move to the. Okay. Then I will request Professor Satya. Leo.
Sorry.
Just to capture
Yeah.
the memory, I would. So I'll invite the next speaker, Professor Pinaki from IIT Hyderabad, and yeah. So we are just chronologically going down. So okay, all yours, Professor
Sure,
Pinaki.
sure, thank you.
You share the clips.
Thank you for your kind invitation. So, myself is Pinaki Bhattacharya from Department of Material Science and Engineering from from IIT Hyderabad, and I was Professor Ray's one of the probably the last students, because by the time we finished, Professor Ray has already retired and has moved to Tata Steel. So after the PhD, I did not really work that much with Professor Ray, but today I want to go to talk about something which Professor Ray truly believed, is that microstructure is key to understanding texture. And that is the paper when I joined first. So he gave me a paper by Professor Torben Leffers, which was published in that conference that was held in Hyderabad. That is Microstructure, the Forgotten Factors of Texture Analysis. So this is a kind of a tribute to what little I have learned from Professor Ray. So crystallographic texture, the better half of microstructure. Okay. By the way, better half is a gender neutral term. Okay, English is a funny language. Better half is a gender neutral term. Okay, dictionary wise it says a person's wife's husband or partner. I emphasize on the word partner, and I will try to highlight that this talk that crystallographic texture in many cases is inseparable from microstructure. It is a manifestation of what is undergoing. Okay. So I will give 3 cases. I do not have whether I don't know, because I have not really followed the time that given, but I will, in case there is a shortage of time, I may skip one of them. So the case 1, I will talk about effect of prior recovery on recrystallization cube texture in aluminum magnesium alloy. Case 2 is deformation texture of worm roll duplex steels, and case 3 is phase separated high entropy alloys. Okay. So cube texture was something which was Professor Ray's very close to the heart, as Professor Leo Kesten said that that is actually his genesis of his own PhD thesis. And Professor Ray never really left the field of cube texture. So he came back often to the cube texture. And when I joined my PhD, he said to me that you take up this cube texture, because that time that this something called this coated superconductor substrate tapes were a very hot topic, where the nickel alloys were used and they needed a very, very strong and sharp cube texture. Okay? So in many respects, so that was the genesis of this. And cube texture is one of the probably the most simple texture and one of the sharpest texture known, because it is often a single component texture. Okay? So, and it affects actually particularly wide range of properties like formability of aluminum alloys, aluminum capacitor foil, where you need another case where you need an extremely sharp cube texture. And then there are coated superconductor tapes, there also you need a sharp cube texture. And the debate about cube texture is very ongoing that time, because he used to tell that there are two schools of thought. One was the preferential nucleation of cube grains. In his own PhD thesis, he had shown that how the preferential recovery can lead to a preferential nucleation of cube grains. And then oriented growth, the other school of thought, where there can be a selective growth of the cube grains. Okay? And what we did is that we studied the effect of worm rolling on the aluminum magnesium alloys, because worm rolling is many times is a very interesting process, because it is between the hot rolling and cold rolling, and it offers certain distinct advantages in terms of the flow's resistance and as well as a surface finish. So it's a very interesting processing route. Okay? So this is why we took a aluminum 2.58% magnesium alloy, which is basically a single phase alloy, and this is the composition, where at a very other elements were in ppm level. So it's a very high quality material that we obtained. Now what we did is that this adhesive material we actually processed initially and through various thermomechanical treatments, and then we got basically a recrystallized starting grain size starting material, and then we processed to two different routes. One is basically in worm rolling and one is basically cold rolling at room temperature. And in both cases, the deformation was carried out to a very high strain, which is basically 97% cold rolling. And normally 97% cold rolling, if you start from beginning, it is very difficult to 90, because the thickness will reduce so, so less that it is difficult to carry out the rolling. What we did is that, so the first step we did an accumulative roll bonding. Okay, so you do not compromise the thickness, and then you do the cold rolling. So essentially you reach that a very, very high deformation level. Okay, and then we did annealing at different temperatures and time, and then we looked at that what is the difference in the texture in a cold rolling and warm rolling. Okay. Now if you look at the cold roll and warm roll microstructure and texture, both show very, very typical deformation structure, and the texture is basically exactly looks the similar. There is hardly any difference. It's a very pure metal type texture or copper type texture we call it. Practically no difference between the texture in the two cases. Okay? And that is also reflected in your pole figure and also reflected in your ODF. Okay? So it's a typical very pure metal texture, which is but what happens is that when you basically, when you basically actually start annealing this material, I think there is some problem with this. Just a minute, it is keeping the slides. Can I actually connect my laptop? Just a minute. Some slides have been somewhere maybe distorted or not connected. Just a minute. Give me to connect my laptop. Sorry for the disturbance. just connect it to the internet so that I can download it from my drive, Google Drive? Is it possible? Install this. It's very slow actually, the internet. No, because it is downloaded, it's a large file, so it is taking time to download. I don't know why this file has failed. But you don't have an internet in this room?
It's there, but it's not connected.
Okay, it will be copied. Okay. Yeah. So can you connect it? Yeah. Can you please connect? So I think, sorry for that. So coming back to this, so when you look at the texture of the cold rolled and warm rolled material, they exactly appear same, identical. But when we look at the annealing texture, here I have, instead of the orientation maps, we have calculated the cube volume fraction from the cold rolled and warm rolled material at different temperatures. So I have plotted. Now here you can see that basically the warm rolled material shows a very, very high cube texture as compared to the cold rolled material. Okay? Although the deformation textures are very, very similar, but the warm rolled material actually shows a very, very high cube fraction. Now why this is so? To understand this, we actually look at that there are two possible mechanisms, as I have said, in the recrystallization cube texture formation. One is the oriented nucleation, that is preferential nucleation of cube grains from the pre-existing cube oriented regions, which they call it cube bands. And the preferential nucleation of cube grains is aided by the pre-recovered structure of the cube oriented materials. And on the other hand, the oriented growth theory says that there is a preferential growth of the cube grains due to the particular special misorientation boundary relationship. Okay? Now to understand that what is going on, why the two materials are different, we looked at the very early stage of nucleation in the cube grains, okay, in the two materials. Now what we did is that we basically did the short time annealing for both cold rolled and warm rolled material at a very low temperature and try to look at that what are the orientations that are nucleating. Now in the case of cold rolled material, you can see that here the recrystallized fraction is only 7%, and here in this case warm rolled material, the recrystallization fraction is also very similar, of the order of 9%. But in the cold rolled material, you can see that there is hardly any cube oriented grains. There are all different grains. The blue grains are the cube grains, but you do not see practically any cube grain in the cold rolled material. But in the warm rolled material, you can already see that at the very early stage of recrystallization, you can see there are many, many cube oriented grains. And the fraction of the cube oriented grains is actually, for instance here, if you look at that, it is only 1%. But in the warm rolled material is almost 30%. So there is practically no comparison on that. Okay? And now if you calculate the ODF from this recrystallized nuclei or recrystallized grains, you can already see in warm rolled material there is actually a very, very strong cube grains formation. So you can see that, so 5 to 0 degree section, you can see a lot of cube oriented grains, and due to this the ODF clearly shows a lot of cube grains nucleation at early stage. Now what we presume is that in cold rolled material, so basically these solute magnesium atoms, they behave in a very interesting way in aluminum magnesium alloys. So they strongly pin the dislocations in aluminum magnesium alloys, and due to this reason the recovery is strongly prevented. So the preferential recovery of the cube grains is very difficult during the cold rolling. Okay? And also the annealing has been carried out in a salt bath furnace, so the temperature reaches instantaneously almost, very, very quickly. So there is no time for any recovery during heating up also. Okay? So there are practically the recovery advantage of the cube grains are snatched away from the cube grains. But on the warm rolled material, it is basically rolled at an elevated temperature, and also due to the simultaneous application of your deformation. So there is a possibility that these dislocations, they may be actually annihilated by the process of climb. So there is a possibility that the cube grains can preferentially recover in the case of warm rolling, and that gives rise to your strong cube texture during the warm rolled material. So now, so if this is the hypothesis that the preferential recovery of the cube during warm rolling leading to strong cube texture during recrystallization, so how to prove it? So then prove the negative hypothesis, that if you actually snatch the advantage of the cube grain during recovery, the preferential recovery of the cube grains in the warm rolled material, will the cube recrystallization texture weaken? So starting on that basis, we actually, what we did is that we recovered the worm roll material, we give a pre-recovery treatment to the 97% worm roll material. Now, what we did is that you can see that this is the map where you can still see a lot of low angle boundaries. So, this is basically still a recovered structure, there is no visible recrystallization, and to basically prove it, we did a conductivity measurement of the worm roll, then 200 degree centigrade recovered, and then fully annealed. You can see that the conductivity of the recovered material is actually in between these two cases. So, that means that it has actually recovered during this pre-recovery treatment. Now, if this is so, it has recovered, that means the worm roll material I have now pre-recovered, and then I am annealing at the same temperature. Okay? So, remember that this material, when annealed directly at 250 degree centigrade, it shows a very preferential nucleation of the cube grains. But now see what happens. So, when you give a pre-recovery treatment, you can see the volume fraction of the cube grains, it dramatically decreases. It is only 7% by this pre-recovery treatment. Okay? So, one question is that in aluminum magnesium alloy, so the pinning of the dislocations should inhibit the both dynamic recovery as well as the static recovery. Okay? So, because that is the way magnesium atoms will behave. But what happens is that these two papers, if you look at that, they show that aluminum magnesium alloys behave in a very strange manner, because since the recovery, because during cold rolling the recovery is actually very difficult to happen due to the pinning of the dislocation, they actually retain a very high stored energy. So, when you do recover, then there is a very fast recovery that can happen. So, if you look at the two situations, then we can see that what happens without worm rolling and during worm rolling without prior recovery and with prior recovery. So, during worm rolling without prior recovery, you can see that the cube nuclei, they have very low dislocation density as compared to the surrounding. So, during recrystallization, this actually recrystallizes very quickly and you have a very strong cube texture. But when you do a prior recovery, what happens is that due to the very high stored energy in the surrounding, then this surrounding also recover very fast, because there is a high driving force for doing it. So, then the dislocation density between the cube nuclei and these are somewhat comparable. Okay? So, now this snatches the advantage of the cube nuclei, and then that weakens your cube texture formation. Okay? So, what we now did is that, so we actually, this worm roll material, we give a recovery treatment at 200 degrees centigrade for 1, 6 and 24 hours, and then we did an isothermal annealing after this prior recovery treatment at these two temperatures, 275 and 400 degrees centigrade. So, what we have found is that, and then we have measured the electrical conductivity, and the electrical conductivity is always between your fully annealed and your worm roll state. Now, if you look at the orientation map, so this is without your recovery and this is with recovery at 200 degrees centigrade 1 hour. Now, without recovery, the cube volume fraction after annealing at 275 is 60%, very strong cube texture. You do a prior recovery treatment, the volume fraction of the cube is only 23%. Okay? So, prior recovery significantly weaken your cube texture. And similarly, 400 degrees centigrade also, you can see this effect is quite visible. So, if you actually now compare so this is from also the rolling plane, I mean throughout the volume, actually we investigated this. So, for instance, when you looked at the rolling plane, so it is without recovery it is 62%, and with a prior recovery it is only 28%. So, it is significant weakening of the tube texture. Okay? But when you look at the cold roll material, you do a without recovery and with a recovery, so you can see that there is not much difference between that, because during the cold rolling cube cannot recover, but when you do a prior recovery treatment, the both cube and non-cube grains, they recover almost quite comparatively. So, there is no distinct advantage of the cube grains. So, the cube recrystallization texture is never very strong in your cold rolled material. So, from this what we understand is that prior recovery can be a very effective step in controlling the strength of the cube texture. Okay. So this is the story here. So as worm rolled, you can see here rho c, the cube, the dislocation density within the rho c, the stored energy is much lower. After recovery, quite comparable. In the cold rolled condition, it is very comparable between the cube and the non-cube. And after prior recovery, there is almost a homogeneous recovery. So basically, there is no nucleation advantage for the cube grains. So in cold roll material, it never really actually have a strong cube texture. Okay, and the prior recovery shows that it can very effective in controlling your cube recrystallization texture in aluminum magnesium alloys. The second is that we'll go is the deformation texture of worm rolled duplex steels. Okay, I think worm rolling has been, the previous speaker has already said about this. So what we did is that here is that, so what duplex steels are basically, you have these beautiful austenitic ferritic microstructures in this. Okay, so what we wanted to look at that how worm rolling affects the evolution of texture in a duplex steel. Okay. So what we did is that this steel, we actually, it is almost a 50% ferritic austenitic structure. And what we did is that we actually worm rolled this material at 3 different temperatures, 225, 425 and 625 degrees centigrade. Okay. And then we continued the deformation up to 90% deformation. Okay. So basically all the steels were deformed up to 90% at 3 different temperatures. Now if you look at the 225 degrees centigrade, you can see a very typical lamellar microstructure after worm rolling. Okay. Right. So and then after 425 and then after 625, you can again see the same kind of very ultrafine lamellar microstructure in both the ferritic and austenite phase, very regular lamellar microstructure. But something is very different in the interim range, 425 degrees centigrade. You can see that microstructure is very fragmented. So 425 degrees centigrade, this intermediate temperature of worm rolling, it actually behaves in a very different manner. And then when we look at the texture at these 3 different temperatures, you can see the typical RD fiber and ND fiber for the ferrite. And you can see that very notable example, very notable difference is in the case of this 425 degree worm rolling center. What we find is that this component which belongs to the RD fiber becomes very strong as compared to these 2 cases. Okay? And austenite texture is very expected because it is more a brass type to transition to a copper type texture. But the ferrite texture is something very surprising. If we go to the volume fraction plot at different temperatures, here this is the RD fiber and this is the ND fiber, total RD fiber, ND fiber. You can see that at 425 degrees centigrade, RD fiber suddenly peaks. Okay? And then ND fiber is the weakest. Okay? And then at the 625 degrees centigrade, it again is very comparable at the 225 degrees centigrade. So at 425 degrees centigrade, the microstructure is very different and the texture of the ferrite is also very different. Okay? Now here you can see one interesting thing is that we also looked into the kind of HATV fraction in ferrite at 225 degrees centigrade. You can see that at 225 degrees centigrade, basically the high angle grain boundary fraction within the ferrite is the lowest. Okay? So normally when you expect a deformation driven ultrafine structure formation, you expect the high angle boundary fraction to go up. But at an intermediate temperature of worm rolling, it behaves in a very different. So instead of a deformation driven ultrafine microstructure formation, the microstructure becomes fragmented. So why this is so? So actually this 425 degrees centigrade is actually the range where there in duplex steel there is a very strong strain aging phenomenon. So what happens is that the carbon strongly interacts with the dislocations and ferrite, and this interaction is not very strong at the 2 end temperatures because due to the low mobility and due to the high mobility of so it cannot effectively capture the dislocations. But the in between at the temperature, carbon is very effectively pins the dislocation. So what happens is that if 11011 slip is retarded due to the carbon locking, but 11211 slip is favored in low carbon steels. Okay. So what happens is that if this is the case, then the simulation results show that the suppression of this slip, so basically this suppression of this slip suppresses the MD fiber, while this 112111 slip promotes the RD fiber formation. So what happens is that both this microstructure, fragmented microstructure, and as well as a very strong RD fiber component indicates a strong role of dynamic strain aging in the evolution of your microstructure and texture in a duplex steel. Okay, so something which has happened at the microstructure level is actually very, very strongly reflected in the your evolution of your texture. Okay. Now I come to my last talk, because this is phase separated high entropy alloys. So this is something because it is our more active area of research. So we all know about high entropy alloys, and there are many, many fascinating properties of high entropy alloys that have been published over the years. High strain, very high fracture strain, and blah blah blah. But one way to go in the cost-effective direction is that basically you decrease the content of cobalt and nickel, and then you can make the linear alloys. So then it will definitely actually decrease your cost. Okay, so some of the compositions that we have developed actually can show, at least the composition wise, much reduced cost compared to your other high entropy alloys. But there is another way to approach this problem of cost effective high entropy alloys, is basically starting from the recycled scrap. Okay. So what happens is that this equipment and machinery with these internal wirings of copper, when they are sent to the scrap shop, so these internal wirings of the copper, they are actually mixed with the the steel. So gradually the copper enters the recycling. Copper enters the cycle, steel recycling. But copper is a very, very detrimental element because it causes the hot shortness. So one prediction is that by 2050, the copper in supply, copper in steel, will actually exceed the tolerance limit and hot shortness. Okay. And on the other hand, if you look at that, some of the e-recycling, some electronic waste, many of this electronic waste, the metallic part of the electronic waste, they contain these kind of important elements, like which are typically used in your high entropy alloys, like aluminum, cobalt, chromium, blah blah blah. But in India, the recycling is actually a very kind of very inefficient. Only 1% of the electronic waste can be recycled in our capability today. So a lot of this electronic waste are actually not utilized. So we are thinking that why don't we actually take scrap, okay, at different proportions, and then mix the scrap, and then you can get a compositionally complex alloy. So that will be a kind of a cost effective, because we are talking about electronic waste and the steel composition, which are not going to be used due to their high copper content. So now if you look at this, interestingly, all these scraps, they actually contain very, very high copper. Okay. So and that means there is actually a reason to understand how copper behaves in high entropy alloy. So what we did is that if you look at the copper is a very interesting element, it has a high positive enthalpy with most of the other alloy elements. That means it does not like no one. Okay, except nickel and etc., copper does not want to go. So copper, chromium, you can say very, very high positive enthalpy. It does not want to go with anyone. It does not have a friend. So what we are thinking is that, so we tried to understand that how copper can behave in a high entropy alloy. So what we did is that we took a low starting fault energy high entropy alloy like this and added copper, and then you can get a high entropy alloy with this composition. So this will lead to a phase separation process where how these two phases, they actually do behave during deformation and during decrystallization. So here if you look at the XRD, then they can see that you can clearly see there are two copper phases already. And then since it has a high chromium content, that gives you a sigma phase. So if you look at then the microstructure of this, you can see this beautiful two-phase microstructure. You have a copper rich and copper lean phase. Okay? And then there is a core. It is basically a core shell structure where you have a sigma phase core inside the copper lean phase. The reason is that chromium cannot go to the copper side, because due to the strong repulsion, it comes into the copper ring only. So, and then it does not segregate to the grain, or it does not precipitate at the grain boundaries, but the interior of the copper ring phase. Okay. Now, when we do the cold rolling of this, we have done it up to a very high cold rolling of 90%, and then you can see that you have this beautiful lamellar microstructure, and then you can also see that by the chromium map, you can also see that these are the kind of a fragmented sigma phases during the cold rolling. One problem with this kind of alloys is that since their lattice parameter is so close, the EBSD is not very effective to find out which phase is what. Okay, that is a big problem. So what we did is that we actually did a simultaneous EBS measurements on this. So this is after the microstructure after annealing, right? So you can see this microstructure, okay, after annealing. Then we did a simultaneous copper mapping of the area. Now you can see that these are copper deficient phase, okay, copper lean phase, and this is a copper rich phase. And you can see that in both the phases you have very, very ultrafine microstructure. So the grain size here is like a 540 nanometer, and it is like a 1 micron. So you can get actually a very, very ultrafine microstructure in both the phases. But more interesting is that when you go to high temperatures, okay, the microstructure remains the same. This is a combined EBS-DDS map. So this is the copper map, and again, if you look at the copper rich and copper lean phases, you can see that the microstructure still remains is actually very, very fine. Okay. So if I compare the grain size with the temperature, and in terms of the homologous temperature with the different high entropy and medium entropy alloys, you can see that this is the data point that falls in 1000 degrees centigrade annually. Okay? And you can see that this 1000 degrees centigrade is actually close to about 0.99 in the absolute melting point for this. And this is 0.86 of the absolute melting point for the copper rich, copper lean phase. So what you can see at the very, very high temperatures also, annealing temperature, the grain sizes are extremely fine. The reason is that because copper ring and copper rich phases, they don't have a mutual solubility, right? Because this, if the grain growth has to happen, there must be a compositional adjustment of the copper rich and copper lean phases. So that is very, very difficult unless the intermetallic phases precipitate out, because these are basically incompatible phases, copper rich and copper lean phases. Okay, so that restricts your grain growth very, very strongly. Okay. So the key takeaways for me is that case 1, recovery is a very subtle microstructural phenomenon, but it greatly affects the recrystallization texture formation. Now, dynamic strain aging is a very atomic level phenomena, but these are not separated. These are very integrated phenomena. Okay? So when you want to understand this, probably you have to look at all these phenomena together. So as I have said, for this, the crystallographic texture might be a manifestation of your underlying microstructure. So we come to the same conclusion after these 3 case studies. Thank you.
Okay. Thanks, Professor Pinaki. Because of the time, I think we will push the discussion and question in the coffee time.
Sure,
Okay.
absolutely.
Thanks a lot. So, yeah. May I request Professor Satyam to... Thank you. So we'll come back in 20 minutes after the coffee, please. So there will be 2 online sessions from Tata Steel, and the other one is from Netherlands. Let's have a picture first, and then we will have a coffee. Yeah.
आप गाना गाओ, एंटरटेनमेंट.
Let me know when should I share my screen.
I can see a screen. Did you share, sir? I can see a screen.
What? Should I? I did not.
10 minutes more. They are in the coffee break.
Okay, just if you allow me, I will just would like to share the screen and just go through the PPT, maybe one or two slides,
Yeah, fine.
just to see
Yeah.
whether it is working. Can you see my screen?
Yes, sir. I can see your screen. You can close
Okay.
the short window.
Yes.
Yes.
Now I am giving this in presentation mode. Can you see it?
Yeah, I can see. You can hide that toggle. That's all.
This one. Okay.
Click on hide.
Yeah. So the slides are moving.
Yeah, moving, sir. Fine.
There is a bit of. This is moving, right?
Yeah, everything is fine.
Okay. So you can see this slide. The title is Factors Influence Final Properties.
Yes, sir.
Very good. So I'm just. Yeah. So what I do is that let it be like this. Let it be like this. Just let me know when people arrive, and then I can start. Is that okay?
Yes, sir. No problem. I will inform you once everything is ready.
Okay. Or should I stop sharing once everyone has?
Yeah, better stop sharing. You can have
Yeah.
your person.
Correct. Thanks. Thanks.
online?
Yeah.
And then did you convey to Rene?
He will join once he joins. He said he will join by 12 o'clock.
Okay. Yeah. Then we have to tell that to wait. It's okay. Problem will be not there.
No.
Okay. Good afternoon, Jirdeep. Can you hear?
Good afternoon. Good afternoon. I can hear you and I can see you as well.
Okay, wonderful. Good to see you. Sorry for a little bit of delay,
That's okay.
but I'm very happy that everyone is on time. Only thing,
Yeah,
controlling the time later on, it's a bit.
I understand that. Not an issue at all.
So I would like to welcome next speaker, Dr. Have been associated with Tata Steel, I think almost more than 10 years, almost 10 years. So it would be interesting to hear his contribution, both personal and professional, and his impact towards Tata Steel. Dr. Chirdeep, all to you. Looking
Thank
forward to
you.
hear from you.
Thank you. I'm just sharing my screen. If someone can confirm whether
Yeah,
you can.
yeah,
Okay.
it's visible. Everything looks good.
Thank you. So thank you, Professor Jayaprakash Gautam. Thank you very much for inviting me to share my thoughts and little bit of research that we are doing here, which is largely being inspired by Professor Ray. So my association with Professor Ray was so let's just begin my talk first. So today my presentation would be on development of high strength steel for automotive applications. We have been engaged quite heavily in this domain for more than 15 years, 20 years now in research and development department of Tata Steel. Why so? I will just briefly explain why this high strength steel is necessary for next generation automotive cars. So, which is why we need to know the global mega trends, a bit on global mega trends. Some of the mega trends that I try to capture here is starting from shifting in global economic power to climate change, to technological breakthroughs. Then there are demographic and social changes. This I will explain how it is connected with the topic, let's say. Then rapid urbanization and connected consumers. So if we see this particular slide with time starting from let's say 1950, we did a study and it shows that the urbanization is taking place quite rapidly across the globe. And because of that, the urban mobility demand is also increasing day by day. So from 2010 to 2050, it has increased from, let's say, a particular unit is used here, trillion kilometers, from 26 to 48, almost double. So urban passenger mobility demand is increasing. So because of that, there is a climate change, which is related to CO2 emissions. So in this slide, I try to capture the global CO2 emissions, how much is being contributed by the transportation segment. So it is almost like close to 14% of total global CO2 emissions from the transportation segment. And within the transportation segment, the road transport is contributing something around 72%. And within that, there are different segments like passenger cars, heavy duty trucks, heavy duty vehicles, etc., etc. Now, so around 72% or 70% of the CO2 which is coming from roadside is contributing to total CO2 emissions from transportation segment, which is around 49 GT CO2, 49 gigaton of CO2 approximately. So as a result of this, the emission regulations in different countries, we know that it's day by day it is more stringent. So something like in 2015, in different countries like US, China, European Union, it was like around 130 grams of CO2 per kilometer a car travels. That was the norm. In 2030, it will actually reduce to somewhere around 70 and 80. In fact, in India also, we are not far away. We are almost in this range, within this regulation corridor. Now, because of this, the government is making this mandate that we need to comply. Now, what sort of technologies the automotive manufacturers will take, that depends on the OEMs. Now, it is almost certain, if we look at this table, that this kind of within this kind of regulation corridor, with the normal internal combustion engines vehicles, it is almost impossible to have this compliance to be made. So moving forward, we would probably see more of electric vehicles, plug-in hybrid vehicles, and maybe 20 years down the line, fuel cell vehicles. So that is why we can see a shift in the vehicle domain, more from ICE to electric vehicles and other kind of vehicles, plug-in hybrid vehicles, so that the total emission comes down. And every OEM, every car manufacturer, we can observe this change. If we go to market and try and buy a car, suppose from Maruti or from Tata Motors or from Mahindra's, for every segment nowadays we can see there is one electric vehicle, one or two electric vehicles are available. However, this electric vehicle market in India probably will be governed by different factors. One of them is government support. Then comes the customer concerns. Very, very important is the charging infrastructure. So in India, we are trying to develop this charging infrastructure. It's actually developing quite fast. And then it depends on the supply chain. So moving forward, this electric vehicles, we need in these electric vehicles to increase the efficiency of the vehicle so that it can run longer distance with a single charge, we need to use more of lightweight materials. However, there is a dichotomy. The dichotomy lies here. We have seen that the next generation cars, the customer demands for safety, demands for performance, demands for luxury. In order to have all these things, we need to have larger fuel tanks and brake system, higher car body rigidity, and more powerful engine. Because of this, the structure becomes heavier. So in a way, the next generation car becomes heavier, theoretically speaking. However, we need to make it light. So how to make it light is to use more of materials which can reduce the weight. One of them, the most potent one, is of course high-strength steel. Here is a study which shows that if we can reduce the weight of a car by 100 kg, it will require 1 liter of less fuel if it travels like 200 kilometers. And that will in a way emit around 8 grams of CO2 per kilometer. The total CO2 emission will be reduced by 8 grams per kilometer of this car will travel if it can save 1 liter of fuel. So it sets the context that we need to have material which will lighten the car body. So that is the crux of the whole story. And this lightweighting can be done with using different lightweighting materials, with different structural constructions and different production process optimizations. So in today's discussion, we will be discussing on these different high-strength steels and what we are doing in R&D Tata Steel. So evolution of high strength steel, if we see over the period of time, starting from 1960s, the first conventional high strength steel which comes into picture was like big hard double grade steel and high strength low alloy steels, which we are still using very big way. Then comes the first generation advanced high strength steel, which were mainly ferrite based. And the examples are 12-phase steel, trip steel, complex phase steels, and a bit of martensitic steel. Quite a bit of high strength, but very low ductility, these martensitic steels. Then comes from between 1990s and 2000, the second generation high strength steel, which are austenite based. So first generation was ferrite based, second generation was austenitic based. So there lies this austenitic stainless steel, twave steel, etc., etc. Property wise, very, very promising. I mean, very high strength coupled with very high ductility. So in a way, it gives quite a bit of high toughness. However, this second generation high strength steel till today is not so popular. And that is the genesis of the third generation high strength steel. So in third generation high strength steel, property wise, it is in between of time to make the high strength steel. At the very beginning, we were using a lot of carbons and little bit of microalloy additions in order to produce high strength steel, which were mostly hot rolled and normalized. And the microstructure was mainly ferrite and pearlite. But with time, as the research has significantly advanced, the different techniques like grain refinement and precipitation strengthening comes into picture. So in today, if you see, the carbon has actually reduced. The average carbon content has actually reduced from 0.28% to 0.08%, and we are adding a lot of microalloys, titanium, niobium, vanadium, in alone or in combinations. With some new additions are also being made today, like molybdenum, copper, nickel, chrome, case-to-case basis. And processing strategies, in processing strategy also there is a change. So simple hot rolling normalizing to more of thermomechanical control processing and different cooling strategies. And microstructurally, if we see, it's like bainite martensite, combinations of ferrite, bainite, martensite, something like that. The different cooling strategies in the runout table of the hot rolled material gives different kind of microstructure. If we cool it slowly, we can get a ferrite pearlite structure. If we cool it fast, we can get a martensite structure. In between, we can get a ferrite bainite structure. So a lot of advancement has actually taken place on these different cooling strategies. Then for the automotive steel, it mostly, what are the factors, different factors which influence the final properties of a cold rolled continuously annealed material. So in generally speaking, we do a cold rolling, then we annealed it, and then we cool it. And this particular section is known as overaging section, which is a kind of homogenization treatment which is given to the material. So if you try to see the different factors, the first factor, which is very important, is the percentage cold rolled. So percentage cold rolled, as we know, if we change the cold rolled reductions, we can actually change the properties quite significantly with the same base composition. Second factor, which is quite important, is the intercritical annealing temperature. So depending on this temperature, it could be intercritically annealed or it could be fully annealed. So depending on that, either we will get a combination of alpha gamma or simple gamma. Now, as we change this intercritical annealing temperature, obviously the gamma proportion, the austenite proportion in the microstructure will going to change. And this gamma, when we cool it, if we cool it fast, it can form. So depending on that intercritical annealing temperature, different martensite can change the microstructure, which will going to change the final properties of the material. However, a word of caution is that if we change martensite volume fraction with the same base composition, just by changing the intercritical annealing temperature, the carbon content in austenite will also going to change. And carbon content in austenite is a factor which influences the hardness value of the austenite, hardness value of the martensite. The third factor which is important is this intercritical annealing time. Depending on time, the amount of carbide will dissolve or will not dissolve. That will also going to dictate the final properties. The fourth important factor is the cooling rate. This cooling rate, depending on different cooling rates, we can arrive at different microstructures. The fifth factor, which is quite important for us, is this temperature, which is like overaging section temperature. Now, depending on this temperature, the amount of different phases, final phases will form. So if it is too low below martensite start temperature, obviously the martensite content would be higher. And this time is also important because when we form this amount of different hard phases, martensite and bainite and so on and so forth, this needs to be tempered a little bit in order to arrive at a good combination of strength and toughness. So with all these 5 different factors, we try to develop the third gen high strength steel. Mainly, we were working right now on quench and partitioning steel. So I will be describing our efforts on developing this quench and partitioning third generation high strength steel. So development of quench and partitioning steel, the quench and partitioning steel in today's world is quite popular, at least in research field as on date, because of its simple composition. So starting with a simple composition, we can have a martensite start temperature, which we can calculate it, or we can from thermomechanical simulation, we can calculate, we can see the MS temperature. So suppose for a particular composition, we get a MS temperature of 430 degrees centigrade. So here, if we plot a curve between percentage of different phases versus quench temperature, MS temperature is somewhere here. Now, when we anneal the material above A3, everything in the microstructure would be austenite. Suppose the alloy carbon concentration is 0.15, as I have taken in this particular composition example. So when we austenitize it, initially the carbon concentration will remain 0.50. Now, if we quench it below this MS temperature, depending on the quenching temperature, depending on the degree of supercooling below MS, some amount of martensite will form in the microstructure. This martensite in quench and partitioning steel, this is known as primary martensite. We call it as primary martensite. So obviously the primary martensite will going to increase depending on this quenching temperature. Now, when the primary martensite forms, at that moment, the volume, the carbon concentration will remain same between martensite and austenite. However, if you allow some time, since we know martensite is a supersaturated with carbon, it will reject carbon. And this carbon will actually go to austenite. Now, if it goes to austenite, suppose at a particular point in time, the carbon concentration is in austenite becomes 0.32 from initial 0.15. And because of that change in carbon concentration in austenite, the MS temperature has also changed. MS temperature, now the new MS temperature is 356 degrees centigrade. So the new MS temperature is 356 degrees centigrade. And we have like alpha prime and gamma in the microstructure. Now, in the second quench, if we quench it below this new MS, obviously, after some temperature, some other martensite will also form, which is known as secondary martensite, or someone also we call it fresh martensite. Now, because of the formation of this fresh martensite, which I try to depict as a red line over here, the total written austenite content will not going to follow this green line, initial green line. It will follow this dark green line. So something like this will happen in quench and partitioning steel. Depending on the quenching temperature, the initial quench temperature, the written austenite volume fraction will keep on increase up to a certain point, and then it will decrease because of the formation of secondary martensite. However, in this particular model, which was proposed by Professor John Spear and Dikuman, there are certain key assumptions. The assumptions are no other phases are forming except martensite and austenite. So no bainite formation is taking place and complete carbon partitioning is happening. That means carbon is not precipitated in the form of carbides. It is actually partitioning in just elemental carbon. But in reality, we have seen in our experiments, which I will show you in a few minutes, this never happens. whatever maybe the composition is in the real world scenario kind of a composition, there would be some amount of bainite formation, there would be some amount of carbide formation. And because of that, the actual austenite fraction in the microstructure does not really follow this path. However, it remains, it shows a trend. So from there, this sequential partitioning can probably be done in two different ways. One is isothermal partitioning. This is more conventional, and anisothermal partitioning. So isothermal partitioning is basically for cold roll continuously annealed material, and anisothermal partitioning is for hot roll material. The examples that I will going to show you would be mostly from anisothermal partitioning route. So in hot rolling, what we do after hot rolling, we cool it in runout table, and then we coil it at a particular temperature. Now, if this coiling temperature is below the MS temperature of the material, obviously in the material some amount of martensite will form. Now, when we coil it, the coil remains at the total heat content of the coil is quite high, and that is why it takes long time to cool. During that cooling, that heat which is remaining in the coil is aiding the carbon partitioning. So that's why we are calling it anisothermal partitioning, because the temperature is going down continuously with time. So here is a model which shows how a coil cooling takes place. A coil takes like, let's say from coiling temperature of 200 degrees centigrade, it takes almost like 30 hours to cool to room temperature. Now the key point here is that, which I have written here, this quenching temperature is very important for quench and partitioning steel. This quenching temperature should not be very close to MS temperature, because in that case, what will happen, the initial martensite content would be too less, and written austenite or austenite content would be too high. And this martensite, which is the source for carbon, the total source would be too low. So the austenite won't be able to stabilize. And the whole concept of quench and partitioning steel is to stabilize some amount of written austenite or austenite in the microstructure with a lean composition, not with something like 5% medium manganese kind of a composition. So if the total source is too low, obviously the austenite will not going to stabilize. And in that case, a lot of fresh martensite or secondary martensite will form in the microstructure. On the other hand, this quenching temperature should not be too low. If it is too low, if it is very low below your MS temperature, lot of primary martensite will form, and we will land up with a very low amount of written austenite. We will land up with a very low amount of austenite. That will also not going to serve our purpose. With all these fundamental things in place, we try and devise a sort of composition like this initially in the lab scale, and then we did some kind of quench and partitioning treatment and try to cool it quite slowly in different using different paths, and then we see the microstructures. So when we see the microstructure at different quenching temperature using different quenching medium, what we have seen that the slowest possible cooling profile gives us some amount of written austenite in the microstructure with the kind of composition that we picked at a particular quenching temperature. So it was quenched to 250 degrees centigrade temperature, and then it was cooled in salt water atmosphere in order to replicate the coil cooling, hot rolled coil cooling profile. And here we could see some traces of austenite. In the microstructure, when we see the microstructure in ACM, we could see some white patches. And then we did this EPMA analysis to see the carbon distribution maps. It shows the carbon distributions in the EPMA maps. However, we were not sure just from doing EPMA whether these are really written austenite or something else, carbide. So then we did obvious things like EBSD and TEM, which shows, yes, some of them are actually written austenite. However, we could also see the presence of carbides in the microstructure. Then we try and see what are the changes it happens in the microstructure when we change this quenching temperature. We try to select the quenching temperature where we should get the peak for red austenite, highest amount of red austenite. And then we did some experiments here and there. I mean, very close to that point. And in the microstructure, when we change the quenching temperature, everywhere, almost everywhere, we could see the presence of primary martensite, secondary martensite, and carbides, and some amount of red austenite. Now, it is actually quite difficult to distinguish between primary and secondary martensite, but we did that using the philosophy that whether carbide precipitation is happening adjacent to the martensite plate or far away from the martensite plate. And one observation that we could see over there is that with the increase in quenching time, the thickness of these RA flames is actually increasing. Then we try and see the percentage carbon in written austenite, how it varies with different quenching temperature. The black one is the theoretical predictions. The blue one is showing the actual experimental values. And the red one is the critical carbon content to achieve a martensite start temperature of 27 degrees centigrade, which is something like room temperature. And this green line is the alloy carbon content. So obviously, the theoretical calculation and experimental observations, both are showing a decreasing trend with quenching temperature. And when we could reach this MS temperature of 27 degrees centigrade, obviously written austenite would be stable. Some amount of RH should be stable. And sufficient carbon diffusion is happening. That is what it shows. Then we also try to see with quenching temperature how much distance the carbon atoms is actually diffusing in the microstructure and what sort of plate thickness that we are getting using different diffusion equations. So as we know, the diffusion of carbon in martensite would be higher. However, diffusion in austenite should be lower than martensite. So the total process should be governed by how it diffuses in austenite. That's why we check the diffusivity in the austenite and try to plot this curve. So the half thickness of RA flames showing an increasing trend with quenching temperature. And the diffusion distance is also showing an increasing trend with quenching temperature. Now you can see the spread of the flame thicknesses with different quenching temperatures. It shows a wider spread at higher quenching temperature and a skewed spread at a narrow spread at a lower quenching temperature. So there is a thickness distribution also we could observe in the microstructure. Then we did some rolling simulations, actual rolling simulations using Glibble, and then in the pilot scale rolling facilities to predict a lot of things like rolling loads, what is the kind sort of TNR in this material, something like this. And then we come up with two different kind of compositions and did a rolling simulations in the pilot scale and measured the different properties. Different properties means YS, UTS, wear properties, elongations, etc., etc. In order to judge how good or how bad our material is finally. We measured the fracture properties. We observed the fracture toughness and observe the fracture surface. So the left-hand diagrams, these are without rolling, and these right-hand diagrams are with rolling. So what we have observed, the deformed, the ductile region, the length of the ductile region is increasing, and deformed PAGB length, prior austenite grain boundary, which is getting sheared, that is also showing an increasing trend. And with hot rolled material, when it is hot rolled, the impact toughness has increased a lot, and which is also depicted in the fracture surface because of the prevalence of dimple in the hot rolled material. Now, going further, we were also interested to see the stability of this written austenite, its thermal stability vis-a-vis its mechanical stability. What we have observed that it is thermally stable. So we quench the material in the liquid nitrogen, and then we could still see the peaks of retinol. When the quenching temperature is low, the quenching fraction of primary martensite is more and very low secondary. Now, from the final property point of view, we should have more of primary martensite and less of secondary martensite. Because between primary and secondary martensite, there would be a difference in hardness. So that is not what we want. We need more of primary martensite and less of secondary martensite. However, at the same time, we also need some amount of retinosteride, which should be stable and which should be stable enough so that it can give us the trip effect finally. We also did some experiments with isothermal partitioning condition. That means we changed the partitioning time as well as we changed the partitioning temperature in fixed time. And then we observe the microstructure. What we have seen with constant time, martensite present in the vicinity of the retinosteride films, which are devoid of carbide precipitates, we are calling it as primary martensite, and which has carbide precipitates, secondary martensite. This enlarged image also shows the presence of retinosteride and martensite in the form of streaks, alternate layers. We did some experiments at constant temperature with different time. So within 1 minute, we could see the presence of retinosteride in the microstructure. And when we increase the timing at a constant temperature, not many changes is happening probably in the microstructure. The reason could be carbon being an interstitial element, it moves very fast, even at maybe 200 to 250 degree temperature also. And that is why there is no further change which is happening when we change the time. Then we did some EPMA analysis to see the same thing, the presence of retinosteride and carbon mapping and manganese mapping. Incidentally, we couldn't see any distribution of manganese within the microstructure. It is obvious because manganese is a substitutional element, not an interstitial element like carbon, so it cannot diffuse fast. So it is almost like homogeneously distributed. So from there, we finally come to a conclusions that probably in the microstructure, that is what it is happening. When in the initial stage between martensite and retinosteride, the carbon contents remain same. With some time, during some intermediate state, the carbon content in martensite and austenite will change. So carbon will try to diffuse out of the martensite and will go to retinosteride. So there would be a shape like this. If we allow sufficiently long time, what will happen? This will stabilize. So martensite will have a carbon content which is much lower than austenite, and this austenite will going to have a higher carbon concentration, and this austenite should be stable enough to room temperature. And the carbon concentration becomes uniform across the phases. We measure the properties in terms of hardness. So here we could see that with change in temperature, with change in quenching temperature, there is a slight drop in hardness value which is happening. However, with the change in time, there is not much change in hardness values which is taking place in quench and partition state. So coming back to these relevant body parts in the vehicle auto body, we also did a study and try and some from the different tools. If we use, suppose, a particular pillar section, if we use a DB590 1.2 millimeter thickness material and try to replace with a third gen partitioning 980 MPa steel, the thickness we can actually reduce from 1.2 to 1 millimeter for this particular body part, and the weight saving could be like 0.2 kg. Similarly, for a pillar, each pillar, if we replace with a 1.2 to 1 mm thickness QP980 steel, the weight saving potential could be 0.58 kg, and here it could be 0.3 kg. So in this way, if many of these body parts can be replaced with advanced high strength steel, third generation advanced high strength steel, the total body weight would be reduced, having the same kind of rigidity in the in the total car.
Dr. Chiradeep, can we...
However,
Hello? Can you hear me?
hello,
Yeah. Can
yeah,
we wrap up
should we
in 5
conclude?
minutes, please? Hello?
Yeah, okay.
Yeah.
So I will skip this competitors part and directly maybe I'll go to the my last slide.
Yeah.
So the concluding remarks is like high strength steels are mostly driven by fuel efficiency and enhanced safety performance. So as we can see, the journey starts from first generation to second generation, and finally we are now in third generation. Uh, Different effects, processing strategies, alloying additions, which will going to give rise to unique microstructural features. And I think the next generation, after third, there could be a fourth and fifth varieties of steels, generation of steels. We need a very strong industry academia collaborations in order to arrive in that part of the steel, that gamut of steel. But whatever we do, I think the future lies in multi-material approach in automotive domain, not with monolithic materials. With this, I will just show you one last. It was in March 2025, where you could see Professor Ray here, Mrs. Ray here, with many of his former students at Jamshedpur. So here is Dr. Sandeep Ghosh Chaudhary, Director CSI NML, then Dr. Radeep Shaha, Dr. Basudev Bhattacharya, myself here, and my wife, Pampa. She is also a student of Professor Ray. So I consider myself very, very fortunate. So I could get some chance to interact with Professor Ray, first as a student at IIT Kanpur, and then when he was there in Tata Steel. Though I was never his direct student, his influence on my career was quite profound. Thanks to his support that I could actually complete my PhD. I could get a chance to complete my PhD at McGill with his associate, Professor Jonas. To me, he was just not a mentor. He was a friend, philosopher, and guide for many of us. I think, sir, you are being missed every day, and your legacy will continue to inspire all of us. With this, thank you. Thank you very much.
Thanks a lot. Thank you, Chaudhary. Actually, you rightly said it's a legacy, and also the aura of Ranjit Ray. I mean, it's just enormous, I would say. So thanks a lot. And maybe I will invite you to University of Hyderabad of the third concluding points. So industry, academia interaction. Maybe I would be very happy if you could come, and then
Correct.
there is a memento which is waiting for you.
Sure.
Okay.
Okay. Thank you. Thank you very
Thanks
much.
a lot. Yeah. So I will go to the next speaker right away because we are running short of time, which is from the Rene. Are you there online? Can you hear me? Goedemorgen.
Yes.
Yeah.
Good afternoon. Good morning. I can hear you.
Yeah. It's beautiful sun here. I don't know how is there on the other side in Tilburg.
Dark and rainy.
Okay. Anyhow, you can enjoy 30 minutes of, beautiful sun here. We will send you warm regards from this side. Thanks a lot for, connecting to us immediately to the request for giving presentation on advanced, features of the software which we use quite a lot to understand the orientation, particularly as a part of microstructure. So floor is yours. Please go forward. Thank you.
Great. Thank you, Mr. Chairman. Thank you for the introduction. I hope that the screen sharing works and you can hear me well.
Yes.
My contribution today is about a novel eBSD indexing method and how it can really help us expand analysis of eBSD to new materials and to new types of deformation structures. So as an outline of my talk, I want to briefly review the conventional eBSD indexing, something we've done for multiple decades now, It's based on the Hoff transform. And then I'll introduce two new methods using simulations. One, dictionary indexing. I'll glance over that very quickly, and I'll spend a little bit more time on dictionary indexing. And then I have, spherical indexing. And then I have the spherical indexing, and how does it really help us? So I have a number of examples in here, and really shows you what it brings over the conventional Hoff-based triplet voting. Then I have a few examples in the end on alternative master patterns, so not dynamical simulations, but other simulations that we can use before going to a short summary. So let's start with conventional EBSD indexing. That's the basis of EBSD analysis, right? The orientation determination is what we need. And when we get a pattern, we need to process it somehow. And the traditional way of doing that is finding the bands some way. In the past, long past, we manually had to draw the bands. Later, we used the Hoff transformation to detect them. Then we could measure angles between the bands, the location of the bands in the pattern, and match that against a lookup table, against a structure file, which would give us the solution. And in a quick workflow, we have the raw pattern, we calculate the Hoff transformation, we find the bands, reconstruct the pattern, and match it against the model, and then we find a solution. It works really well. As I said, we used this for a few decades, but there are some requirements, and this really limits also the application of DBSD to this day. And one of them is we need to have a consistent band detection. If you want to collect a map, at each point, at each area you want to analyze, you need to find enough bands. And typically that is 5 to 10 bands is what you need to get a reliable, consistent indexing solution. So you need to find them, you need to find enough of them, and you need to find the direction of the band. Because when we reconstruct the patterns, the main thing we're looking at is the angle between intersection of bands. So if we can measure that precisely, we can get a good solution. If there's a big error in there, our orientation precision goes down, and in some cases, the indexing may fail. And the last thing, and this is really important also for the Hoff indexing, in minimal pattern shadowing. So if you have a rough sample or you have something sticking out somewhere on your specimen that blocks a part of the pattern, that gives you a large distortion in the Hoff transform, and that can cause also indexing problems. But when you have no problems with that, you can get fantastic EBSD data. So here I have a nice map of a cold rolled molybdenum. It's heavily deformed, just conventionally indexed, and you can see we get great results. You can get all the quantitative information you want, the grain size, misorientations, texture analysis, and so on. Not a problem. However, you can already see when I say here, but requires, there are potential problems. And one of all the reliable points, and you can see that the area of interest is not indexed at all. And just to illustrate what the patterns look like, here I have a pattern in the substrate, that's fine. Here, yeah, you can make more difficult, still doable, but over there, there's virtually nothing visible. So it's obvious that the Hoff transform cannot deal with this. So what can we do to improve that? So let's take a look at some alternatives. onto a virtual EBSD detector and get an EBSD pattern. Important to remember here is that this simulation is for the actual EBSD detector projection geometry. So if your sample is in a different place, if your EBSD detector is in a different place, you have to make a new simulation. You can, of course, use the master pattern, but the simulation of the pattern will have to be redone for the new geometry. And you can use that for something we call dictionary indexing. And I just have a nice 2D analog. Let's say I have a master pattern, I have a picture. And when I want to do dictionary indexing, I can cut that picture into lots of subsections. So I just have all the different bits of that picture. And when I then have my own picture, so my experimental pattern, I can try to match them against that library. But the limitation here is you need to know the point of view. So you need to know exactly the same projection geometry, and you need to know the size of the pattern. The resolution is not so critical. And what you can do then is you take those, you combine them, you compare them against all the possibilities, and you look at the similarity between the images. And then you look at all the possible subsets, and you find a point where it fits. And that is where your orientation comes from, or where your image comes from. Here on the left, where it's mapped, it's quite noisy in those places. And when I remove the bad points, we only have about 50% indexing. When I take the patterns and match them against my dictionary, I can actually get a much better indexing result. There's still a little bit of noise there, but now I go up to about 82%. So there's a big improvement between the simulated tests and my experts. So there's the difference once again. Now, there is an alternative to that, and this is what I want to focus on today, and that is based on function correlation, so not image correlation. So what we're doing here is we take the original image, the master pattern, and we describe it with a set of mathematical functions. Then we take the experimental pattern, and because we know the calibration of the EBSD system, we know the geometry, then we also describe that as a set of mathematical functions. And then we are matching those two function sets together. So we are not looking at the images and try to match the images, but we are combining two sets of equations and see where they fit best. And in this case, that's also there at the bottom, and that gives us the orientation. This is a lot faster than having to browse the entire library of possible images, because it can all be done straight in memory, even on the GPU, and it's a very quick process with thousands of solutions per second. And that's what we call spherical indexing. So we are using the same master pattern with the diffraction intensities. Then you take the experimental pattern, we remove the projection distortion, so we make it, let's say, independent of the EBSD geometry using the calibration values. And then we put that undistorted pattern virtually on the sphere and see where it fits best. And the best match gives us the orientation. Because we are using the entire pattern, it's extremely sensitive to very small changes in the pattern, so small shifts or small differences. That gives us an enhanced orientation precision, better than 0.01 degree on good patterns, and it also allows us a pseudo-symmetry discrimination. Furthermore, because we are using the entire pattern, we don't try to find the bands. Fragmented information is enough to get an indexing result. So even on very poor patterns or overlapping patterns, we can get indexing that works well. And just to show that in a little other diagram, here's the master pattern. This is the distortion projected experimental pattern. We make those two sets of equations to describe them. Then we fit them together. Of course, it's not just plastering it over the sphere, but also all the possible rotations everywhere. And then we identify where this experimental pattern fits. And the equations, it's spherical harmonics. Please don't ask me about the mathematical details. I don't know. But just as a visual representation, you can combine it or compare it a little bit with a texture analysis. If I have a 1D function here, where I have some intensity profile, you can look at a whole sequence of sine, cosine functions with different wavelengths. And if you have enough of them, with enough variation in wavelength, you can have a good description of your initial intensity variation. That's what we are also doing in 3 dimensions. So we are using spherical harmonic equations, and the higher out you go, so the further out you go, the higher order of these equations, the more detail you can describe in your pattern and in your master pattern. And just to illustrate what that means, here I have 2 patterns that are extremely noisy. The Hopf transform here on the top can just make a little bit out of it. At the bottom, it totally fails. When we do the dictionary indexing that I just described, the top is almost 100% indexed. At the bottom, it's okay. It's a little noisy, but it's usable. And when we use for spherical indexing, that's also the only parameter that is important to use it, is what we call the bandwidth. So the higher order of the spherical indexing, or of the spherical harmonics, the more detail you can see. So if I go from a pretty low order, you can see here it's quite blurry, and you need reasonably good patterns to be able to match that. The higher you go, the more details you can see in the master pattern and in the description of your experimental pattern. And so if I go low, even a very poor pattern still doesn't work, but the higher I go, the more indexing I get. And here I get about the same as for dictionary, but 1 or 2 orders of magnitude faster, because I don't have so many reference patterns to work with. Okay, so that is the principle behind the spherical indexing. The other tool that we want to use sometimes is NPAR. That is a tool that we use to maximize the pattern signal to noise ratio. Here I have 7 patterns that are from an actual data set. And what we do is we take the central pattern and we average it with the 6 patterns around it. And when you do that, the noise disappears for a large part in the background and we can find the bands. So let's see how that helps us. So here I have our shot-peen titanium alloy again. And this was the initial indexing with the Hopf transform, where we didn't get much. When I do this with spherical indexing combined with NPAR, you can see that I get results all the way to the surface. And when I zoom in a little bit, you can actually see that close to the surface in the shot-peened area, there's a lot of very, very small grains that are individually recognizable. And when I index them, they also get a consistent indexing result. Now, from this, it's difficult to judge if it is valid. So I also put the phase map on top. And in this case, you can see it's a duplex titanium. Those green bars are beta titanium lamellae that actually can be traced all the way to the surface in the shot-peened area. And that to me also is a pretty good indication that the phase separation is good and we have a nice indexing result. So this allows you to measure extremely deformed materials. Same thing for the Hopf indexing here on this ferrite powder. This is the Hopf indexing, and this is what the spherical indexing can do. So you can now clearly see all the grain structures. And if I zoom in a little bit, this is a 1 micron scale bar. A lot of the grains are smaller than 100 nanometer here, and they are nicely identifiable and indexed well. So you get a good description of your microstructure. So that's one thing. That was very poor patterns. Here I have make this problem a little bit worse. I have poor patterns and I have very strong overlaps. This is a titanium nitride coating on a steel substrate. IQ map is measured. You can see the topography effects. And the indexing result is like that. It's about 25% of the surface. A lot of the points are really dark, and 23% as you can see here. And this is the description that we get in the EBSD map. So we get something, but it's not really satisfactory result to get good statistics and an indication of the entire texture. Now, what happens with the pattern quality here? Here I have a few patterns from the good grains. And you can see that by eye, you can actually recognize where the bands are. If I apply NPAR, signal to noise gets a lot better. So now, yes, I can see it, and that is indexable. So those are the good points. Those are the points we could index before. And this is what the patterns look like on the bad points. Now, by eye, it's very difficult to see any bands at all. When I apply NPAR, you get something, but these are actually overlapping patterns in most cases. So it's a mixture of bands from multiple grains. And for Huff indexing, that fails. So it just doesn't know what to do. But it's enough for the full pattern matching. So I can combine it with the master pattern and identify the best possible match. And again, that gives me from the original indexing, gives me this. And this is, again, now I have a good separation of the grains. I have a good indication of the grain size, of the texture. And this allows me to report the microstructure properly. Now, the third improvement that I mentioned for the pattern matching that we did with these equations is the orientation precision, because the Huff transform needs to find the bands. And each band that is detected has a little bit of an error in the Huff transform in the band detection. And a typical orientation precision for a Huff transform is about 0.2, 0.3 degrees. Here I have the result of indexing with the conventional triplet voting, Huff indexing, and spherical. It looks the same. So when I'm interested in grain size, texture, misorientation, the triplet voting is fine, and as we've used that for many years. But when I want to look at substructures, and I want to look, for example, at GND densities, that's very, very different. 2.5 degrees. Here I have which is the image here of orientation on the leg axis. That is caused by the band detection in the Huff. You can see a lot of the substructure here, some slip planes, and there's a little bit visible here, for example. But it's difficult to judge what is noise and what is not. And when I look here on the spherical indexing part, you can see the substruct, all these cells very sharply. And if I want to quantify the absolute values of the misorientation, here I have profiles. This is what you get. So here on the left, in red, point-to-point misorientation, so changes from one point to the next. And in blue is the overall bending of the lattice from the left to the right on this profile. And you can see on the pattern matching the spherical, that noise that you have on these curves is almost gone. So it just drops to the bottom of the chart. And if I zoom into that, now the vertical scale on the left is 1 degree. On the left, you have the point-to-point misorientation, and the error is about 0.2, 0.3 degrees. And on the right, it's a lot better than 0.05. And that actually includes the observed orientation changes. So that's an order of magnitude better. Actual patterns on a deformed structure. On an undeformed structure with nano indents or micro indents, you can get even better than that. Now, then going to, let's say, almost impossible samples. I have here topography. Normally, we tilt the sample 70 degrees. And We do that to construct the surface, to get the grain size. But to get an EBSD pattern, you don't need to do that. You can get patterns anywhere from 50, as you can see here, if I just go through this sequence, all the way to 89 degrees. Here's very sharp edges everywhere. So I iron milled it a little bit just to smooth out. Not happy. It can only see the optimum points. On the tips of them, a really good solution. And when I zoom into that, so let me put the IPF on the background and zoom into a small area. You see here that almost the entire area is analyzed. And this is the actual fracture surface of the fatigue failure. This is the only way to measure it. Otherwise, you would have to make a cross section, and you would only have a very small set through this entire microstructure. Okay, now if I have a little bit about phase analysis with alternative patterns. This is an experiment I did last year with Virginia Bertolo from Delft here in the Netherlands. It's a zinc plating on steel. And as I said before, the spherical indexing is based on when you do phase identification, when you have a lot of candidates, you may not have those simulations available. And in this case, so the half thread, what can I do there? So when I want to make a dynamical simulation, I need to know the atomic positions. So for zinc, it's easy. That's a pretty small unit cell, not that many atoms. But the other zinc, iron intermetallics become difficult very quickly. So iron 3, zinc 10 is already a lot bigger. Iron 11, zinc 40, you can see, look at the number of atoms in a unit cell and calculate the dynamical simulation. That is reflected in the time it takes to do this. Here, zinc takes a few minutes, that's okay. This one, half an hour. This one took me about 2 hours, but there's more, and this is an example of that. Iron 13, zinc 126. That took me many hours to calculate the dynamical simulation. And when you know you need to use this, you can do it once, you can use it again. But when you want to use phase identification, and you want to quickly check, they're just taking too long. So what we can do is we can use alternative master patterns. Kinematical or from actual terms. Point, we can identify the band would be for that point, just in a kinematical model. That is to calculate a mental Kikuchi sphere. The other benefit
Sorry, Renee. Hello, can you hear me?
Yes, I can hear you.
Okay. Actually, the last 5 minutes, something we could not hear, the dynamic simulation part. Anyhow, if there is any question, I can take up. Is there any question? Leo, you have? No. Okay. Anyhow, so I would like to thank you, Renee, and wish you to come back to India sometime. We will be looking forward to you here. And thanks for accepting the invitation on a very short notice.
Thank you for your attention.
Yeah. Thank you.
Yeah, no problem. Okay.
With this, I will request Professor Manojit. Actually, Professor Ranjit Ray had a, how to say, very strong connection from BE College. Now it is known as IEST, Shivpur, or IST Calcutta? Shivpur. Okay. So maybe you can explain more about it. Yeah. Thank you, Professor Manojit.
You have a dense forest in front of you, and then the teacher should give the torch to his students up to that, and then allow the students to carry on. So that was his one of his speeches, which repeatedly sometimes I have seen that. So he is definitely a great motivator. We used to sit in our classes. He used to sit in my classes. I used to sit in classes. As Professor Sattam in the morning said, it was very sweet. Yes, I had the taste of getting sweet fruits from his lectures. And then why I say motivator, so one fine morning he in the corridor he was walking through, and then he proudly announced that how good Manojit is teaching. Yeah, I'm not good, but he passed this statement. So it changed the status of mine in the department. So he said, you're such a legendary person, and he told this about me. So we have, yes, giving honor, a lot of things has been spoken. So I will keep that. And then obviously he redefined humility. So of course he's a person of a kind of a stature, I would say, that Professor Sattam in the morning said that he started many new things. You know, in the one day cricket, when Sachin Tendulkar scored first 200, nobody wanted to believe that in one day 200 can be scored. After that, many people scored 200. You know, Tenzin Norgay, he first climbed Mount Everest. So I'm talking about such a personality who opened many things. You can compare his legendary work like in the metallurgical fraternity. So he also have a clear understanding about life. So one day I asked him, do you believe God? So he said, Manojit, do you know the value of G is gravitational constant? So maybe some of you may be knowing that. So, and yeah, I was stumbling, but yeah, sometimes I was very close to it. 6 point, as you know, this value is that. And then he said, you know, what would happen if this value was not that? So I said, yes, probably Earth will not be created. There will be gravitational differences. We will not be here. And he said, then can you estimate what is the probability of this value to be this value? And what is the probability? Okay, I mean, probability is very high. I just wanted to explain it in terms of quantification. So he said, can you imagine this probability, a monkey sitting in front of a computer or on a typewriter? So it's, I mean, we cannot think about that. So he said, no, this is not the end of the story. The end of the story is, he is writing in front of a computer, and he is writing, I am a monkey. So that is the end of the story, and that is the probability of the creation of the earth. And he believes this is God. There is one more example he also gave, that anomalous expansion of water. Think if there is no anomalous expansion, the ice wouldn't have floated on top of the sea, and the flora and the entire flora and the fauna in their existence. Of course, we have some more examples in metallic system. For example, arsenic, antimony, and gallium. They exhibit anomalous expansion. If you say alloyed system, it's gray cast iron exhibit anomalous expansion. But this is one of the rarest examples. Because of that, we are here. So that is his definition of God. I said I'll be very simple in explaining that. I know most of the students here don't have special knowledge about texture because this is not curriculum in undergraduate study, not even in the postgraduate study. So I just wanted to follow his path that I wanted to be simple. Let's see if I can be very simple in explaining whatever I try to do. So crystallographic texture is what I try to do is I try to put everything. I'll be passing the slides to Jay, my friend, so you can take it here. And I would say that Professor Ray could have been writing all the things. He would love to write all the things on the board. So I try to put everything, whatever I try to convey. So anisotropy, mechanical, physical, functional properties. And when we talk about the failures, like fatigue, fracture, localized cracking, we need to determine a microstructure texture combination. So you'll see how we'll do that. And then we need predictive processing for microstructure property maps, which is also our goal to do that. This is a very famous picture. If you repeat 100 times the experiment, you will see the values on the trows, we call it earring property for material specific applications. And this is very much related to texture. We have 0-90 years, and then if you balance and if you have 45 years, and it has been seen 0-90 responsible for cube texture, 45 is responsible for ghost texture. So that is the origin of crystallographic texture and the implication of studying that. So what classical says is which orientations, so whether it is gauss or whether it is cube, whatever. But beyond texture, what we need to study also, as in the morning, in several lectures we have seen that where are they, how they are connected, and how they evolve. So that is also something we need to look at it. So some assumptions we make in classical textures, that properties as a function of ODF only. And classical textures says that which orientation exists, what is the volume fraction of that orientation, and what global orientation distribution. And I'm sorry, I don't have time to explain. I said I have to be simple, but I'm failing my duty if I need to explain what is pole figure and ODF now. It's a series of lectures will be needed. Maybe sometimes I can come and discuss with you. So you have tools, pole figures, we have ODF, and what we normally have is the texture components and the average anisotropy we normally have. So what it says, in the morning also, I was discussing with Professor Leo that, so classical textures are typically applicable for debroining of the sheets, where you can see various kind of textures, and classically we can use Taylor or self-consistent models here, and you see is experimentally they matches quite well. And they assumes that each grains deform independently. Microscopic response is average of the grain responses, and no long-range spatial correlations are needed. So it is actually a function of sigma g and fg, where g is the orientation and fg is the orientation distribution function. So according to the classical texture, if two materials have same ODF, which Professor Pinaki Prasad showed in the morning, that Leo also I think you showed in the morning, that if we have two identical ODFs, they should show ideally same mechanical behavior, but sometimes we do see something different. So what it does not consider is those grains where they are located, and where a similar orientations cluster, and where if there are some special boundaries, they don't consider those special boundaries. If CSL boundaries or twin boundaries are there, they don't consider. So these are some of the basic books we can refer to. So if we just take an example, let's say this is a Rick-sliced sheet. So this is a mid thickness. This we call it that top layer, and this is just below the mid thickness or the subsection, you can say, sub thickness. Then we make, we take the texture at 3 different levels, and we take the EBSD along the sections. What we do is then we do the normal tensile test, and if we see the texture, you can see that for I think it's yeah. So from this is a gauze dominated texture. You can look at it here. So if the gauze, this is gauze, is increasing from surface to 50%. So this is gauze, and yeah, this is gauze. So you see, gauze texture is clearly increasing. Now, if we try to see what is the impact on the R value, so this is experiment, So R value, you see when we go for the full constraint Taylor model. So this is this one, I think, no. So FCT is, EBSD FCT is average. When you go for EBSD, this is FCT. And when you go to VPSC, this is a closer match whenever you go for the VPSC. So even just simple, for some simple predictions, if we go with the models, we see that there is some differences with the experiments. I just wrote some conclusions here. So, yeah, the conclusion is 2 samples may have same ODF, but they may have different grain size, different boundary network, different clustering. So observation is failure life is different, crack path difference, and strain localizations are different. So basically they are all localized effects which we cannot capture from the averaging out and finding out the ODF. So because the real deformation is local and heterogeneous, so ODF cannot catch that. So where classical fails, you need to incorporate the spatial arrangements that we need to take care. It ignores the boundary and the characteristic topology, and it is actually a static snapshot, and we need to actually capture the global picture instead of, the local pictures more carefully instead of the global one. So therefore, if we see ODF A and B, they are same. Classically, they could be same, but actually the properties may differ. Yeah, I again gave 3 examples of the book. So this is of Bonge, which is still called the Bible of this, and we have Cox, and we have Angler's book, which is about 10 years old. So interesting readers may go through that. So continuing the reasons for the failure, which is actually the motivation for going beyond. If the classical if it is classical only, then volume matters, like 40% brass, 40% copper, and all these things, but it does not take care which grains are. So Professor Pinaki Prasad already mentioned in the morning that maybe if I am having a large gauze grain, so which has increased the volume percent, but the distribution is different compared to the copper grains. So randomly scattered or connected or clusters, this is also important. Grain boundaries completely ignored. So ODF does not include the grain boundary misinterpretation. If there is any CSL boundaries or twin boundaries, that is being ignored. And but these actually controls crack propagation, sleep, transmission, fatigue, and all these things. So 2 steels, if you have a strong gamma fiber, so sample 1 might be having many CSL boundaries, strong boundaries, which can lead to high toughness, but in other case, it might be having random high angle grain boundaries, which might lead to lower toughness. So properties will be different. So texture evolution is dynamic, not static. So classically, we measure something before and after, meaning before rolling, after milling, after rolling, before deep drawing, after deep drawing. But in between, there are so many things which could happen, which we are missing in the which is missing in the story. So we need to break the classical theory. So ODF gives the final average orientation, but we need to rotate the we need to rotate the path and see what are the things happening in between. So that brings us to the importance of we need to incorporate the spatial structure. So what is spatial is in between what we have in ODF in classical, and then we need to incorporate the neighboring impacts, and these neighboring impacts are actually in the form of called texture, microstructure aware texture, or the spatial texture. So classically, it could so happen that we have only FG. In the spatial structure, we are incorporating the X, Y, Z direction. So positions are incorporated here. Plus we can have grain boundaries, connectivity, boundaries network, and topology itself. I will skip that. So Watanabe made significant contribution in assuming the role of grain boundary. So in classical we have polycrystalline material, so it's a connection of independent grains. So only orientation matters. So many times we said that, but how these grains are oriented, which not been incorporated here. So what is wrong physically? It does not include the isolated grains. So it happens across the grain boundaries. So most failure starts at the grain boundary. So we need to control, we need to see what is the role of grain boundaries. So boundary matters mechanically. Why? So slip transmission, for some boundaries it may offer easy slip, so ductility may happen. So some boundaries it blocks the slip because of the stress concentration. So yeah, we need to see which are high angle areas or high energy areas, and then cracks will prefer the high energy areas, and we have to find the exact loophole. So failure is boundary controlled and not specifically purely orientation control. So how to solve that? We can define boundary by 5 parameters. So we can have 3 misorientation angles and the boundary plane normals, and then we can see the boundary and its own crystallography just like a crane. So if you can incorporate the idea and to understand what is grain boundary character distribution. So it is a statistical distribution of the boundary types, which is analogous to ODFs for the boundary. So let's say if we have in orientation statistics we have ODF, and in the boundary statistics we have GBCD. So we have grain frequency, we have grain boundary frequency, and likewise we can find we have how many sigma 3 grains, or what is the fraction of that, and how many high angle grain boundaries or low angle grain boundaries, what is the fraction of that, and then we can incorporate that, because we know depending on this value, because high CSL boundary, high amount of CSL boundaries will for sigma 3 it actually does. So obviously this is significantly powerful. There are 3 examples I chose here. One is grain orientation, where we see that grains are rotated towards the brass orientation. So instead of just having final brass peak, we know how the brass orientation has happened gradually. So in example 2 is if you have twinning and it has appeared at 8% strain, but we don't know exactly at what strain it has appeared. So now we know how the twinnings have been formed. So the information about DRX also, it can be quite easily found. So how the researchers are doing experimentally? So methods, so we have some serial sections of EBSD, we do ACM, and then we do shrinkoton, and or you can also do some 4D study, tensile stage inside ACM or EBSD. We can do that, and then yeah, I skip that. So texture becomes more fundamental, because we can predict now we can predict, not just describe. So we learn the mechanism, the texture evolution, the property, we know the processing route, and finally we can prefer it to the ICME route. So final takeaway is classical texture 2 snapshot, and 4D texture is the full movie. So science is the full movie. There is a small example which I'd like to go through. After that I'll close. So actually close this one. So we can add CP phase field modeling as well. This stuff I think we discussed. What you can do, what is CPFE, is the crystal plasticity modeling. I'm going simple because I know there are speakers who will be coming next, who will make life more complex, explaining that after the lunch maybe. So CP is a crystal plasticity stuff, and we know that how deformation happens is a sleep dominated lattice orientation, and the hardening laws will come into play, and after that physicists will come into play, and then the finite element study can be imposed. So the idea is, instead of one average crystal, we can take 1,000 actually, and then the grain all individual grains have their own orientation, own stiffness, and slip response as well. So workflow, how it goes: EBSD, digital mesh, we go for CPFE, and then local stress map we can get it, and which is actually impossible for EDF. And then application of the phase field, yes, this is just one idea. Phase field can do a lot actually. So as we complete the CPFE, then we can ask the phase field to do automatically. If it is 0, there is no crack, and if it is 1, there is crack. So automatically we can identify the grains and where the cracks has been initiated. So this is a nice example of combination of CPFE and phase field modeling, which can actually give the global picture, but not neglecting the individual local components. Yeah, this is one citation. I put it here. I think I will skip this example because slides are there. You can already go through. So, few conclusions. Classical crystallography is powerful, but it would be nice if you can combine these spatial information. 3-dimensional or 4-dimensional experiments would give the complete overview, and the texture is becoming an input of the mechanics, not the characterizing tool. I would like to take maybe 5 minutes. Is okay? Just 5 minutes. Just okay. So one more, just a few slides more, which I'd like to share the last communication I was having with Professor Arkere. Because it is beyond texture, it's not related to the crystallographic texture, but you can see that how fundamentally this idea was. So it is about anomalous eutectic microstructure for binary and for high entropy alloys. So this there is a factor called alpha, which is actually a ratio of entropy of fusion and the R value. So when alpha is greater than 2, they are faceted. They are unconventional eutectic growth microstructure. When alpha is less than 2, this is already established. We have the eutectic microstructure, be it rod or be it lamellar structure. So this is a famous Jackson-Hunt equation. I think it's established in 1966. And based on that, this curve, this diagram has also been established. Once you see this, there is a clear indication where we have the eutectic structure, conventional eutectic structure, and the non-conventional conventional eutectic structure, or the anomalous eutectic structure. So if you have a volume fraction F, and if you have entropy of fusion, so you can have a clear demarcation that below that, left to that you have conventional eutectic, right to that we have non-conventional eutectic. Yeah, so now this is some pictures or eutectic system for silver copper system. As you can see, this is an eutectic gradually transforming to anomalous eutectic when you are changing the undercooling. This is an example of copper cobalt 20% tin. This is lamellar and then gradually transforming to non-lamellar or anomalous. This is again lamellar structure, kind of beautiful picture which is coming, which is also non-lamellar structure. So there is a 3D phase field study which shows that how phase 1 is gradually transforming to the matrix, and the phase 2 is becoming the second phase particles. Again, this is an anomalous microstructure. Surrounding that, it is normal eutectic microstructure. So what we see in eutectic high entropy alloy is the same features. You have anomalous, the normal eutectic structure. This is normal eutectic structure which you see in this kind of alloy. Yeah, obviously in different situations. And this is irregular eutectic in eutectic high entropy alloys. The previous examples are binary alloy. This is eutectic high entropy alloy. Some beautiful pictures of chrysanthemum structures you can see under different conditions. And finding these structures are not uncommon. So this is a paper which is published in Science, where you can see this is a normal cast structure, and this is directionally solidified structures, where you can, I think, so you have the 50% increase of the tensile stress because of that, and is the crack are getting blunt over here, that's why the toughness is also very high. So this simple mechanism, which has been published in Science in 2021, which is a nice example. And then for this alloy, we also have same kind of anomalous structures, but anomalous structures can be obtained through these processes. There are a lot of processes. I come back again to the structure which I was referring to, and the point of discussion we are having with Professor Ray. So yeah, this is you see, there is a clear indication for the binary system which may appear. These are different examples. So he was telling that if we can plot the same kind of things for the high entropy alloys. To my knowledge, people haven't done that, but would be nice. Probably I won't be able to do that, but maybe somebody else already trying. And for the students, if could be having some motivating idea, if you can start working on this. Okay, few references. I just cannot pass by without saying this. Of course, this cannot justify the capability of a person, but some of the references, as I said, is this is this historical texture as a historical perspective. The Professor Suhas published in 2025. And then this is on refractory high entropy alloy. Actually, these are two publications which initiated the discussion. And then this is also a high entropy alloy, paper. And we have microstructural evolution strategy, control, multiphase. I don't know why I put this. So this is a texture for the past 75 years. And of course, I should not miss this book. I think another legend was asked to review this book. I think Professor H.S. Ray was asked to review this book, if I'm not wrong. And he said that, in India, we have an epic called Mahabharata, So it's told that if something is not there in Mahabharata, it is not there in India. So he told that if they haven't missed anything. So it's a worth reading book, what Professor Suhas did that with this. And of course, Professor Leo mentioned in 1994 the highest cited paper of Professor Ray, which I just wanted to convey my regards, pass my regards to him. So I just want to say Jai Hind, and at the same time I want to say thanks, Jai, but don't be confused that you may see these two words the same. So two ODFs, it's and thank you. You have the floor.
Thank you. Thanks a lot. I know everybody is hungry. And what I admired actually Professor Ranjit Ray is like he was very, very simple person with the very, very complex problem, bringing it to the very simple way. So, I mean, he has done 2 PhDs simultaneously. I do not know if somebody have done 2 PhD with the same subject, 2 different places, one in the north hemisphere, another in the south hemisphere. Unbelievable. And so it's amazing. And you summed up very nicely all the stage of, let's say, the legacy of Professor Ranjit Ray goes to the modeling. I hope you take enough food and come to the next session. Thanks a lot. Thanks having a patience listening to us. Thanks a lot. Yeah. learning all those like experimental texture, and beyond that what you can do. I think we will start with Dr. Anand from IIT Madras, but he has been a friend of mine. I think we were doing the PhD together, then there used to be a GLAD meetings. I'm glad he is here. GLAD means Ghent, Leuven, Aachen, Delft, and Düsseldorf. So that was a fantastic collaboration between the professors, all these institutions, and we used to meet every 6 months, and it used to give us a platform to interact with the PhD student together. That's how I know Anand, and at the same time with the professors. So that was a wonderful setup. And the one thing I want to see, like, it's not me who is doing the magic, is the magic of Professor Ranjit Ray, which is all around the world, I would say. And this, so sometime the personality, how it makes the impact, I'm really surprised and also humbled from that point of view, that the moment I initiated this idea, every one of us, particularly in the texture community, came together to talk about the legacy of Professor Ranjit Ray and also to take it forward. So thanks a lot, Anand, all yours.
Thank you.
Yeah, and try to see if you put me.
I will be on time. Okay, good afternoon. Can you hear me? Excellent, thank you. So first, Jay, thanks for having me here. It's actually kind of a redemption for me. I was invited as an invited speaker for the RKD Symposium during the ICOTOM that happened in Metz. I couldn't travel, but somehow I could still contribute to his symposium here, much closer where I can travel. So thank you, thanks for that. So my name is Anand Kanjarla. I'll talk about my academic journey a bit. But the work that I'm going to present is actually done by my PhD student a couple of years ago. And the work was funded by Sandvik from Sweden. And now after graduation, actually, he has left India and joined Sandvik in Sweden and is now the scientist there. The work itself is about texture evolution during rolling of duplex stainless steels. What I'm going to do is to present the big picture of what we did, not the details, given the time constraints that we have anyways. So to begin with, I'm not directly connected with Professor Ray professionally, but I've met Professor Ray when he has been visiting IIT Madras, and like what speakers in the morning said, he's one of the most down-to-earth person that you will see. You know, I was very young professor, faculty member, and he would still talk to me as if, he has known me for many years, and he would give me the respect. So that was very humbling experience interacting with him. So having said that, I still come from a very prominent texture community, right? I did my undergrad 5 kilometers from here, from a college called MGIT, some of you may know it. And then I went and did my master's and PhD in Leuven in Belgium with Professor Paul van Houten, who was also Professor Leo Kesten's PhD advisor. So that was a European journey, and from there I went to America, where I spent some time in Los Alamos National Lab. That's another prominent texture community. And then for slightly more than a decade, I've been at IIT Madras as a faculty member, right? So I do belong to one thread of texture community, and I have kind of saying, in some sense, like Leo had a European PhD and then a North American postdoc, I had a similar journey back to the home country, right? Okay, so few quick things that matters when we talk about duplex stainless steels. Thanks to Professor Pinaki Bhattacharjee, we already know that you have the equal fraction of ferrite and austenite. Alpha and gamma, they are equal fraction. They are known for good strength, excellent corrosion resistance. That's the main reason they have it, right? The particular grade that we are interested in is a trademark grade from Sandvik. There are 3 aspects that this material requires from the texture point of view. One is each of these faces are actually strongly textured. Second, because you have 2 phases, you also have what is called as an interface texture, that is the orientation relationship between them. And the third is the morphological texture, because these faces are typically pretty elongated. All of these affect its properties and actually the way material responds. In this talk, I'm going to kind of focus on these two. This is something which we'll not cover today, but it's part of the PhD. So it's a texture talk, so just a quick reminder of what is the important components. For those of you who already know, it's great, but what our interest is going to be is looking at gauze, to a certain extent brass, and then rotated cube and the eye component. That's what we are interested in, and you'll see why. So I'll quickly jump to the main thing, right? So this is, okay, I can't, oh yeah. So this is the initial as received texture. This is for FCC, this is for BCC, okay? It's a bit unusual texture for an FCC, okay? It's a weak gauze, and then with subsequent rolling, actually the gauze strengthens. And this is FCC austenite, and the gauze strengthens. That's what we have here. And in BCC, you actually have a rotated cube, and then that after rolling, this intensity goes down, and you kind of have a peak at the eye component. These are not texture components that you're typically associated with for these kind. I mean, you see them, but it's particularly gauze in FCC, and the rolling is not that common. Okay? So we wanted to understand what's happening here, right? These are all experimentally measured, of course, so far. And it turns out when we were looking at the microstructures, I have to point this. Oh, okay. One important aspect that we saw was that sometime around between 60 and 80% reduction of rolling, you start seeing deformation twins inside the austenite face in the steels. So this is one important microstructural observation, right? Then we started our journey in trying to understand how to interpret this. So we have used two models. The Prini one is a Taylor Lamel full constraints, and the other one is a Lamel model. Because it's a two-phase material, now each of the grains in the Lamel model belong to different phases. One is FCC, another is BCC. Okay? And because we have seen from microstructures that the material exhibits twinning, so we actually incorporated the so-called PTR scheme, which is a popular twinning model that is used in VPSC, and we've used a Voce type of hardening model. First, like anything else, when we do crystal plasticity, we want to make sure that the work hardening parameters are well calibrated. We have done that for a uniaxial tensile test. Okay? What's important is in our calculations that you'll see forward, we take both FCC slip system, the slip family, and the twin family, and so it's for BCC. Particular thing to pay attention is the critical result shear stress for each of these. The twinning critical result shear stress is almost 3 times that of the slip. Okay? So it really has to work harden quite a bit before the twin can become favorable. Okay? And the BCC is almost 2.5 times stronger than FCC, the initial critical result shear stress. Okay? So once we had all of this set up, we went on to say, okay, what do we have? Yeah. So we did a whole bunch of things to understand the genesis of this texture evolution. First one is to just do the full constraint Taylor, okay? And then we did the Taylor only for FCC with twinning inside it. Similarly, Lamel model, okay? As if it's a single phase texture. If you start off with the original texture of austenite, if it is, think of it as not being part of dual phase, duplex steels, how would the texture evolve, right? And here again with FCC with twinning, Lamel two phase without twinning in FCC. You see, you are doing a lot of combinations, and the final one is the Lamel two phase with twinning in FCC. You should probably see something very immediate, that is, every time we incorporate twinning, you start seeing the component that is of our interest. Okay? Whenever you don't incorporate that, you have more classical textures, right? Now, that itself is not really surprising, but what matters is, of course, for the BCC textures as well. So now we are only going to look at experimental one, the Taylor full constraints, the Lamel 2, and the Lamel 2 with twinning. And surprisingly, if you see here, right, in FCC, the Taylor and Lamel 2, they are classical textures, but BCC texture seems to be a little bit different, particularly if you see, in FCC, there's not much difference in these two cases. But in BCC, when you go from lamel to tail, from tailor to lamel two-phase, it kind of indicates the presence of an FCC phase is actually influencing the texture of the BCC phase, right? And this is with the presence of both FCC and twinning in FCC, we have such a texture. Now, then we started to look at what's happening. Can we explain the mechanisms behind this texture formation? One of the things that we did was to see how is the texture evolving in the initial stages, right, up to 40% rolling reduction or 60% rolling reduction. We did a simple exercise. We know what is the prominent components that we have, right? We have gauze in FCC, rotated cube in BCC. If we were to look at these individual texture components as single crystals and we deform them further, what would happen? It turns out both of these are symmetric orientations, and under rolling they don't actually reorient themselves. So technically, if you have these two textures components or these two crystals either standalone or next to each other, we have done both lamel as well as tailor, the reorientation is 0. So that means this particular texture should be stable as far as we can roll. But obviously we see that you move away from the stability. So this is a kind of representation when we did the simulations, we saw that you have complementary slip systems which cancels out the reorientation completely, right? So the question is, if simulations tells us that these two texture components should be stable, but experiments are telling us the other way, that means there is something in reality that is not captured by the simulations, or at least from the simplistic simulations that we did. And we know the answer to that. This twinning, right? So we have twinning. Now, once you have twinning, you start seeing and this is after 40% rolling reduction, you start seeing some very small twins, all right? Maybe no more than 50 to 80 nanometers, and the volume fraction is also quite low to begin with. Now, when we incorporate twinning in FCC phase, we are able to get to the right textures. We have seen that with the simulations. Now, the story there is how does it end up in a gauze kind? Yeah. So typically, again, you must have heard this name earlier today, Wasserman. In FCC, generally, the approach is you either have a copper type texture or you have a brass type texture, and you have the transition going from copper to brass. The general hypothesis is when you go from copper, typically the copper orientation grains twin. You have the so-called twin copper orientation that's in between. That's unstable with respect to the reorientation. So the minute this forms, with any further slip, you actually end up having it gauze. But gauze itself is typically seen in experiments that it doesn't stay there. For further plastic deformation, it goes to brass. But in our case, the texture stops at gauze. It doesn't really go to brass till the time at least 80% rolling reduction that we have seen. So what our hypothesis is that we know the twins are forming, okay? But once the twins are forming, they're not necessarily traveling the same path that normal material would do to all the way to brass. So then the question for us is how do we then rationalize this response? What we did was to see something interesting. We wanted to see what happens when these twins form. For example, in the kind of modeling that we do, each grain is either a grain or its twin. You don't have small twins inside a grain. This is not a full field approach. It's a homogenized approach, right? So the FCC phase will completely become a twin. And this is at a much larger strains. So we did a simple exercise. We said once a twin forms, you again let it reorient. Or once the twin forms, you don't let slip to occur further. So the idea is to say that if a twin region forms in the material, okay, ideally you should still allow plasticity inside the twin domain. And that is what actually leads it to brass, right? But because we are not leading to brass, what if we say twins form, but the plasticity inside the twin is restricted? And that's what we did. And luckily enough, we actually found that when slip is forbidden inside the newly formed twin, we still retain the gauze. That's the intermediate one. But when slip is allowed, then you end up going away from them. You end up going closer to the brass. So what seems to be happening from our understanding, even though the volume fraction of the twins is less, that once the twins form, there is no plasticity that is taking this further, or at least within the regimes that we looked at. And that kind of seems to be stabilizing the gauze orientation. Okay? That's the texture that we have in case of FCC. Now, we also need to look at BCC, what's happening to it, right? What happens to BCC is that if twinning is occurring in FCC, and it's affecting the texture evolution in FCC, something should also change in BCC, right? And that's what we actually do. Till it is only process of slip in FCC, the BCC remains more or less within rotated cube regime. But once you start transitioning or incorporating twinning in FCC material, the BCC material responds by reorienting itself to I component. Okay. And what surprised us is this. When we were trying to match the experimental textures, right, and we couldn't get it for a long time. No matter what we did, we were not capturing the I component. The transition wasn't simply there. But then my PhD student said, okay, you know, we have to somehow see what's happening to the FCC phase next to the twins. And then he said, maybe if one of the consequences of the twinning in FCC could be that the way the slip mode alters in BCC could change. So we tried a couple of things. What worked out is when we say that the second mode on BCC saturates, that means that particular slip mode now doesn't work harden anymore. You just let it saturate to where they are, and that is the only option that we could see working towards that particular BCC texture. Okay? So what we have, I don't know, is a situation where initially you had a gauze orientation in FCC, rotated cube in BCC. After rolling, the gauze strengthens, but the rotated cube goes to I component. And then we said, okay, look, when we look at these components, because this is a two-phase material, and we are also interested in what is the relationship between these orientations, right? The orientation relationship. And it turns out gauze and rotated cube is one of the variants of the Bain orientation relationship, and the gauze and I belong to the Kuzhumov-Sachs orientation relationship. I mean, every orientation relationship is a descendant of Bain in some sense, but this is a little bit easier to do. Once we came up with this, then we were thinking, okay, that's an interesting point, and because till this point I've never worked on duplex stainless steels or steels with almost equal fractions. So we said, what happens to orientation relationships when you roll the material, right? And we have the tools. I can do a virtual experimentation. I can start now thinking, if I have an FCC phase as a parent, let me see, okay, sorry. If I have an FCC phase as a parent, and if a BCC phase comes out of it, it inherits some orientation relationship, right? And it could be either Bain or Kuzhumov-Sachs or Nishiyama-Wasserman. These are just very little differences between them. This is a big debate in texture community. I think this was settled few years ago, I hope, I'm not sure, but I don't work on transformations. So, but then we said, okay, let's do a virtual experimentation and try to understand if we were to start rolling a two-phase material with these orientation relationships to begin with, how will it evolve with strain? So we did, for this, we have to rely on a full field approach. We wanted to take the morphology and things like that. So we used an RVE, which looks like this. You have a parent grain and a child phase. You assign one of the textures to the parent phase, and then you assign the textures to the child phase depending on the orientation relationship that you're considering, okay? We have used FFT-based approach. This is viscoplastic FFT, which can go to very large strains, which the mask usually cannot beyond a certain rolling reductions, right? And we have gone up to 80%. And what we see, let me first tell you all the combinations that we did. For parent, we have taken cube component as the original orientation, and then the corresponding Bain, Kuzhumov-Sachs, Nishiyama-Wasserman, right? Similarly, we have taken brass component, gauze, and rotated cube. We did it for actually both FCC as a parent and BCC as a parent, just for the sake of it, but And we also tried with different critical resolve shear stress ratios for FCC and BCC to make it more comprehensive. This is for the FCC textures. It's a little bit difficult to read. It's a very dense slide. Let me help you with that. What we are seeing here is first one is FCC face has a random texture, but for corresponding orientation, we have the BCC, which is orientation relationship here. And each of these colors indicate the OR. The blue one is the Bain, red one is Kuzhmov-Sachs, green is the Nishiyama-Wasserman. This is a case when FCC parent had a cube orientation. This is for brass and this is for gauze. What you would notice is that there is no noticeable difference, at least in FCC textures. When you start off with different orientation relationship, it seems to be that's the one that's taking place, right? But when it comes to BCC, again, the FCC parents are still there, same random cube, brass, or gauze. And it turns out the BCC texture is a lot more sensitive to the kind of orientation relationship that exists between FCC and BCC. In particular, in that, if you see this particular case, we have a situation where you have a rather dramatic increase in the intensities coming from, let me just say, this is blue one is Bain orientation, right? So we already start seeing that the orientation relationship seems to be affecting only BCC textures more than the FCC textures. And within the BCC textures, the one that seems to be the affected one is one which has inherited from a cube FCC. And the Bain one seems to be stand out because Nishiyama-Wasserman and Kuzhmov-Sachs are identical, but the Bain is the one that's kind of taking off. So of course, because we have tools, this is all numerical, we wanted to focus this a little bit on this. Yeah. So what we did was to look at the reorientation of all the voxels in the RVE, both for FCC and BCC phase, and how it's changing with strain. It's a similar story. Everything here is an FCC, different orientation relationships, and the color indicates the strain levels that we are seeing. The black one is 80% rolling reduction, green is 60, red is 40. The FCC kind of behaves similarly, but look at BCC again. You have bimodal distribution of the reorientations within the BCC, okay? And the nature of the bimodal is kind of fixed, but the intensities of these, in particular in case of Bain, seems to be something that stands out compared to the other two orientation relationships. And we are still not sure why that is the case, right? Okay. And we also looked at the individual configurations of taking Bain orientation or relationship with cube as thing. I don't think you can see the, yeah, it's not that clear, but what we are looking at is the reorientation angles, and to see if there is something that we can learn from different classification of the orientation relationships. And we seem to believe that when you start classifying the case or Nishiyama-Wasserman or Kuzhmov-Sachs, I think Bain A, or depending on how you name it, one of the Bain families seems to behave very differently from the other two, and we don't have a reason for it yet. And this is kind of more important. What we have seen, of course, is the stable orientation relationships that typically we call with a margin of 7 to 9 degrees are not stable anymore. Once you have an initial texture that you inherit because of phase transformations, once you start rolling them, those particular orientation relationships are not maintained through the rolling, right? And that depends on when will it migrate from the special orientation relationship, depends on the kind of OR that you have. And with that, I think I want to complete my story. The main concluding points. Oh, what's happening? Okay, the first thing take home is that deformation twinning in FCC phase, okay, seems to stabilize Gauss in FCC, and it's kind of a catalyst for the texture transition in BCC. That's one take home. The second one is that from the simulations we seem to find that the twinning in FCC seems to saturate the work hardening ability of BCC. Okay. Now there are some reasons why this could potentially happen, and it seems like what we have seen, it's austenite, which is a dominant phase when it compares, when it comes to changing the textures. And the type of orientation relationship is insignificant if the initial parent orientation is random. But strong parent textures, like what we have seen, cube, gauze, or brass, can lead to different textures in the child phase depending on the interface OR that you see. I'm talking about after rolling. Okay. And the final point is that any of the orientation relationships that you see to begin with, once you start rolling them, they don't survive. That's what we see. With that, let me thank you for your attention, and I think I finished on time. For the sake of completeness, I should, yeah. So my content is basically, my slides are from these two papers, which were published a couple of years ago. We want to do follow-up, but I don't have a student working on it. There are a lot of interesting points that are like a cliffhanger.
Question?
Oh, you have a question.
Thank you, Anand. A very interesting study, and I think we could discuss for hours
Yes.
about it. Did you have your initial EBSD measurements from these before deformation?
Yes.
Because then you could have identified your orientation relation and see how prominent it was.
We didn't do that. Yeah, but I continue. Sorry. Yeah.
No. Did you do this?
No, we did measure the textures. So in fact, it is there. If you see.
But you have the EBSDs from the experiment.
We do have the EBSDs for sure. Yeah. So for example, these are actually the measured EBSDs.
Okay.
But we didn't look at point, like what you're saying is how many of these interfaces are actually this particular interfaces. We didn't do that. Yeah.
Okay.
But that is something that ideally we should have been done. But the thought occurred much later on because we were focusing so much on the bulk.
Yeah.
We didn't pay attention to the granular details.
Because if you have this information, you can somehow supply it at least to your Lamel model.
Yes.
Not to take the pairs just randomly, but to take the pairs according to the misorientation that you observed in the EBSD.
Yes.
So I think that would be, could give some clarification or upgrade your modeling work, so to say.
I completely agree with you on that. We, as I said, the student graduated, and then I've been looking for someone else to continue the work. It's been 3 years. Yeah.
Because I think this is very interesting to, ALAML offers some way to, Lamel or ALAML, to include topological aspects of the macrostructure.
Yes.
Which, by not just randomly pairing grains, but pairing them according
with
to
a certain misorientation distribution. Yeah.
So
in fact, one of the things that that student tried, but then we didn't take it to completion is, in the initial stages, he actually has taken the same texture to begin with, but different misorientation distributions. It's just single phase, FCC. He has taken the Lamel code, and then he started pairing the grains such a way that the misorientation distribution follows a certain thing.
It's interesting.
Right?
Yeah.
And then what we saw, of course, we were at that point focused a lot more on the bulk textures, that it had no effect on the bulk textures. Yeah. But that is not really surprising, right? But the local features, like what you mentioned, is something that needs to be done. But
okay, I have many other questions, but I leave it at this. But very interesting work.
I will stop here. So thanks the speaker once again. Thank you, Anand, for finding time to come here. Time of momento leo. Okay. So the talk now to, thanks a lot. Sorry for the misunderstanding. I'm happy that you manage it. Okay, we are running short of time, so please see that if you could manage things in time. Thanks once again. Yeah.
Sure. Just give me 1 sec. Is my screen visible?
Yes, sir.
Visible? Yes. Okay. Yeah. Thank you to the organizers, Dr. Gautam, for the invitation. And unfortunately, it's very nice to present and to a texture community. The work that I'm going to show today is on the periphery of texture. It's more related to the misorientations and how we can predict misorientation developments using crystal plasticity. So the way I have structured the talk is, in the first few slides, I will give you a brief overview of crystal plasticity, start with the mechanics aspects, and then move to the misorientation, and then show some case studies from our research group where we have used the crystal plasticity tool to predict the misorientation developments. So with this background, I'll start with the mechanics of crystal plasticity, just 1 or 2 slides. We all know that the deformation of crystalline materials is an anisotropic. Is anisotropic. So, for example, if you look at these 3 figures on the bottom left, these are of course they predicted by a model, but these are the single crystal yield surfaces for different loading orientations. And one of them is 001 loading orientation, the other 2 are 011 and 111 loading orientation. And one thing which is very clear by looking at these 3 yield surfaces is that the yield surfaces change in shape, and they are also very anisotropic. And at the macroscopic level, what we see, if you look at the single crystal yield surface, it looks something like a Tresca yield surface. But for polycrystals, if the initial material itself has an isotropic texture or a random crystallographic orientation, then you would expect something like a von Mises yield surface. So the von Mises yield surface that we all learn about in textbook mechanics is essentially a superposition of the yield surfaces of different grains that are present in the material. And if you superpose them, we get what is something which may look something like this, which is a polycrystal yield surface. And a von Mises yield surface is basically an approximation of that. And so this is a broad overview of anisotropic deformation. At the level of crystals, the plastic deformation is governed by the Schmid law. And Schmid law states that plastic deformation via slip occurs if the result shear stress is greater than what we call as the critical result shear stress. And this is a material property which is analogous to the macroscopic yield surface. Now, depending on the orientation of the crystal or the loading direction with respect to the slip plane and the slip plane normal, this is again something that we know, the result shear stress is going to be different. For example, if you look at this inverse pole figure IPF triangle over here, we have plotted the Schmid factor for octahedral slip in a cubic crystal. And depending on where or how you are loading, the Schmid factor itself is going to be different. The point I'm trying to drive here is that the expected deformation is going to be anisotropic, and a crystal plasticity model is a mathematical framework for modeling the orientation-dependent deformation of crystalline solids. So a little bit about the kinematics in crystal plasticity. Actually, I think Anand presented results from two types of models in the previous talk. If we think of the full field model, in a full field model, Anand discussed FFT based results, but this is something what we use in our group quite extensively is the finite element, the crystal. In that, we generally decompose the total deformation into the plastic and plastic parts at each material point. And each material point in the crystal plasticity model has an associated crystallographic orientation, which tracks the orientation of the slip direction, which is represented by this vector S, and the normal to the slip, represented by which is represented by the vector M in these figures over here. And generally, when the link to the crystallographic texture is through the crystallographic orientation, which is denoted by the Euler angles. So as plastic deformation happens, the crystal plasticity model keeps track of the vectors, the slip and the slip plane normal vectors, which evolve with plastic deformation. And this is something which is naturally accounted for in a crystal plasticity model. I will just touch a little bit on the crystal plasticity kinetics. The plastic part of the velocity gradient, which we saw in the previous slide, is basically given as the sum, the crystallographic sum of the shearing rates over all possible slip systems. And the Schmid law, which we saw a few slides ago, also manifests in terms of the Schmid tensor that we are seeing over here. And if we take the tensor sum of all of these, we get the crystallographic shear, which results as a which results due to plastic deformation. And this resolved shear stress governs the amount of plastic shear or the shearing rate gamma dot alpha on the different slip systems. And then this mechanics and the kinematics of crystal plasticity has been established for many decades now. The research which has happened in the past few years and the past couple of decades is more on developing physically based constitutive models to account for the underlying physics of deformation. So I'm not going to go into the details of all of these, but I would just say a couple of lines in that we can use power law flow rooms, which work well and which are phenomenological in nature. But if you want to account for the strain rate and the temperature effects, something like a Cox flow rule is perhaps better suited because it can naturally account for such effects. And then, of course, for the evolution of the hardening, dislocation density based models can be used, which take care of how the substructure evolves during plastic deformation. So, if you are wondering, where does the crystallographic orientation and the misorientation comes into all of this? As I mentioned earlier, in our crystal plasticity model, we keep track of the crystallographic orientation via the Euler angles. And there are different notations for representing the Euler angles. One very commonly used one is the Bunge Euler angle, which is basically a set of three Euler angles, phi 1, phi 2, corresponding for a given set of Euler angles. We can calculate the orientation matrix G at any material point. Now, misorientation is basically and again, there are different measures of misorientation. The one which I'm going to talk about today is the local misorientation, which is also sometimes called as the kernel average misorientation. So the kernel average misorientation is basically the difference in the orientation between the neighboring points, which is given by this kind of an equation. And again, in a crystal plasticity model, if if we just keep track of how the orientation evolves or how the Euler angles evolve with plastic deformation, it is very easy to calculate the misorientation, which is essentially a byproduct of the crystal plasticity calculations. So with this background, I'm going to show a couple of examples or case studies from our group where we have tried to look at the misorientation developments during plastic deformation in different alloys. And we have also tried to compare our results with experimental measurements, which were done in collaboration with Professor Indradev Samajdar here at IIT Bombay. The first work that I'm going to show is basically looking at the misorientation developments in a polycrystalline nickel-based superalloy. This work was done by two of my PhD students, Sukrita Chaudhary and Namit Pai. Both of them graduated last year. Sukrita did the modeling work and Namit did the experiments. And as I said, this has been done in collaboration with Professor Indradev Samajdar, with whom help we did all of the experiments of EBSD measurements. And Professor Guru Prasad was also involved. And then this work was sponsored by folks over at DMRL in Hyderabad. So the material that we are interested in is a powder metallurgy processed nickel-based superalloy. And this material has what we like to call is a multi-scale microstructure. So if you look at this SEM image over here, we see different types of precipitates. We see these large precipitates which really called as the primary gamma prime precipitates. Then if you zoom in at the submicron level, we see two different types of precipitates, which are the secondary precipitates, which are of the order of about 250 nanometers in size. And then we also have tertiary gamma prime precipitates, which are of the order of 20 nanometers in size. So the role of precipitates in nickel-based superalloys is to impart strengthening. The material derives its strength from these precipitates, especially at high temperatures. And the material has a very steady strength up to about 800 degrees Celsius, 900 degrees Celsius, all of which comes from the precipitates. However, the primary gamma prime precipitates are undesirable in the microstructure, and this can be changed by changing the processing methods or the heat treatments. And these microstructures also show, which is something I'm going to show in the subsequent slides, a lot of annealing twins. So the grain boundaries, the twin boundaries, and the phase interfaces between the primary gamma prime precipitates and the and if you may say so, the matrix may occur as stress concentrators. Based on literature studies, it has been found that twin boundaries and interfaces act as the sites of stress concentration and major stress concentration and eventual failure in these materials. So what we wanted to look at was how do the misorientations evolve at these different stress concentrations that are present in the microstructure, and if the model can predict that. So this is a crystal plasticity finite element model, which can directly take as input the EBSD measured microstructure. So what you are looking on the left is, on the top left, we have the phase map. In the phase map, we show the green phase, which is the primary gamma prime precipitates, which are quite large in size. And then the secondary and the tertiary gamma prime precipitates are considered in the homogenized matrix of the gamma. And so this is essentially, we are trying to do a two-phase simulation. And then we have also considered the individual crystallographic orientations for each of these phases, which go as an input to the model. And then we did some parallelly, we also did some simulation. We also did EBSD measurements during interrupted tensile deformation of these same areas. And we tried to compare the model predictions and also gain insights into why the misorientation developments might be occurring. So, I mean, I'm going to skip, since this is more, this workshop is focused more on the texture and the crystallographic orientation. I'm going to skip the mechanical property prediction part. I'm going to just show one slide which shows that yes, if you have these twin annealing twins in the microstructure, you can see that there is some localization of the strain, and of course, especially in the larger twins, which also show localization of the stresses. And then just by looking visually at these stress and strain contours, we can also see that some of the precipitates, the primary gamma prime precipitates, are showing a large amount of stress development, but this trend is not uniform across all the precipitates. We then wanted to look at the misorientation developments. And this plot on the left shows the comparison between experiments and simulations of the kernel average misorientation on a normalized scale for different amounts of strain. So we are looking at 5% strain, 10% strain, and 15% strain as we go from top to bottom. Again, I mean, if you just look at them visually, not much inferences can be made. So we wanted to collect some statistics of the misorientation developments from these microstructures. So what we did was we looked at how the misorientation develops in the vicinity of these grain boundaries, the annealing twin boundaries, and the phase interfaces between for different amounts of strain. So as you can see here, 5% is shown in red, then we have 10% shown in blue, and then the 15% strain is shown in pink color over in all of these images. And again, it looks like, yes, the experiments are shown in the top row, and the simulations are shown in the bottom row. Again, it looks like there is some correlation between the experiments and simulations, and these are qualitatively comparable. Then we further went ahead and put the misorientation developments between the grain boundaries, which are shown in black over here, the phase interfaces, which are shown in blue over here, and the twin boundaries, annealing twin boundaries, which are shown in red over here, and compared them side by side from 4 such areas. So basically, we performed EBSD simulations of the EBSD microstructures for 4 different regions, and collected the statistics from all of them. And based on the statistics that was collected, we see that the misorientation developments are the highest at these annealing twin boundaries. This, and again, this is comparable between the experiments and the simulations. This tells us 2 things. First of all, since the results are comparable between the experiments and the simulations, the model, at least it can be said that the model is qualitatively validated. The more important thing here is that the localization is higher at these twin boundaries as compared to the grain boundaries or the twin interfaces, or the phase interfaces, sorry. And this could be the possible reason of why failure happens, eventual failure happens at these twin interfaces in these superalloy microstructures. So this particular work was published a couple of years ago. If you are interested in more details of the work, please go ahead and look at this paper. I'm sorry. So another case study, and this is the second one. This was again done by the PhD student Namit, who graduated last year. He was jointly co-supervised by Professor Indradev Samajdar, with whose help he did all the experiments. So taking the crystal plasticity model, we wanted to improve the predictions of the misorientations. There were some, if you looked at the local comparison, one-to-one comparison, there were some differences between the experiments and simulations. So the idea was that what happens if we introduce strain gradients? And the physical motivation for this work, this particular work, comes from this theory of mantle core deformation. which was proposed, I mean, as early as the 80s, where it says that, and I mean, this is quite intuitive, that the grain is less affected by the deformation as compared to the regions which are on the regions which are near the grain boundaries. And the grain boundaries, the regions which are near the grain boundaries, which is called as the mantle region, shows higher misorientation developments as compared to the core. So we wanted to look at the development of these near boundary gradient zones very systematically using experiments and modeling. And for the modeling, as I said, we are using a strain gradient crystal plasticity framework, where in addition to all of the considerations that we discussed earlier, we are also now looking at the strain gradient, the gradient of the plastic strain, and the associated development of GMDs and the backstress, and how it contributes to the local misorientation developments is the interest of this particular part of the work. So the material in this case is an aluminum magnesium alloy. I cannot remember the magnesium content off the top of my head at the moment, but it was more or less homogeneous microstructure with very little precipitates. And the regions that we studied in these microstructures, the regions we studied, we made sure that there are no precipitates in those regions. So first we calibrated the model to the experiments, and then we again took EBSD microstructures as input for our work. The picture that you are seeing on the right is showing the development of the misorientations with progressive tensile deformation. And this is again, Namit did these experiments very painstakingly and calculated the misorientation developments and also the GND developments. So now since we were interested in what is happening at the level of grain boundaries, we systematically studied grain pairs. So for example, if you look at this microstructure, which is shown where my pointer is, we systematically took grain pairs with different orientations, and we studied what is happening at the interfaces of these grain boundary, at the grain interfaces with respect to the misorientation developments and the size of these near boundary gradient zones. So again, some representative deformation contours. A lot of different quantities are shown here. We are showing the effective stress, the effective strain, and then we are also showing the GND, the backstress, and the misorientation developments. What I want you to focus on is that if you look at these misorientation plots, which are in the bottom row over here, is that with increasing applied strain, the misorientation developments keep on increasing near the grain boundaries. And then what we did was we systematically tried to quantify them based on the Schmidt factor of the two grain pairs that we are studying. And we looked at the misorientation development and the GND profiles. So if we draw a line profile, if we take, let us say, this grain pair that we are seeing over here, if we draw a line profile across the grain boundary, and then we look at the evolution of the CAM, the kernel average misorientation, and the GMB density, we see that there is a region in the immediate vicinity of the grain boundary, which has high misorientations and also high GND densities. And this is what we call as the near boundary gradient zone. So, and we systematically try to measure the length of these near boundary gradient zones, and then also look at different grain pairs. So here we are showing a qualitative comparison between an experimental grain pair and a simulated grain pair at 2.5% strain and 10% strain. And again, as we see that with increasing strain, the misorientation developments the misorientation itself increases, and the length of the or the width of the near boundary gradient zone increases. So then we took all of these grain pairs that we studied both from experiments and from simulations, and we classified them in terms of the Schmidt factor as shown on this IPF triangle. And then what we wanted to do was we wanted to find some trends in terms of whether the Schmidt factor of the two grain pairs plays a role in the development of the misorientations or the near boundary gradient zones, and whether there is a correlation with the size of the grain itself. So what you are seeing in these plots is on the x-axis we have the Schmidt factor of the grain, and on the y-axis we have the length of the near boundary gradient zone normalized by the grain size. And the black symbols are the experiments, the red symbols are the simulations. You can see that as the Schmidt factor of the grain increases, the length of the near boundary gradient zones, the normalized length of the near boundary gradient zones increases, which makes sense in this because we would expect that as the grain becomes softer and softer or more compliant to plastic deformation, the width of the near boundary gradient zones should increase. And then the thing that you should also pay attention to is the fact that all of these quantities are normalized by the grain size. And if you collect the statistics from all of those, the mean values are shown on the right-hand side plots, again with the experiments in black and the simulations in red. You can see that both experiments and the simulations tell us the same story, that the width or the length of these near boundary gradient zones normalized by the D, there is a strong correlation between this length and the grain size, and the width scales with the average Schmidt factor. So this is, this sort of an analysis was not done previously, and this is what we were very interested and found. We found this interesting correlation by the analysis of all our simulations and the experiments. This work was published a few years ago in IJP, and if you are interested, again, you can take a look at this work. With this, I would like to summarize. Basically, I would like to say that crystal plasticity is a versatile tool or a versatile framework for modeling the mechanical response and also the microstructure evolution of polycrystalline aggregates. Misorientation developments, we have shown some examples of misorientation developments in single-phase and multi-phase alloys and correlated with the underlying microstructure. And we have also seen that consideration for strain gradients improves the prediction of the misorientation developments and associated near boundary gradient zones. Now, we do all of this work using our open source crystal plasticity solver. It's called as ROCP. If you want to use this tool, it is available at this link on GitHub. This is a crystal plasticity solver which interfaces with the Moon's finite element solver, which is also open source for performing crystal plasticity finite element simulations. So with this, I would like to thank you for your attention, and I would also like to acknowledge funding from ACRB and BMRL for this work. Thank you.
Thanks a lot. Thank you, Anirban. Question?
Thank you. I'm Leo Kestens from Ghent University. Thank you for a very comprehensive presentation. Your conclusions were largely based on the crystal plasticity finite element measurement calculations, but do you see any way how to incorporate this topology in mean field models?
So I think what was being discussed in the previous talk as well, if you consider grain pairs and something which Lamel models do, there, if you consider grain pairs and look at misorientation developments, that would be a way to look at it. And of course, mean field models are significantly faster as compared to these full field models. That is a big advantage.
Okay, thank you.
Hi, Anirban, Anand here. Nice talk as usual. One quick question. What is the kind of element that you're using in your finite element? It's a quasi 2D. So is it a plane stress or plane strain condition? Because you're dealing with surfaces from experiments.
That's a good question. So for the first case study that we showed, we did it like a 3D simulation. So essentially we have, if you look at this slide, we have 2 layers of elements in the thickness direction. So it is quasi 2D, but the boundary conditions are for a full 3D simulation. For the second case study that we showed, we used generalized plane strain elements.
Okay. We will discuss later when we meet. Okay, no problem. Thanks.
Yes, thanks.
Just a curious question from my side. This microstructure which you have for iron 718, I don't see this delta precipitate on the grain boundary. It's a specific microstructure like you.
So this is not a Inconel 718. This is a what they are calling as a, this is, first of all, this is indigenously developed at DMRL.
Okay.
The equivalent composition is, I think, it's a French composition.
Oh, Rene, okay.
It's a Rene. I'm forgetting the number.
Okay, no problem. It might be 88 or so. This grain, this black one, which kind of this gamma P you call it? Like what is the gamma prime? You have prime and gamma prime. What is the, how to say, the composition of this?
So this is a nickel 3 aluminum.
Okay.
Yes.
So this looks like a exposed, like heat treated composition, right?
Yes, there is a heat treatment aspect involved as well, which I did not emphasize here.
Okay.
If you heat treat some of these large precipitates might dissolve.
Yeah, okay. Good. Thank you, thanks a lot. So since you could not come and also Indra also could not come, so I don't know what should I do with your memento. Should I invite you here, or maybe I can give it to Anand, maybe then he takes the responsibility to get your memento there, or I don't know.
No, we will definitely make it a point to visit Hyderabad sometime.
Wonderful. Yes. Yeah, that would be great. I will be looking forward to it. Thanks a lot. I would like to clap. Yeah.
Thank you. Thank you.
So next speaker. It's online? No. Okay. Yeah, this is Mr. Ravi Teja, right? I think you are the student of Anand and now working in JSW. It's an interesting, how to say, topic from the texture to Tesla, linking crystallographic texture and micro texture to magnetic properties in electrical steel. It's how to say, electrical steel is always a very fascinating, how to say, material, which can help people learning about the texture. Basically, a lot of people have learned texture using this material. So yeah, all yours. Thanks for coming and accepting the invitation. So time is like 20-25 minutes.
Yeah, yes. Okay, good afternoon all. So I am Ravi Teja. So I will basically work in JSW Steel as a new product development in electrical steel segment. So this is my topic. Thanks Jay sir for giving the opportunity to present my industrial work in front of my academic guide also. Okay. So if you come to this is about the JSW presence all over the India. So we have the 4 integrated steel plants in India, which is advantageous because as we use other facilities in another research institutes, we'll use all our steel plant facilities. Wherever we want, we can go and we can roll our material. we can compare the facilities. So this is the one of the advantage working in the JSW. So and also if you see, this is the single largest location in India, which is the highest capacity of 17.5 million ton per annum. So going to expand further in a couple of years. Development will happen in industry. So in a research world, the new research starts from the research gap. So we find the research gap, we found the curiosity in that, we will work in it. But industry, this comes from the customer inquiry. So customer will comes to us, we want this product with this specifications. Then if it is not in our product basket, we'll go to the new product development. So after developing the product, it will not end here. We'll go for internal quality improvement continuously, and after supplying to the customer, we'll go for the customer complaints, and again we'll come back to the internal quality. This way the new product development in industry will continuously go. Then in order to perform the above functionality, as a central department in the steel plant, we have to work with the sales and marketing, we have to work with the customers, and we have to work with the R&D facilities inside the plant, and we have to coordinate all these departments like steel making, hot rolling, cold rolling to the end. So this is the central department which will cover the entire overview. So working in this department, you will get the market, you will get the customer information, you will go into the R&D, and you will work in the plant. So this is the global outlook of electrical steel. As you can see, the both non-oriented grain and grain oriented is expected to go with the CAGR of 4.8% from 2026 to 2033. There is a huge potential in the electrical steel markets in the coming years. So if you see, this is the segregation of segment wise. Mostly electrical steel, 37% of electrical steel is used in the energy and power consumption, because it is indispensable use the electrical steel in energy transformers, distributions, and electrical motors. So if you see the domestic demand also continuously increasing. It is the CAGR growth of domestic demand is more than the global demand. And the market share of India in electrical steel is 4.8%. So it is continuous to increase in the coming years. Because of these factors, we have the EV expansion is going on, and stringent norms for energy efficiency is coming up, and all industry is shifting towards from low grade to high grade steels. So that's why JSW is also planning. Currently we have the only one annealing and electrical steel line. So we are planning to put ACL2 and ACL3 because of this global and domestic demand to cater our customers. So in this slide, I will explain the types of electrical steels. So based upon the grain orientation, electrical steel is divided into cold rolled non-grain oriented steel and cold rolled grain oriented steel. Inside CRNGO, we have the condition called fully finished. In the fully finished means from the plant, customer can directly use. So in the semi-finished means customer has to do decarb annealing to get the final properties. So that's why it is called semi-finished. In the hot rolled condition and cold rolled condition, we'll supply pole and rim sheets for high-end generators and everything. These are the CRGO. So what is the metallurgical division for CRGO and CRNGO? You can see this is the grain structure of CRNGO. It is in the micron level. It is the grain size of CRGO. You can see it is in the millimeter range. So one of the importance of this image is this is produced by the JSW acquired in the Tyson Group. It is made from the Indian soil. So we are in the coming years we will commercialize. JSW will commercialize the CRGO product, which is extracted, mined in India and produced in India. So these are the typical orientations required for CRNGO. So cube texture is very much needed for cold rolled non-grain oriented steels because of isotropic properties. Because motor is rotating in 360 degrees, we need properties in electrical steel in 360 degrees, which is achieved by the cube texture. But in the transformer grade, that is CRGO, we required the properties in a single direction, which is along this rolling direction, because transformer what it will do is it will conduct the flux from primary coil to secondary coil. So easy magnetization direction along the rolling is sufficient. So these are the few applications of CRNO we will use in different types of motors as you can see here, and CRGO mainly we will use the static application of transformers. These are the main properties required for this one. We required low iron losses, high magnetic flux density, and we required better punchability and better dimensional tolerances. So all in the academic research will stop with from low volt losses and high flux. No one will talk about the better punchability and dimensional tolerances. So why this importance? I will explain here. Because if you see, this is the sheet we produced, customer will take it, they will punch the rotor part and stator part out of this. As you can see, because from the sheet they are punching, maximum 50% of the material is going to, they are scrapping. That's why they will scrap from the same sheet. First they will punch with rotor, then they will punch the stator. So as you can see, from the single sheet of 0.5 mm thickness, they will stack one over the above into the to make the core of the product. So if this is magnetic properties is bad little bit in the product, so customer will agree because they will use that same material to the lowest grade of motor. So if the dimensional with thickness tolerance, width tolerance, flatness is not there, so the customer can't use that material anywhere, because if there is a thickness deviation here, if you pile up one over the another, so after stacking few laminations, it will not be flat, it will be taper, so customer cannot use. So apart from the magnetic properties, in electrical steel supply, most important is thickness, profile, width tolerance, flatness is most important than the magnetic properties in a commercial point of view. Okay. So coming to the basics, this is from SARS review paper. This is the snippet. So this is the basic hysteresis loop of the magnetization and demagnetization. The area inside the curve will tell the how much losses happening in electrical steels in the form of hysteresis. So what are the basic requirement for electrical steel is, we required as narrow as the curve and as tilted as the curve to get the lower iron losses and to get the more magnetic flux density. And if you comes to the, because electrical steel is basically made of ferritic steel means BCC. So if you see easy magnetization direction in BCC is 100, that means it is good for electrical steels, and 111 direction is very hard to magnetize, it is bad for electrical steel. That's why if you see in CRNO and CRGO, 100 is common. So in CRNO 100 we required in plane of the sheet to get the properties on all direction. In CRGO, this 100 direction is required in the rolling direction to get the easy flux transfer from primary coil to the secondary coil. So if coming to the losses in the steel, so this slide will represent the what are the losses occurring in the electrical steel. One is the hysteresis losses, which comes from the hysteresis loop from the previous slide. So which is controlled by the grain size, crystal orientation, purity, residual stress, surface roughness. These are the factors affect the hysteresis loss. Apart from the hysteresis losses, we have the eddy current losses also. When we try to magnetize any ferromagnetic material, so secondary currents will generate inside a material, that is called the eddy currents, which will oppose our primary field. So in that terms also we will get the losses, and we have the excess losses because of the various other phenomena happening inside a material, unknown phenomenon. So these all sum up will give the total losses. These eddy current losses can be controlled by increasing the resistivity of the element and by reducing the thickness. So based upon this, we can quantify our material losses. If you see this graph, so based upon this and our production, we model the watt loss with respect to different silicon levels and with respect to different thicknesses. As you can see, by increasing the silicon, the watt loss is started decreasing, because silicon will increase the resistivity of the material, and you can see by decreasing the thickness, the watt loss is decreasing. But by increasing the instead of increasing the silicon, reducing the thickness is more effective, because this eddy current is decreasing with the square of the thickness. That's as it can be indicated by the spacing between the points. So to get the better magnetic properties inside a material, we required lower thickness, higher silicon content with a better texture will lead us to better magnetic properties. So this is the relationship between how the grain size will affect these losses. So from the curve you can see the hysteresis loss is proportional to the inversely proportional to the root of the D, and the eddy current losses is linear with the grain size, and anomalous losses is somewhere proportional to the square of the root. So in the cold roll non-grain oriented steel, the challenge is by we have to get the good texture and we have to get optimum grain size. Both are important in non-grain electrical steels to get the better magnetic properties. So apart from the basics of electrical steel, so I will take you virtual tour of how integrated steel plant work to make the electrical steel. So these are the raw materials for the making the iron. So all we throw into a blast furnace where we will get the iron. So from the pig iron we will take into the hot metal pretreatment plant, then it will go to the basic oxygen furnace to get the steel. From it will go to the RH degasser because electrical steel required extremely low impurities. So we will go to the RH degasser where alloying additions will be done and it will go to the slab caster. After going to the slab caster, it will come to the hot rolling mill. So these hot rolling mills, electrical steel after casting slabs, we have to hot charge into the reheating furnaces, because if you go to the cold charges, because of the higher silicon content, micro cracks will form. So if you load the cold slabs inside this furnace, it will break down inside the furnace, it will set down the entire mill. So we have the reheating furnaces. After reheating furnace, in order to remove the scale formed on the steel, we have the scale breaker, and we have these roughing mills to reduce the thickness, and we have the finishing mill to reduce the thickness further, and we have the runout table, means water will spray here to get the required cooling rate, and we have the down coilers. So basically what we will do in hot rolling means from the meters of slab to we will make the kilometer of coil. So this is what we will do in the hot rolling mill. Then it will come to the different parts of different products of electrical steel we will make, which will follow different path. For example, conventional grade will follow cold rolling, then it will go to the annealing. If high permeable grade will go to the pickling line, then batch annealing, then cold rolling, annealing to get the high permeability, extra properties in the electrical steel. For example, in semi-finished it will follow different route, cold rolling, BAF, SPM, and we after skin pass mill will supply to the customer, and customer will do decarb annealing and they will use it in the final product. So this is the main line where the decrystallization of electrical steel and coating will happen simultaneously, where we load the coils and we will clean it. See, this is the continuous line, it will run 24 hours. So we have the welder where simultaneously 2 coils will load and it will go feed into the furnace continuously. And we have the in furnace, we have the different zones because we can't heat instantly. We have the preheating section, soaking section, then cooling. After cooling we have a coaters, because we know that if you decrease the thickness and we need to apply the insulation resistive coating between the 2 laminas to reduce the eddy current losses. So this is the coaters. So we will coat bottom and the top simultaneously against the gravity to maintain the uniform coating thickness, and it will, after inspection, it will form a final cold rolled non-grain oriented fully processed steels. So these are the line capabilities. So this is the virtual tour of integrated steel plant of making electrical steel from soil to coil. Okay, I am explaining three cases how this texture, like how we are using texture to get the more profits. So this one is telling that here 2 routes are there. So one is conventional route, it is cold rolled, then ACL. This one is we added extra BAF annealing. So that means prior to hot rolling and cold rolling, we are recrystallizing the material, we are increasing the grain size. So what will affect the process? So accordingly, if you increase the, if you apply the hot band annealing, the prior cold rolled microstructure grains are bigger. So because of the bigger grains, there is a shear band formation in the gamma, means blue grains is gamma grains. So what we expected is from the shear bands of gamma, cube grains will nucleate. Whatever is the cube is already it will present, it will form a good cube texture in the final stage. For example, if prior to cold rolling, if there is a very narrow microstructure is there, instead of shear bandings, grains will get flattened. From the grain boundaries, the nucleations are mainly gamma. So in the final microstructure, gamma is undesirable texture will be prevailed. So this is the microstructure of low silicon, which is from the top to bottom you can see lot of heterogeneity is there. We will recrystallize this microstructure to get the better properties. So how this route will affect? So this is the final texture and microstructure of the, this is without hot band annealing microstructure and texture. This is with hot band annealed microstructure and texture. I took the two compositions of 0.7% silicon and silicon electrical steel and 1.3% silicon. You can see clearly there is a, without hot band annealing, there is a gamma fiber, so which is nullified with the hot band annealed sample. Similarly, in 1.35 also there is a predominant gamma texture present in the without hot band sample. There is gamma is diminished. These are the results. You can see the texture factor is a quantifiable thing. It is the good texture by bad texture. So higher is the better. So in the, here in 0.7% silicon, by introducing the hot band annealing, texture factor improved from 0.33 to 0.39, and in 1.3% texture factor improved from 0.26 to 0.35. So because of this, it is resulted in very good properties, like watt loss is magnetic induction is increased from 1.75 to 1.71 to 1.75 in this grade, and 1.68 to 1.74 in 1.3% silicon. So there is a huge change in the magnetization. So because of the huge change in magnetization, what we will do is we are selling this as a premium grades. So we can, by introducing the extra BAF annealing, we improved the magnetic properties. We are getting, we can ask the customer for the to pay extra. Okay, this is the one of the case study. We use the texture to get the more profits. Okay, another is how antimony will affect the texture. So we take the 2.6% silicon steel. This is the process route. We casted slabs. Means all for disclaimer, I am telling all these experiments will done in the industrial. These are not laboratory experiments. This is performed on the industry. So one heat it will take 180 tons, 180 tons to cast. So these are all like we will take the in tons. Okay. So this is casting done with antimony and without antimony. Then hot rolling, recrystallization, cold rolling, and annealing. So if you see the microstructure of the hot rolled steel with and without both, there is a lot of microstructure heterogeneity. There is a recrystallized grains on the top, and there is a long elongated grain at the center. This is because if you increase the silicon, there is a ferritic, there is no phase transformation. All the rolling happen in the ferritic region, and recrystallization fine microstructure at the region surfaces, because it is in a continuous contact with the roll because of the lot of shear stress and friction. These are recrystallized and equiaxed, and here there is no recrystallization, only recovery is the softening phenomenon. So after that hot banding, so this with antimony it is completely recrystallized, but still small elongated grains is there. Here still microstructure is only partially recrystallized. So because of that, there is a in cold rolling we can, because of the bigger grains, we get the more shear bands here when compared to here, and this is the final microstructure. So the magic will happen in the final microstructure with the presence of antimony. In the absence of antimony, there is a grain size are grown bigger like 170 micron. So in the presence of antimony, what it will do is it will segregate to the grain boundary and it will pin the grains grains means undesirable texture, grains means gamma grains it will restrict. I will explain in the next slide. So it will restrict the overall grains also. If you see grain size come to 91. So by optimizing, by adding the antimony, we optimized the grain size 1. So another factor is we have to optimize the texture. Whether we optimize the texture or not, it will come to in this slide. So these are the texture of the hot rolled microstructure. This is the surface and center. You can see in the surface predominant texture is the, and when you cold roll, the basic BCC texture evolved like alpha and gamma. So this is the, at the cold rolling texture came, even though there is a difference in texture in hot rolling and hard banding, for the both cases texture became the same during the cold rolling. So when we recrystallize this material, the magic happens here. So these are the 4 samples I stacked one over the other because of the 0.5 mm alignment of inside the SCM is difficult. That's why we stacked 4 and we made a bunch and we did the E-based-D. This is the E-based-D ODF and this is the bulk texture ODF. As you can see, with increasing the antimony, the texture from gamma it moved to theta. And grains also, from bigger grains we will get the smaller grains. So these 2 are main important for the electrical steels. So because of these changes, how the properties are changed? By decreasing the gamma and by increasing the theta, we are increasing the texture factor. So because of this, we got the lower watt loss by going from without SB to with SB, and we got the higher magnetic direction. So in the first case, I explained the how hot band annealing changed the microstructure and texture. In the second case, how alloying additions are changed the microstructure and texture. So this is the one of the product. So we successfully developed. So far, this is the highest sales revenue in our product. From March to so far, we earned the 12 crores extra profit from this grade. So another one is the EV grade. Like this is the proactive development, not commercialized. So in the EV car, at the low speed, we required higher torque. So it is given by the high flux density. And at higher speed, we required very less losses, which is get from the lower losses. In the EV grade, we required both high magnetic induction, low losses, both are required. Along with this, mechanical property also important, because in a traction motor, it will rotate on 8,000 RPM, 10,000 RPM. So higher mechanical properties also required. So we taken this is the route. So in the previous case, we did the cold rolling and directly annealing. Because it is at 0.25 mm, we introduced intermediate annealing and second cold rolling to get the reduction further. So this is the, like earlier I showed the microstructure only, how the heterogeneous is the microstructure. So here I am showing the IPF map. So microstructure from top to bottom is very heterogeneous. In the top, I plotted the fibers here. So legend of the fibers I have given. Blue grains are the gamma, and red grains are the theta, and green grains are the alpha. So in the center, you predominantly observe the alpha grains. In the top, we can see the zeta fiber mostly. So when you recrystallize it, so most of the microstructure is changed. But if you see texturally, there is a texture hereditary followed, even the recrystallization happened. And a majority, if is a alpha, is went to alpha star fiber. So after that, we did the first stage recrystallization. So these are the 2 samples stacked together. As you can see, we did the 60% rejection. Majority of the grains is developed as shear bands. So this where these shear bands are mainly located, I superimposed the grain orientation map on the IQ map. You can see majority are there in the gamma grains. So which are the better nucleation shades for the cube texture further. So if you do intermediate annealing, so already some cube grains are already formed. Again, second cold rolling I have done. So in the second cold rolling, shear bands formed. If you zoom in here, along the shear bands there is a cube nuclei, already strain-free cube nuclei is there, which is further advantage. So if you recrystallize it, These are the samples of 0.25 micron stacked together, and we dig this thing. If you see, majority of the cube grains are retained in the final recrystallized microstructure. So this is the texture evolution stage-wise. Initially, we have the strong alpha fiber texture in the HR. It changed to alpha star fiber in the first add band annealing. Then comes to the gamma, and then after second add band annealing, gamma is reduced. Then again gamma fiber came. So in the final recrystallized annealing, cube texture with lesser gamma fiber is achieved. So this is the cube components plotted against the stage wise. You can surprisingly you can see the theta fiber is maintained constantly throughout this one, and gamma fiber is decreased in the final. So overall texture factor is increased. So these are the properties which we have achieved with this trial. We can get the 12 to 13. These are the customer requirements. These are the achieved properties with this trial. This is the proactive development. So, and another thing, as a proactive development, so we changed the intermediate annealing. This means between the first cold rolling and second cold rolling, temperature we changed from 750 to 1050, and I have plotted showing the how intermediate annealing is changing the properties. See, there is a drastic decrease in the watt loss with increasing the intermediate annealing. The axes are not main because of the confidentiality, and there is a drastic increase in the magnetized B50. So B50 with increasing the intermediate annealing. So finally, my conclusion is texture is no longer a metallurgical curiosity. It is a central design theme for powering the next generation energy efficient electrical missions. Thank you.
The volume fractions.
Volume fractions, yeah. Some people will consider gas as also good, theta plus gas by gamma, but I considered theta by gamma.
Okay. And what is the, because that depends on the tolerance that you include.
15 degree means
15 degrees.
Yes.
Okay, thank you.
My question to you is, in the CRGO steel production, so like which stage, like in the processing stage, has the final texture, like a gauze texture, influence in which process? Like in secondary recrystallization or decarbonization or like?
Yeah, in CRGO, the process will start from the casting itself. So there are different technologies of CRGO, high slab heating, low slab heating, depending upon the composition. So we are working with both JFE and Tyson Group. Both are employing different technologies. So it will, the final texture effects from the casting itself. There are a lot of parameters. The main is precipitates will decide the final, in the secondary registration whether you grow a gas or not will depend upon the final precipitates. That is comes right from the casting.
So the initial conditions are different.
Each stage matters.
So one more question.
Is we can supply one customer to another customer. In CRGO, if gas grain is not grown in the secondary recrystallization, the material is scrap. There is no other alternative.
One more question. Have you ever tried warm rolling in JSW?
No, warm rolling is, here warm rolling is not possible. Because warm rolling will give the good properties in the material. But as I said, surface finish, surface roughness is more important in electrical steel than the magnetic properties. Because we are stacking one over the other. Okay.
So I think this talk has been already presented like with STBM, like antimony in IMW.
Yeah.
Yeah, IM, yeah.
Last year I presented.
Yeah. Okay, thank you.
Okay, I would like to thank the speaker again. Thanks a lot. Okay, let's go to the next talk. Heath Young from Brooker. Are you feeling better? take your time. I think you can shorten even if you feel like.
Can I find your presentation?
We are 20 minutes late?
Yes, yes, sir.
It's my short one, so you'll be okay. Okay, thank you. Yep. So how do I move the slides on, and how do I do that? Okay, that's point to the next slide. Okay. Oh, okay, thank you very much. So my name's Heath Young. I'm Regional Sales Manager for Europe, India, and the Middle East for Brooker. Electron microscope analyzers. This is what we do. So today, my talk's going to be on EBSD, our products on EBSD, but just a quick summary of what we do else. We do, obviously, we do WDS, we do micro XRF, standard inclined EDS detectors, flat quad, which my colleague Atul talked about yesterday, and this is our new flagship EBSD camera called eWarp. And all of these detectors go on one single software platform, so they're all controlled from one source, and they use common algorithms, things like advanced phase ID, and it's all from one software platform. So I'll start with, so we have EBSD for all users and all levels of budgets as well. So I'll start with EDXS. This is a combined EDS and EBSD system, the world's smallest EBSD camera, and the cheapest combination of EDS and EBSD. Then I'll talk about on-axis TKD, transmission acoustic diffraction, using our patented Optimus 2 head that goes onto our CMOS camera. This has been developed along with our product manager, Daniel Goron, and we can go down to like 1.5 nanometer spatial resolution. We're really turning our kind of SEM into a low KVT, so a low KVTEM. Then lastly, our new flagship eWarp, direct detection EBSD camera, which was launched last year. And this camera is actually going into IIT in Mumbai at the end of February this year. So we encourage you to go along and have a look at the system and run your samples there. So EDXS. So we have our EDS. It's a fixed design, so it's no insertion retraction. Our eFlash EBSD camera, it's all USB-free power, so the data and the power comes from one connection only, and it goes onto a combined single port on the SEM, which you'll now see. So there's the detector against a Brooker pen, just a normal ballpoint pen, and you can see how small it is. So it's got a frame rate of 520 frames per second, binning modes from 2x2 up to 6x6. It's a fixed design geometry-wise. So this has got a dovetail head on here, which basically you can take this head off of the inside of the chamber. This is where the flange is, and then frees up the space in the chamber, and it's just a basic dovetail, slot in, slot out. Then the EDS detector, as I said, it's a fixed design. We're measuring from boron up to americium, 129 EV at mean K alpha, fixed design. And what I will actually state about all of our detectors, which I don't think Atul mentioned yesterday, all of our detectors are now FRU concept, which is field replacement unit. So the silicon drift detector inside this EDS detector now can be replaced on site in less than half a day. That includes the super light element window as well. So basically, there's no need to ever send any of our detectors back to the factory now because we can do this on site in less than half a day. This includes our EDS, EDSD, flat quad, everything. So here's the geometry design. This was originally designed for the Joel Corporation in Japan. They had the exclusive rights to it for the first year or 2 years, I believe. That one. So what you can see here is zoomed in of what you get here. So here is the dovetail sitting here. Here's the EDS detector coming in. And then there it is again now. And here we have the phosphor screen, which is also like our previous CMOS or our current CMOS camera as well. That phosphor screen is user replaceable. So if you bash the screen at all, or you scratch it or whatever like that, you just slot in and slot out a new phosphor screen, which is we have those in stock constantly. Here's inside a couple of examples of where these systems have been installed. This is on a Thermo Fisher Scientific Axia Chem. And you can see the detector coming in here. And that's it, kind of, well, sticking out there. It's very, very tiny. Oh, one more. This was on the Coxem, benchtop SEM, the Korean company. So you can see again the EDS detector, EDSD. And this solution, this combined solution, is available on many, many systems, not just these two I'm showing now. So things like the SEC from Korea, it's compatible with that benchtop microscope. It's also compatible with small chamber SEMs like the Zeiss Evo 10 SEM. And a couple of other slides now. Okay. Showing you on a test scan. So it's generally on the LM chambers, the ones that are really tiny, tiny chambers, has what you can see is a combined port here. So this is one flange with the EDS detector going in, and then there's EDSD. And another one, so it's available on Claras, Vegas, Magnas, and Miras. Now we go on to TKD. So we still keep this product at the moment because we've got what we call on-axis TKD. So this is basically, the phosphor screen doesn't sit at an angle to the actual sample anymore. It actually sits in line with the pole piece. So we measure electron transparent samples directly in plane with the phosphor screen, giving us the maximum signal and the maximum spatial resolution as well, as it's down to 1.5 nanometers, which means we can actually measure very, very fast at fairly low beam currents, and we get no distortion or drift. Yep, okay. Now, I forgot to mention that head here is basically yet again, it's just a slot in, slot out. So basically you can go from standard mode with the phosphor screen in this plane to it being in this plane in less than 5 minutes. So here's another enhancement we made to the Optimus product, along with, I think it was TU Delft we developed this with in the Netherlands. So we now really extend the capabilities and turning it into a real kind of low KV TEM, because we now have originally dark field imaging. Then we introduced another silicon diode in the center of the phosphor screen, and that gives now bright field as well. So we get the best of a lot of the worlds that TEM guys already do, so at the fraction of the cost. And here's some other kind of techniques or detectors we actually combine that detector with. Here's our flat quad, which Atul talked about yesterday. So you can see the pole piece here. Here's the finger of the flat quad. Here's the sample holder. Here's the phosphor screen in the in-plane orientation, getting those direct electrons through the electron transparent sample. And then lastly, I'm not sure I should be pointing here or there, we also combine this with our Pico indenter from Hysotron. So what we're doing here, we're actually doing simultaneous measurements of indentation, as well as taking real-time crystallographic information through TKD with the Optimus 2. Now finally, our new eWarp. So this has been 7 years in development. Our product manager in Berlin has done, we think, a fantastic job in creating the most sensitive, fastest EBS detector ever made. And hopefully you'll agree. So here it is. eWarp stands for Wide Area Pixelated Sensor. And if you kind of look at the warp kind of word here, if anybody knows anything about sci-fi and Star Trek, when they go into hyperspace, they go into warp mode. So he's a bit of a Trekkie. So this is why he named it Warp. The actual sensor itself, as I said, has been designed for over 7 years. It's a custom-built Brooker design made from CMOS and silicon. It's fully patented. And it's got on-chip bidding as well, up to 10 by 10. And it's got integrated forescatter and backscatter detection as well, with 100 channels. Most traditional companies, including ourselves previously, were just like 5 channels, 5 different diodes. We've now got 100 diodes, which is on-chip. So yes, 14,400 frames per second. We are now 3 times faster than any of the competitors out there. Yep, patented design. It's wide area pixel, 160 by 160 microns. It can be used at very, very low kV and low pro currents as well, which is very, very good if you've got sensitive samples. We'll see some of the examples. And it's flash firmware upgradable as well. So yet again, as I said, the sensor itself, you can't see it's on the left-hand side, but oh, here it is. Okay, so there's the sensor. This is a plug-in, plug-out sensor. So literally that can be changed in 15 minutes. So if it ever were to die, just swap it out and you're up and running straight away. On-site replacement. Where are we now? Okay. Yeah, so we can flash the firmware, and we've got lots of things planned about developing this product to really enhance it and keep it really at the top of its game. We've got a predictive monitoring feature on there as well, so we can actually monitor the life and the performance of the detector itself and report this back to the user, or if they actually agree, to report that back to Brooker, and then we can monitor the system ourselves, and we can predict when there's going to be a failure or a problem. And as I said, 10 kV is the new norm for this product. We don't need to go higher than 10 kV. If you see, this is at 15 kV. This is a, what is this now? Titanium alloy, and we go to 10, and hopefully you can see, I don't have the resolution of this screen here, it's much sharper, it just locks in. That's the geometry of the eWarp here, coming up to the sample. So now we're actually going to look at a nickel superalloy, beam conditions 10 kV, oh, go back one, 12 nanoamps, 14,429 frames per second, 7.7 megapixels, and a mapping time of 8 minutes. If you were to do that on a conventional CMOS camera, you'd be talking over 30 minutes, maybe 45 minutes. So you're really, really kind of reducing the time of your mapping now, really, really considerably. Step size of 25 nanometers, which is the spatial resolution of the product as well, and the indexing rate, that one, is 99%, so it's almost perfect. So now some nice pretty pictures. And what we're seeing here now, just to prove the spatial resolution, we're looking at annealing twins of resolving annealing twins of just 100 nanometers wide, excellent indexing quality, and pixel size of 25 nanometers. And then we go a little bit further, we can also see some precipitates as well, which are 50 to 100 nanometers wide. You zoom in there, you can see where they are, and then we get a zoom in here, up to here, and there you can see them. And of course, we can also work out the orientation as well, so we learn about the structure and nature as well. This is the other thing I talked about, which is the forescatter, backscatter diodes with 100 LEDs on chip, built into the chip itself. So we can collect that contrast image super ultra fast at 350 frames per second. It's almost as quick as like a backscatter refresh It's super, super fast. And it's all on chip, so the product only comes with this integrated anyway. You can't get it without it. So it's not an option. It comes included with the product. And it's ideal for things like in situ experiments. Another one, another nickel superalloy. This is using the 4 scattered diodes again. So what we've got here, we've got 10 kV, same kind of full speed, 25 nanometers, same kind of thing. And then more pretty pictures. Really high contrast at super, super fast times. Next one is a hot rolled carbon steel. Now we're actually doing this at 5 kV. We've got some data on 2 and 3 kV as well, which is got pretty good results as well. So we can go down to very low kVs with this product because the sensitivity is so good. Okay, so that's showing you orientation. Next one is plastic deformation of an aluminum alloy. 10 kV, 12 nanoamps, a very, very, very small pro current, which no competitor can get close to, not that kind of small. 2 megapixels, and mapping time was 52 minutes, but it's a pretty big sample and pretty highly resolved. Next one is, still the same thing, it's a deformation of an alloy. And severe okay, so 10 kV, 12 nanoamps, 20 nanometer step size, indexing rate, pretty good at 79%. And that's it for me. Thank you very much.
Any doubt or question on the capability?
Hanulio would have a question.
Sure, I have questions. With very impressive data and images that you've shown. I remember a few things. For example, you speak about the resolution of 1-2 nanometer for TKD. How do you do this? Because I always thought that the resolution was in the end determined by the thickness of the sample.
Yeah, well, so okay. Obviously, with TKD using an electron transparent sample, 50 to 100 nanometers in thickness, we're obviously doing in plane. The whole thing is coming from the pole piece through the sample directly onto the Foster screen. So that's how we optimize the actual kind of signal intensity and the resolution. Obviously, with 1.5 nanometers, you'd have to have a very decent FEG SEM to actually run it on, plus also a very, very good isolation.
What acceleration voltage did you use?
So this product currently, the on-axis TK, is on our mid-level system, the E-Flash FS. So it's coming for E-Warp. It's not arrived yet, but E-Warp will have on-axis TKD. So your question again was?
Pardon?
What was your question again?
Which acceleration voltage?
Oh yeah, so slightly higher acceleration voltage than you would do with E-Warp. Okay. But when we do eventually introduce on-axis TKD for E-Warp, which is later this year, I can't say when, then again we can use 10 kV, and we can even go down to like 2 or 3 kV.
And then if I may ask a second, so you had these ultra small mini EBSD camera.
Yes.
Was this? But this is not retractable.
No, this is fixed geometry, so it's exclusively for small chamber SEMs. So it's perfect for benchtop SEMs. So what it does basically, as I said, the dovetail, it slots in, slots out the actual head. You take it away from the inside of the chamber, frees up the space, and then when you want to go back to EBSD, slot it back in, do your EBSD work, and then you're good to go.
I get it. Yeah. And then the E-Warp camera, is this still with a phosphor screen, or is it's a digital camera then?
Yeah. So basically, it's like, think of it as an example of a Medipix camera. The reason that we can be competitive with the E-Warp against our competitors now, because we designed the sensor ourselves. We didn't buy in the technology like EDAX do.
A potential liability that I see is that the camera is fantastic, no doubt about it. But anyone who has worked for a long time with EBSD knows that very regularly, because you work in a very narrow space confinement, that phosphor screens get scratched.
Oh yeah.
And you have to replace them.
Which ours are user replaceable. Yeah.
But what about these digital cameras? Do you have to pay?
Yeah, but you don't. I mean, that's the
these
thing.
digital screens, sorry.
Yeah,
the
well,
detectors.
It's hard to see from what you saw there, but basically the actual sensor is actually recessed back from the finger housing, so you're not actually going to indent when it's a few millimeters back retracted.
So there is a protective layer.
Exactly.
Okay, so it's kind of an advantage that you.
Exactly.
Okay. Yeah. Okay. Okay. Thank you. Very impressive. Thank you.
Thank you. Any other question? Okay, we move to appreciate the speaker. Thanks a lot.
Thank you. Thank you.
Okay, now is the online. Professor Indra?
No, sir. One more.
Yes, I'm very much there.
Oh,
so sorry, guys.
Thank you.
Doing it online. Let me just open the slides. So one of the two.
Who is there? Okay, can you wait, Professor Indra, for 20 minutes?
Sure.
Okay. Yeah.
All right. Hello. I hope you can hear me. I'm going to share my screen.
Yeah, please. Thank you.
Entire screen. Present tab, entire screen. Share. Okay, so you're sharing my screen. So can you see my presentation? Okay, and I need to minimize this. Okay, why does the slideshow not launch? Ah, good. Can you hear me? Can you confirm that you can hear me? Okay, excellent. Well, what I'm going to do for the next 20 minutes or so is talk about the development and different types of detectors, and also the different indexing methods, as this is all very relevant given a couple of the talks that you've had already. So this goes back quite a long way, obviously, and back in the very early days of EBSD, the camera technology was nowhere near as developed as it is now, and we were using silicon intensified target cameras. These were very large and bulky with a very large lens, and these would be installed outside the tube of the detector, which would have a circular phosphor at the end. Not quite like my drawing at the top there. The lens would actually be too big to fit in the tube, and the whole camera and lens would be quite some distance from the phosphor, and you would focus onto the phosphor screen with the lens and take that image away and do whatever it is that you wanted to do with it. These were tube type cameras, very noisy, and not a great technology really. And along came CCD, charge coupled device, and these types of camera were very superior, but again, quite bulky, and so would normally be installed outside the detector tube, quite some distance from the phosphor, and it would have a, quite a large, hopefully large aperture lens to try and image the phosphor screen itself. Then a development came along where you could get remote head cameras, and this meant that the actual front end of the camera could be removed from the body of the camera, as you see in the third picture down, and the lens could be moved much closer, and this greatly improved the sensitivity. And the sensitivity is compromised by how far away the lens is from the phosphor and the acceptance angle of the lens, the amount of light that's going to enter the lens. Because if you consider an individual point of light from the phosphor, it's only those rays of light which enter the lens that will actually be registered and used to form the image. So CCD cameras were in use in this configuration for quite some time, and then the manufacturers of imaging devices moved over to CMOS, and CMOS as a technology has many advantages over CCD, but unfortunately they're generally not as sensitive as CCD cameras. So even though they can run faster, they're not generally as sensitive. So if you do nothing else but switch to CMOS from CCD, you find that you've got a less sensitive detector, which is very irritating. So at that time, when we moved over to CMOS, we looked at an alternative to getting the image of the phosphor back to the imaging device. And the obvious way of doing this is with fiber optics. And the advantage of the fiber optics is that you don't have all of the losses associated with the lens. So just a very brief thing here on CCD versus CMOS. Really the big thing about CMOS, as I've just mentioned, is that it's a parallel device. You can read out many registers simultaneously, and this gives you much higher speed. But it does generally have, as a camera technology, a little bit more noise and lower sensitivity compared with CCD. Also, you can't have any on-chip binning like you can with CCD. But using the fiber optical coupling, this gives you by far the greatest sensitivity. So just to show that graphically, in the top picture, you can see a theoretical point of light on the phosphor screen. Light will be emitting in all directions, but only the light that enters the lens will actually be focused onto the device itself. Now, using fiber optics, any individual photonic event that's at the phosphor screen can be captured and taken via the fiber optic to a corresponding position on the device. You lose all of the losses and aberrations associated with lenses, and the collection efficiency is very much higher. Now, as we've just heard, direct electron detection is coming onto the scene, and these detectors generally, bit of a sweeping generalization, generally favor low dose, low kV, although we did see in the previous talk 12 nanoamps, which I would consider middle to high beam current, really, being used for doing your EBSD experiment. So generally being operated sub 10 kV. There are many different varieties available, as alluded to earlier, either off-the-shelf type designs or those that have been made specially. And of the variety that have been made specially, I think I'm right in saying that the pixel resolution is 100 by 100 pixels, so relatively low pixel, well, very low pixel resolution compared with other types of detector, although you do have very high speed available. So if we compare direct electron detection with an indirect electron detector, then if you're using a lens coupled system, and all systems on the market apart from the Oxford Symmetry and related detectors, they are all lens coupled, so suffer from the fundamental lack of efficiency that I've just alluded to. Using the fiber optic coupling greatly increases the sensitivity, and so the sensitivity is actually comparable with DED from mid-range to high electron doses. And I would say mid-range would be from a few nanoamps, maybe up to 5 nanoamps would be, mid-range, and 12 nanoamps or more I would consider a high dose. So we can see that the sensitivity is on a par with direct electron detection at higher beam currents and doses. Also, we have very favorable collection geometry and That makes EDS possible at the same time, which opens up phase ID, EDS mapping and line scans, and using EBSD and EDS together, which we call true phase. We have a proximity sensor to prevent collisions, and obviously the phosphor is interchangeable, which means that you can have field replacements should there be some damage, as was mentioned in one of the questions. You can have an infrared filtered front end, which means that you can do hot stage work, and you can also have a near axis TKD front end, which benefits from using fiber optics rather than an on-axis, which uses a mirror and a lens with the associated loss of sensitivity compared with fiber optics. So using fiber optics, whether you're doing EBSD or TKD, is very much in your favor and puts you in the same kind of territory in terms of sensitivity as DED from mid to high doses. And as I say, I would regard mid as 3, 4, 5 nanoamps, something of that nature, and high maybe 10, 12, 15 nanoamps, something like that. Also, we can vary the collection geometry, which means we can move the phosphor up and down. We can accommodate large samples. It's the most versatile combination, most versatile type of detector. Now, the direct electron detectors, I won't go into any great detail here, but as it's already been covered to some extent in an earlier talk, but basically they come in different varieties. You can have single electron counting or charge integrating. There are some on the market which use off-the-market detectors, which have been mosaic together to give a larger active area, although the speed in that case is somewhat limited. Or as we've seen in the previous talk, a smaller detector with a much lower pixel count, but then much higher speed. So very different characteristics. Generally, the direct electron detection finds favor at lower energies, although I think it's at a cost in terms of the versatility of the sort of work that you might want to do in your lab. So very small physical size, low pixel count. Obviously, you've got a very extreme risk of collision and also contamination for that matter. I mean, generally speaking, I think it would be very difficult to do in situ experiments, but I mean, certainly not hot stage because you've got no means of blocking out infrared. And I've put here expensive and long downtime. I've just heard that the front end can be changed on site, but I don't know at what cost. But I mean, certainly one has to consider the practicality of direct electron detection in terms of the sort of usage that you're going to have in your lab. Electron dose, this is something that we need to think about, and this is essentially the beam current in relation to the time that the beam is falling on the sample. So we normally express that as nanoamps per millisecond as the overall dose that's being delivered to the sample. Some samples being less able to manage high doses than others. So there are, of course, many beam-sensitive materials. Also, it can be referred to as patterns per second per nanoamp. But generally, beam-sensitive materials are poor diffractors, and it's not always practical to go to low doses and very low kV on very beam-sensitive materials. But we find that for the vast majority of the sort of work that you would want to do, you can work perfectly happily in the range 10 to 20 kV or even 30 kV if you're talking about doing TKD. The spatial resolution thing, yes, going to lower kV does give you better spatial resolution, but only in terms really of the backscattered and secondary electron signal. The escape depth of the electron backscatter pattern, the electron backscattered electrons, is very shallow, only of the order of a few tens of nanometers. So provided the beam diameter is kept small, the spatial resolution of the EBSD itself is really much better than the actual microscope image, or the EDS, obviously, if you're doing EDS. So going to very low accelerating voltage isn't always universally acceptable, although obviously one can, if one wants to, improve spatial resolution for the imaging in the EDS, reducing the beam damage, although obviously the intensity and the contrast and the pattern may be diminished. You also, low KV, have to think about the sample preparation, which is more critical. Any contamination is more critical. And also the Kikuchi bands annoyingly get much broader. And this can compromise the band detection unless you've got things really under control there. So if you want to look at more difficult things to index, i.e. not just cubic materials, you know, we saw examples earlier on steels and aluminium and I think titanium, but basically fairly high or high symmetry materials. It's the low symmetry stuff that's really difficult, and that's the kind of thing that very often you find yourself encountering and need to deal with. Okay, let's crack on, because time is not our friend. So low electron doses usually used for beam sensitive materials. We've applied this to many cases of biomineralization, calcite, aragonite, mollusk shells, coral, things of that nature. So it is perfectly possible. Here we see an example at 5 kV using our fiber optic indirect electron detector, the symmetry detector. So you can see that operating with our detector is perfectly possible down to 5 kV or even lower. Well, now we should think about the direct electron detection collection geometry, and this is just a simple drawing that I made in paint, not to scale or necessarily completely accurate, but I think you get the idea that if you have a smaller active area, it needs to be that much closer, and that has certain considerations for the size of your sample and how you can move about. If you want to use a hot stage, the likelihood is, unless it's very compact, that might not be possible. If you want to use a tensile stage, these are usually quite bulky, and again, that's a consideration. You may not be able to get it in there. And also, if you're doing any 3D working, you know, you're going to be ablating material, and that could be depositing on your detector. And also, if you want to use this detector in its standard guise for TKD, that may not be possible, but as was mentioned earlier, a separate development could be coming along on that front. But I mean, there's a lot to consider there with direct electron detection. So we can see that when you've got the conventional size of phosphor, you're that much further away. You can easily accommodate large samples. You can usually, if you've got a eucentric or compucentric stage, do large area mapping. Obviously, you can do the EDS as well. You know, you can have long or short working distance, and obviously you have a good secondary electron signal as well. As you can see, the detector cage is in there. You know, it doesn't compromise your electron image in any way. And here in this case, we can see that we can do simultaneous EDS at the same time. Okay, we're running a little bit out of time. So let's have a look at indexing methods now. And this is really because there have been developments more recently with spherical indexing, etc., and there's a lot of interest in that. So to start off with, all of the indexing was done manually. There was no automatic band detection. You would draw lines on using the mouse, and once you defined some lines, the computer would measure the angles between the bands that were in the pattern, and it would index the solution. Now, of course, that was painfully slow and made mapping completely impossible. So all you could really do was just make point measurements and maybe look at them in a pole figure or an inverse pole figure or something like that. So Huff indexing used a mathematical treatment of patterns, the so-called Huff transform to mathematically convert the pattern into a series of bright maxima in what would be referred as Huff space. Then the bands would be detected, and the angular resolution of those bands would be a function of the pixel resolution of the Huff transform. And once you'd obviously automatically detected the bands, the angles would be measured, the indexing would be done, generally fast, generally reliable, and for many years, perfectly acceptable. But its biggest downfall was that if the patterns were not of good quality, then it may fail to index accurately, and obviously poor sample preparation, although really we shouldn't have poor sample preparation, but it does happen. But residual strain and very small grains can defeat what you can achieve with Huff indexing. So more recently, there's been a great deal of interest in pattern matching, if we can call it that, a direct correlation of the pattern itself. And this was developed largely to index very poor patterns. So the first generation was dictionary or library indexing, and this is where you generate a very large library of patterns, simulated patterns in a dictionary, and then compare those sequentially for the entire space to match up with a simulated pattern. This was painfully slow. So a variation on this was researched and developed, and this is referred to as spherical indexing. And this is where spherical harmonics are used instead of the direct correlation of the very large dictionary. And this makes the whole thing much faster, but it's not without its limitations. Angular accuracy, multi-phase, low symmetry samples, and it doesn't bring any new information to the table, compared with the earlier Huff indexing method. Now, we have a new type of indexing. I put it here and called it innovative pattern matching. It's really the next generation, and we've called it dynamic pattern or template matching. And it's a really hybridized approach where you can use Huff indexing as far as you can and carry on with pattern matching where Huff indexing leaves off. So you can really get the best of both worlds. You can take your Huff index data and massively refine the angular accuracy down to 0.01 of a degree. You can get new information such as crystal polarity and resolved pseudosymmetry. And also we have superior phase discrimination. So it really enhances the total number of points that you can index. So here is Huff indexing. Top left, you see you have your pattern. Then using the Huff transform, you convert it into a series of maxima in Huff space. You have a certain number of bands that you've detected and you index it. But unfortunately, the angular resolution is about 0.1 to 0.5 of a degree. Pseudosymmetry can be problematic, and you can't resolve crystal polarity or left or right-handed crystal structure. And obviously poor patterns can be very bad news. So the dictionary indexing, you compare all of the patterns that you generate against your master pattern that you have to create. So you might have to compare tens of thousands or even millions to find a good correlation, a match between your experimental pattern and your simulated pattern and the simulated master. So it can index poor patterns, but it's very much slower than Huff indexing, and you need to generate these very large dictionaries, a million for a cubic material, for a 1 degree angular accuracy, or if you're going to go to a low symmetry material, if you want even half a degree, you have to go to ridiculous numbers. So really the dictionary indexing is not a winner. So the spherical harmonics really gets you a very great speed improvement. And this is because really, essentially, you don't need to generate this dictionary anymore. And it works by projecting a spherical rendering of the pattern on the internal or the surface of a sphere into which you can project your master pattern. And the spherical indexing can be quite rapid as well, so you can get really quite high speed. But whilst it's tolerant of poor patterns and high noise, there is a limit. And also because of the limitations or the computational overhead of doing the harmonic transform, there's a limit to the angular resolution that you can get. I'm going to have to speed up a little bit here because starting to run out of time a little bit here. So similar to dictionary indexing but faster, similar quality to dictionary indexing. The bandwidth that's used to calculate the spherical harmonic is the issue really, and that is that if you want to calculate with high angular accuracy, the calculation time goes down dramatically. It is slower than Huff indexing, although obviously it's much faster than dictionary indexing, but the time is very much dependent on this L value of the spheric harmonic expansion. So there are certain dependencies, the pixel resolution itself. So generally high resolution patterns are going to present difficulties for using this approach. Also the quality of the pattern and the effects of lattice distortion. So if you want to do stress and strain measurement, there's a consideration there. When it comes to indexing errors, there can be systematic misindexing with phase variance and overlaps and pseudosymmetry. So it's a great improvement over dictionary indexing, but it is affected by the pixel resolution and the quality of the pattern, as you would expect, and the graph shows. But it is one of the more recent and better approaches, although what I'm going to talk to you now about is really an advance on spherical indexing, and this is where we have what we call dynamic template or pattern matching. So this differs from spherical indexing. It's not using spherical harmonics, it's using a cross correlation. It's in 2 dimensions, not 3 dimensions. And if you've got Huff index data as a starting point, even if it's relatively poor, it provides you with a starting point. So you know roughly where to start searching to match the pattern. And with this much smaller subset of possible solutions, that greatly reduces the overall search. We calculate the patterns for the matching in real time, and we do this in 2 stages. First of all, we do it at very low resolution for the pattern matching. And once we've got a solution, then we zero in on the correct solution at much higher angular resolution and pixel resolution for the actual matching process. We use the geometric calibration over the entire frame, and this greatly improves matters because the indexing is very important, very reliant on the calibration, and one single calibration at the center of the frame would mean that away from the center at low magnification, there would be a compromise. So here you see an example of the pattern center. If you just use the single pattern center, then if you're operating at low magnification, you know, your pattern center is going to vary quite dramatically from corner to corner. And we're able to dynamically use that calibration. This is very important. It makes this process viable even at very low magnifications. So here we see how the correlation is actually done. You've got an experimental pattern top left, and you compare it with your simulated pattern on the right. And if you've got a perfect match, then the R value would be 1. If you've got a pattern, or in this case, a picture of a kitten, which obviously is nothing like the simulated pattern, then the correlation factor is 0. So you can see that we can set a threshold value to say above this, to consider this to be a solution. So here is our two-stage method. We get the experimental pattern to start with. We generate our matching patterns at 30 by 40 pixels, very low resolution. We find an approximate solution, and then we zero in using much higher pixel resolution and using the actual geometry from the individual pixel, not just the calibration from the center. So here we see an example of a very poor pattern, unreliable Huff transform indexing, and then the result there, which is being indexed. So we can index where Huff indexing can fail. So here you can see top left, a good pattern, a not so good pattern, a very poor pattern. That we can correlate against that, and we can get an indexed result with much better angular orientation. We can improve the indexing rate. We can resolve indexing errors. We can improve the phase discrimination, and we can even resolve pseudosymmetry and crystal polarity. And this really opens it up to highly deformed and nanocrystalline materials. Here we see the orientation refinement, where the simulated pattern is being jiggled until we find the best R value, and that makes it possible for us to get down to angular precisions of 0.01 degree. Okay, so to compare spherical and the dynamic, the calibration is simple within the dynamic pattern matching, whereas in spherical indexing, it's super critical. And that is because there's a projection of the pattern calculated into the spherical space, and you need to know with very high precision where the pattern is being projected from. So calibration is very critical when you're doing spherical indexing. That really needs to be looked at very carefully. And it also means that it only really is going to be true and accurate at higher magnifications where a single pattern center is suitable. Overlapping patterns can be problematic, and there can be masters generated with specific overlaps in order to cope with that situation. Also, low symmetry phases generate a high computational overhead, particularly in making the master patterns. The setup's quite complex, and it can be limited by low signal to noise ratio. When we look at that with the dynamic pattern matching, which we're doing in the Aztec Crystal software, then calibration is simple. It's all done in post-acquisition. It's a hybrid approach using both the Huff indexing and the dynamic pattern matching, although we can do just straight dynamic pattern matching if wanted. We can do this on low symmetry phases. We can separate very similar patterns and thus get crystal polarity, pseudosymmetry, and stress and strain measurements out. Very simple to set up, and it's very applicable to strain measurement. So here we see an example of a highly deformed diamond, only 50% indexing with the Huff indexing, and you can see what the patterns look like. But when we sweep through the data using the dynamic pattern matching, you can get this very much better result. Here you can see phase discrimination issues in oxide layers on a steel, quickly and easily resolved using the pattern matching. I'm going to whiz through these fairly quickly. Here you can see titanium carbon nitride not resolved terribly well. We can do this directly with a dynamic template matching. This is not a cleanup operation, and you can see how we can greatly improve the quality of the data using this approach. Here you can see inversion domains being correctly resolved. Here we can see dislocation analysis in the Huff data, not very good. and here we see resolved using the dynamic template matching, very much better. Here we can see with the Huff indexing, the initial data with the CAM map or weighted Burgers vector map, no real visible data, but when we use the dynamic template matching, we can see all of those domains in this solar cell. Here we see correcting for pseudosymmetry. And we can see here that pseudosymmetry being corrected. So this is in a tetragonal structure. This is not being done on simple cubics. This is tetragonal. Here we see a highly deformed titanium. You can see the quality of the patterns, and we can get from an approximately 80% indexed result, 79% to about 99%. Here we see a very highly strained aluminium alloy. You can see there's a large amount of data missing in the middle of the map. We can greatly improve that, restore all of that information and get up to 90% indexing using the dynamic template matching. Here we can see the phase analysis and how we can restore the vast majority of the data up to 97%. The crack tip is actually at the bottom, the top of the image. Here we see kernel average misorientation. This is the original Huff index data, and here we see that we can get all of that information now using this dynamic template matching. This is TKD. We can see that we can get from about 56% indexing on nanocrystalline deformed duplex steel, get up to 88% indexing, and in the iron BCC, practically 100% index. Really very good indeed. And pretty much my last slide, I think. This is showing something like, I don't know how many is there, about a dozen different phases, all low symmetry phases. This is as indexed using the fiber optic coupled indirect electron detector, the symmetry detector, and the dynamic pattern matching. So to summarize, using fiber optics in our indirect detector gives you performance which is not so different to direct electron detection. From mid to high doses, we've got collision avoidance, interchangeable front ends, compatible with in situ experiments, very high speed, up to nearly 6,000 measurements a second, a variable collection geometry. You can work with large samples, long working distances, and it represents the pinnacle of indirect electron detector development, whereas I think it's fair to say that direct electron development is more or less in its infancy. And dynamic pattern matching, map sweeper as we have called it in our product, combines the best of Huff indexing and pattern matching, and I think it's fair to call it next generation indexing, because we can achieve 0.01 degree angular accuracy, massively improved phase discrimination, pseudosymmetry, polarity. It complements strain analysis. We can do all of the stress and strain analysis with the new tools. It opens up new applications areas, nanocrystalline, highly deformed, electronics, beam sensitive materials. There's dynamic calibration, it's fast, and it's very definitely not just for bad patterns. So the combination of the symmetry detector and our pattern matching, it's not just for bad patterns. We can deliver very high performance over a very wide range of materials, not just simple cubics. So I think that's, I've run over time a little bit, but I think that's my message.
Thank you.
So happy to take any questions.
Yeah, is there any question? No, thank you. Thanks a lot. Hariharan is here. Okay, yeah. So we once again. again. So now the last speaker. Sorry, Indra, I didn't want to keep you last, but you know, at the end, here we have the legends, so we need to match, you know.
I told you I had a class away till 3:30, so I needed the time. It took slightly longer. Are you able to see my screen?
Yes, 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 yes. All yours.
All right.
Yeah.
So shall I start?
Yes, please. Yeah.
Leo, good to see you from a distance.
Yes, and Satyam is also there in the middle.
I know. Yesterday I was with Satyam.
Yes, yes, yes.
Now,
Thank you.
this is something on deformation training. Uh, uh, so Bhargav and Rakesh, both of them are there online. They are the custodians. So I'm only whatever and add on. So this was the work which Bhargav and Rakesh, they are the joint first author of this. Of course, Anirban, Komal, Rajiv and Ankit were involved. So I'm going to talk about deformation twinning, some very minimal background, controversies and contradictions, because that should be done before what Bhargav called as new insights. I do not like that word. Then concluding remarks. Now, if I see this, and this is straight from Wikipedia, that's a piece of tin, you're bending it and it's crying. It's called tin cry. Noted on 13th AD for certain notice. So this is twinning, deformation. There were experiments by a whole bunch of people and finally led to some kind of formalism and classification, primarily by Moog. So Moog worked on autosymmetry minerals, the guys over there. He talked about K1 and K2 invariant plane notations, and basically Hursford in our textbook, it has the same stuff. You have two invariant plane, K1, K2, two shears, eta 1, eta 2, and associated addendums. So this twinning, you can see in geology, you can see in the nanocrystalline gold, you can see, of course, in the metallic material. And the symmetries are beautiful. You see all kinds of Brazil twin or Japanese twin, but that's geology. So where are the issues? Number one, there is an issue. Of course, you have twinning associated with phase transformation, but you have annealing and deformation twins. Deformation twins looks discontinuous. It also has non-invariant planes, what looks like. Maybe some of it comes from twin decay. It's not detwinning really, it's a twin decay, where OR of the twin changes with the local discreditation. But that's about enough on the background of deformation twinning till we go to the controversies and contradiction. So first of all, where does the twin nucleate? Identical orientation, neighborhood is different. It may or may not twin. Looks like the shear, local shear, isoscopic shear, decides the twin nucleation. Morphology is different. You can take a sample, deform it at different temperature, which David did, and see completely different morphologies. The crystal plasticity guys do fit and capture the work hardening, but not the morphologies. So, summary of the notes. Last I checked, 20 years, deformation twin. With this nomenclature, you have 12,000 plus journal papers. You have invariant plane strain, Moog's definition, cannot explain the 3D lenticular slate. So you have non-invariant twin interfaces. There's a huge issue about twin dislocations. So whether it's 47 or 49, it still goes on. There is an argument about non-space twins, most importantly, the twin nucleation and truths. So there I start with what Bhargav called as new insights. Just got published in 2026 in IJP. So one can refer to the paper if additional information is needed. So what Varghab did, he took a hot extruded but fully rectified titanium tube from LFC and took samples from the three sections, axial, radial, and OF. Microstructures are identical, but textures are different. So naturally, the twin propensity, which you can take as twin dominated and slip dominated Smith factors, Taylor would have been better, but there are some issues. You can get the relative twinning propensity. Experimentally, it's similar, but not exactly the same. So R is to H is 1 is to 1.5 theoretically. Experimentally, it's almost 1 is to 2. So there are differences. Most importantly, if you take a tensile sample, put it in your stage, and keep measuring, you are going to see the frequency of the twins and the size of the twins differ between two samples. More specifically, there are many twins on the grain boundary, but only few of them grow. This is here. Now, why does it happen? So what Varghab did, he started looking at the twins in greater details. You look at a grain boundary twin, there are two classes. Class 1, where misorientation is building up on the twin neighbor. Class 2, where misorientation is not building up. Remember, this is HREBSD, so this misorientation development is to the tune of 0.0006. Now, you can of course look at a sample, lift up samples, and look at the dislocations which came because of the slip transit. You can look at a simple index like elastomoris, look at the misorientation buildup, and classify your twins as N-type, which does not enforce this dislocation movement across the boundary. S-type, which does. So you have difference, sort of straight-jacketed for S and N-type, based on relative slip transfer. Does it related to growth selection of the twin embryos? Let's see that. So Varghab also followed these twins throughout the proboscis formation. As you can see, S-type has a much lower overall growth rate than N-type. Remember, this is the same twin being followed as a function of tensile deformation. Small deformation, of course. So less slip transfer looks like higher overall growth advantage. What else is there? You can look at the twin matrix interface, and you see different types of interface. Something which people call as coherent twin boundary. Very little lattice strain or residual strain. This is PD. Or you can look at the interface, irregular, more strain, distal prism, more strain, and so on. Your twin matrix interface seems to have divergent strains. So what is happening mechanistically? Just presented a bunch of results without the mechanistic explanation. So this is where Rakesh worked. Of course, this is together, and both Varghab and Rakesh are the joint first author, but this is where Rakesh comes in. He simulates this grain boundary twinning. So all you need to do is different type of grain boundaries, enabling or not allowing slip transfer, and you can impose the stress strain. Remember, stress is going to be much higher. This is after all MD. So very high strain rate. You can look at the matrix twins and stacking faults. Basic difference in the nucleation of the twin, S-type twin, it nucleates all kinds of stacking faults. Atomistically, does not grow too much. And then it leads to shear plus shuffle, finally to pure shuffle. N-type, there are no stacking faults and pure shuffle. In other words, this S and N-type, which were observed in much coarser twins, seems to be in the atomistic level having completely different nucleation mechanisms. What happens next? Of course, Bhargav gave it to me. I think Bhargav gave it to me. That is working now. So, this S and N type, based on the stacking fault, no stacking fault, it throws dislocations. You can look at these dislocations, different types of partial dislocations. You can even look at what kind of deviation the atoms has. They call it delta rad. And delta rad, or kernel average misorientation, your EBSD stuff, HREBSD stuff, they follow the same thing. N-type, low delta rad, atomistic displacement, which includes these dislocations, and a high delta rad. So, summary on the simulations. S shows the transfer, N does not. What else? These dislocations, of course, they're more in N, interfacial dislocations. They change, it's not constant. They change with the simulation time. Remember, some of them are well-defined dislocations where you can get the Margaret vector out. Some of them are ill-defined dislocations, disconnections, where Margaret vector and line vector is not well-defined. This is something which Parikh was very particular about. So, more interfacial dislocations, more energy. And the energies of this interface, S-type has Bessel prism and CTB, coherent twin boundary. Whereas N-type has more of Bessel prism, so more energy. The local energy can be measured, more interfacial dislocations, more interfacial energy, and higher growth velocity. But this is towards the later stage of the twin. What happens at the beginning? At the beginning, you can see these 1, 2, 3, 4, whatever numbers, and only 1, 2, 3 are growing. Others are not growing. This is what I would put, and this is the stress or strain. Say, one is the stress from the MD. So, this is a stress-assisted movement for the young twin boundaries. So, let me summarize. Concluding remarks, deformation twinning, I don't know, new insights or others. Grain boundary nucleation clearly differs between S and N type. It's more or less confirmed. Growth selection, initial growth selection is strain-assisted boundary migration. Later, with slip transfer, there is an overall growth advantage. Interface dislocations and disconnections decide interfacial energy and the growth velocity. So these are the final concluding remarks from what Bhargav called as new insights. I would call it as growth selection of deformation twins. So that's it. I kept it brief. So any questions I would like to answer, or Bhargav Parikh can be better off answering. I'm only the custodian, right?
Yeah, thank you.
Okay.
Hi.
Good to see you, Leo, from a
Hey.
distance.
Yes. Hey. So, no, I was confused. I'm not in at all well read in the literature of twinning, but in all classical materials textbooks, it says that you need you have twinning is an invariant plane effect, and I saw on one of your slides said this is not the case. You surprised me there.
Yeah. So if you want, I can ask Bhargav or Barik to send you the copy of the paper.
Yeah.
Bhargav, please do that. Professor Leo questions. You please send the paper.
Okay, good. Thank you.
So this is interesting, Leo, but this is one of the stuff. Bhargav has to have other stuff, but we'll see that.
So, any other question in the audience? No, I mean, thanks a lot. I mean, do you have any?
Nobody is asking me any questions. That means Satyam does not like me. I see is Suresh sitting there, right? That's Suresh. He does not like me. Nobody likes me. This is absolutely not acceptable.
Maybe we were waiting for you here so that that impact will be different.
No questions. I asked him yesterday, are you going to stay back? Hoping that. All right, guys. Missed you guys this time, but.
Will you come to Hamilton?
No. I have a few travels and. So, okay. All right then.
So with this, we will end the workshop. It was on a nice note. Do you have any concluding remarks or something from Professor Ranjit Ray to talk about? And
this is a question for me?
Yes.
See, Ranjit Ray, of course, I met many times. I also know him as supervisor of Satyam, Runan Shahandar, Sandeep Ghosh Chaudhuri, several of the students. So this has been my impression about Professor Ray. A very jolly, nice guy who is always smiling. So of course, I had no direct interaction with him. Suddenly, he came to IIT Bombay once. We had some interaction. We met socially also. The reason what I would give the credit to Ranjit Ray is there was nothing. It was a large country, but it had its own pluses and minuses. There was nothing. This guy sort of single-handedly started the subject. So, nothing else. This is possibly should be the biggest identity of Professor Ray. Unfortunately, in spite of our best efforts, the Bunga Award didn't come to him, whatever the compulsions. So that's something which I would regret. Nothing else. Okay?
Okay. Thanks a lot. Thank you. So with this,
okay.
We close this memorial workshop, and thanks everyone who took this initiative, at least to come on board. And I find it's a very memorable day for me, and also it's a tribute to Professor Ranjit Ray in itself. So thanks a lot. Thank you, everyone.
All right, guys. Bye.
So I also would like to thank Jay Gautam for taking the initiative and organizing this memorial in honor of Professor Ray. And it was great also to see the very lively, vivid texture community here in India. I think we have had a wonderful symposium with many interesting talks, and I'm very happy I made the trip. For me, it was very exciting, and I always feel honored if I can learn a lot. And in the context of the memorial to Professor Ranjit Ray, it's even a double reward. So thank you, Jay, for organizing.
A big thanks from my side also, because it was a pleasure to come here, and thanks to Dr. Jay Gautam that he organized this, even though he was not his direct student.
So it was indeed very touchy for me, and I'm very happy to be here. And for many other occasions, I would like to be here for a similar cause, right? Workshop. Right? Thank you.
రూమ్లో పెట్టా వచ్చాక నాన్న కొట్టి నీకు సరే ఒకటి